Welcome to APEC. It's December 23rd, and I am your moderator, Tim Ventura. I want to thank everybody for joining us on this call, along with everyone watching us on YouTube. We have a really special series of presentations for you today, not just one, but a series. David Paris is going to describe a new VEM Drive breakthrough. We've got video, we have PowerPoints, we have amazing materials for that. Charles Buhler is going to discuss experimental propulsion results based on asymmetrical electrostatic pressure. Again, they are getting remarkable breakthrough results with that. Daniel Davis is going to give us an overview of warp drive propulsion concepts. And Andrew Beckwith is going to come in later and discuss how torsion may allow for a cosmological constant. We have so much exciting stuff going on. We're also going to hear updates from our lab partners. We're going to be finishing off the event with an open discussion by conference attendees. And it is 2 days before Christmas. So I'm going to show everybody my Christmas hat. When we do lab time, I'm going to be putting this on, and Mark Sokol better be wearing his as well. So a couple of quick updates before we begin. Today's event uses StreamYard. We're broadcasting through the Alt Propulsion YouTube channel. We've done some upgrades on this. We are now capable of doing higher quality broadcasts, and that's something that's really exciting. We're still figuring out some of the bugs, so if we run into those, please forgive us. If you haven't subscribed to our channel, please do so now. And you can also visit our website online at altpropulsion.com. If you have questions, you can drop those in using the live chat feature on the right-hand side of the page. And I would ask you to keep your eye on that, not only during the broadcast, but also if you're watching this in replay, because I will drop links in there as well, and that will give you more resources. Also, we're going to have links to the presentations on the altpropulsion.com website. So, again, conference replays, details, and speaker info are online at www.altpropulsion.com. So without any further ado, I want to get into our first presentation. I am really, really excited about this. This is brand new breaking news. David Paris is going to discuss recent upgrades and experimental results for the VEM drive that indicate a repeatable propulsive output of 11.72 newtons, which is about 2.65 pounds of force generated by a 1500 watt input power during 30-second duration tests without any evidence of ion wind or electrostatic repulsion or any kind of conventional propulsion means. And this has also been accompanied by redshifting and other effects that indicate that, again, something more exotic than conventional propulsion is happening here. For the last 7 years, actually longer than that now, the QED team has been developing a proprietary variable electromagnetic drive that they believe compresses the fabric of space-time itself and requires no liquid propellant that chemical or ion drives might use to move through space. So let me bring David in now. David, welcome, sir.
Hi, everybody. Merry Christmas.
And I have a PowerPoint queued up for you, and we also have, let me see, we also have a video, and I can share that a little bit later. But
well,
okay,
I thought that perhaps that everybody might enjoy seeing this right off the bat. Then we can talk about the history of how it came about, where we got the idea, how it's matured over time, and all that. So I think
you want me to put the video up?
Would like to see. Yeah, if we could.
Okay, let's do this then. Okay, give me just a sec. Sorry, share screen. There we go. QED drive. And I'm going to drop this in as well. Yeah, perfect. Okay. Sorry about that. Again, 2 days before Christmas, so please forgive us, everyone in the audience.
Today we'll be going over our December 15th, 2023 experiment. It's a scale experiment with drive model number 19. Purpose is to improve upon our June 9th experiment of 4.66 newtons, which is 475 grams, of model 17, and to see if the new solid state drive is good enough for the next phase using multiple drives to create a field. In this experiment, we do 1500 watts, a 30-second test, and we measured 11.728 newtons, or 1,196 grams. This first video is showing a close-up of the scale as we power up model 19, and it is playing back at ×2 speed. This video is showing a close-up of the scale in the top right that we just watched, and the full picture of the drive in the background. A playback on this clip is 1 times normal speed, so this is showing real-time movement. Here we can see that it takes a while for the field to get going to pull the engine down, and then it seems to accelerate towards the middle, and then as the scale needle gets past the 2000 towards the 0, where it's kind of off the scale, it starts to slow back down again. Here we have our scale comparison experiments of model 19 and 17. They were both at 1500 watts, 30-second tests. And we could see the grams, newtons, and pounds for each of them, and the difference between the two. So basically, our new experiment showed us that model 19 outperformed model 17, and that it'll work for our next phase of trying to place multiple drives together. We go to the chart, we can see that there's 151% improvement between model 17, which pulled about 1 pound, and model 19, which pulled 2.6 pounds. Thanks for watching. Follow us on Facebook, YouTube, Instagram, X, and also on our website, QED-NE, where we have all our documents listed. And coming soon, we'll have a Patreon, hopefully by the end of the month, start of the new year, 2024. So if you want to donate or follow us on there, we'll have that going. Thank you.
Okay, awesome. Again, so we're already starting out with the bumps in the road, but these are all my fault. I will take full credit for that.
No problem. And that was Kyle Finley doing the narration. He's our CEO of QED and also one of our IT engineers that processes and does the data analysis and that. One of the interesting aspects of that video was that, again, the analysis that we have performed with the frame-by-frame video analysis also shows the exponential capability of the motor. And what's exciting about that piece of it, before I go into the background and the history of this thing, is that what we're trying to achieve is less input power, more work out. And with the exponential curves on the power to weight ratio, it just means that it will not need to have as much power as originally thought, like 100,000 watts of power, is that we should be able to lift, according to our indications right now, within less than 15,000 watts of power, we should be able to lift loads going to space. Now, it remains to be seen. However, we have an excellent start. The fact is that what you saw in that video, the other interesting little point is that we broke the scale. And that means that we had to pull at least 6+ additional pounds, a total of 6+ pounds of force in order to break that scale. The scale itself will handle 4.5 pounds. And the fact that we broke it, which is probably a good thing in one respect. It's bad that we expended a scale, but we didn't anticipate this performance that we got. So now we've just got in a 10-pound scale, and we're going to go up in increments there. The reason why we're using smaller scales is so that we can see the the actual incremental deviations as it goes up. On that particular scale, it was 20 grams a tick. So every little mark on that scale is 20 grams. And for us, when we play back the videos, or when we run our experiments, it's necessary because sometimes, well, up until the 15th of December, we were only getting a few newtons worth of force. And it wasn't until we had made some additional modifications to Model 19 that everything kind of came to fruition. Well, we can talk a little bit more about the actual details of the engine and that a little bit later. There are a lot of people out there who probably don't know, where did this thing come from? Where's the ideas about it? How did it happen? Next slide, please. Pilots gave us reports over the years, and we have reports from World War II all the way up to Bruce Gernon's, which is the most famous report of being linear displaced from thunderstorm activity. And this linear displacement is just not being shot out of a thunderstorm, but rather these pilots were wrapped up in a warp bubble and displaced 100 to 300 miles downrange. So nature does a pretty powerful job of creating this type of scenario. So we know it's real. Bruce Gernon's reports put us at approximately a second to go from Bimini Island to West Palm Beach, or to Miami Beach rather, and that's approximately 100 miles. And inside the aircraft, it was the pilot, Bruce Gernon, his father, and a business associate. And they had been going to Andros Island to build a resort. And this is one of the 14 trips that they had taken. And leaving at 3 o'clock in the afternoon, they got wrapped up in thunderstorms around Bimini Island. And the thunderstorms grew up to such a height of in excess of 70,000 feet. They couldn't fly over and they couldn't fly under because the thunderstorms had wrapped right to the surface of the ocean. Anyway, he saw a hole, and pilots referred to these things as sucker holes. And he took that last shot, and this is a rendition of what he had experienced. I had one of my artist students, actually. I teach college, and she put together this artist's conception of what his description was. And this is what it looked like: clear blue sky through the hole. He took it. It was his last desperate attempt to get out of the surrounding thunderstorms. And he actually made West Palm Beach, where he landed, in 47 minutes, where the normal flight time is 75. And when he landed, he always refuels his airplane after a trip. And he did not use all the fuel. He had 9 extra gallons of fuel on board the aircraft, which would have accommodated that 100 miles of distance that he traversed in like a second. So we knew we were onto something. We knew that nature did this. And being a meteorologist, a radar operator, I've done all the jobs as far as the functionality within meteorology itself. I was in the Air Force and teaching college as well as meteorology and astronomy and physics and that. Anyway, bottom line here was I discovered after several years of research, analyzing his flights and other flights that other pilots made, that nature does do this, and in the right series of conditions, which are outlined in some of the papers on our website. I would recommend, instead of spending too much time explaining those things, that go to the website, read some of the papers that we've got published and presented to get additional information. But anyway, based off of this information that this occurs in a natural environment, well, specialized environment rather, how could you replicate this? And the bottom line was, well, I did a number of TV programs for Bermuda Triangle, and as the additional, I guess, nicety was I was able to bring a lot of my equipment with me on board these flights. And so I did a lot of personal measurements, taking advantage of the free ride in the airplane. And we flew through a number of thunderstorms, and we went into around the freezing level of some of these thunderstorms. And I was able to capture the frequency within the realm of that freezing level. So we came back into the laboratory, and we set up a series of antenna arrays that mimicked the frequency of the thunderstorms, which would have created these sucker holes that Bruce Gernon and some of these other pilots had flown throughout the years. Anyway, bottom line here, next slide, please. The bottom line here was that we began to see in our lab experiments compression of a laser beam as we sent it through the antenna arrays, and we hit it through the sweet spot of where the fields crossed over. Anyway, the bottom line is that we were able to, using fractal technology, instead of using these very large cumbersome antenna arrays, was to reduce and still have the same kind of gain by using these modified Koch curves that are specifically designed to match the frequencies of the freezing level, the frequencies that I obtained by flying through these areas. And in 1995, Alcubierre leads us to some additional theoretical possibilities of creating artificial warp bubbles. And throughout his research, although the amount of energy that had been expressed by Alcubierre and other scientists that got fascinated by building warp bubbles was that it would take equivalent of all the energy of the universe to make a warp bubble to start with. And it got down to all the equivalent energy of Jupiter, and then it got down to the equivalent energy of the mass of the Voyager spacecraft converted into energy. And this entailed exotic energy, antimatter, dark energy, dark matter, all these exotic characteristics to create a warp bubble. Well, I guess somebody didn't tell us that we weren't supposed to be able to do this, but we've actually created warp bubbles in less than 5 watts of power. Now, Alcubierre, what's interesting about his concept is that you compress in a warp bubble, the compression of the fabric of space in front, and then it expands in the back at the same rate as you have expansion, compression in the front. Well, we actually found that that's not true. We can compress the fabric of space in front, but it gradually dissipates into the back end of the motor. Next slide, please. And so some of the indications that we had have been, in the beginning, we would be able to, using these, we would etch circuit boards with the fractals on them. And we started out with engines that were approximately 7 inches in length and smaller scale fractals on board these boards. And we would power them up with between 5 to 100 watts of power. And then we started to increase those power levels until, for example, like on June 9th, we had we have a total of 20 models of engines that we built and have fabricated throughout the 14 years of research. So it's a very intensive, time-consuming, a lot of money spent throughout this research period. It's you got to be very dedicated to sit there in unheated environment, not cooled in the summer, not heated in the winter, but to keep the ambient air, everything still, so that there cannot be any disturbance of the engine whatsoever. in this testing. And so we also found out, which was extremely interesting here, was that no matter what the temperature is, the motor still works the same way. So the engine is unaffected by temperature at all. It makes no sound whatsoever. And in some of the variants of engines that we have designed and tested, we also get a reduction in the ambient air temperature within the throat of the engine. So it actually has like a Peltier effect, if you would, so to speak. And that I kind of relate that to some of those Tic Tacs that the Navy had photographed or imaged with their thermal cameras, and we have thermal infrared cameras as well. And we always examine the engines right after and during testing, and we got the same effect of that cooling around the outside of the Tic Tac and the outside of the other saucer-shaped craft that they were chasing after, which I thought was kind of interesting. Led me to believe that it's probably they're using a warp bubble technology, highly more refined than what I'm doing, but nonetheless, all the characteristics that seem to be being reported, we seem to already have replicated in the lab environment. Redshift of the frequency would be expected into a warp bubble, and that's exactly what we get. The cooling aspects, that's what we also get. The pulling of objects through solid objects is the influence of other objects through solid objects is what we have also gotten. Next slide. And these are just the matrix results of the test, and you've seen this on the video part, so really isn't a lot of point going over that. But the next slide is probably the most important piece, and the follow-on slides are probably the most important aspect here. Next slide. This is the gravity data. We're using an Adafruit with a Raspberry Pi, 55 points, and we've done 7 inches, 1-inch layers from on top of the engine to the bottom of the engine. And this is the 4-inch marks here that are being expressed in this data that we collected. And the bottom line here is that within the engine itself, we have tripole fields, and there are 4 fractals that represent a tripole field, plus, minus, minus, plus, and the minus within the tripole field represents the freezing level of a thunderstorm. So that's what we've have mimicked here, is using fractal technology, is thunderstorm electric fields. And so you can see here where the field compresses down into the engine at that point, and then you'll see some null areas in the middle of it, and that's where we could put our power cables into the engine to power them up on these fractal arrays. And so there's a total of 4 tripoles that make up an engine. These are 2 foot in length. These are scaled up from our original smaller engines, and this also means that one can scale this up to even facilitate larger engines. So the fact that we got the 2.65 pounds of force out of this engine, well, that's what we measured. We know we got more, but we'll find that out with our 10-pound scale later on. But this is extremely significant here in this image of the signature of the warp field around the engine. And so you can see it starts to fold up on itself around. And what I also discovered with this is that you can take multiple motors and you can build a bigger warp bubble. So a lot of the scientists, theoreticians that have been preaching about warp bubbles, that you've got to make one large one, it's not true. You got to have to use exotic energy. It's not true. We run our engines on battery power, and we've been doing that for over 7 years now. At 48 volts goes into our linear amplifiers, and we can generate, well, within the next couple of months, we'll be able to actually go up to close to 6,000 watts of power. So power is not really so much the issue at this point. It's the configuration, design of the engines that represent the compression of the fabric of space. Next slide, please. This is how this actually works. The propagation of the near fields of the RF patterns that are generated from the fractal tripole fields. They go perpendicular to the plates of the arrays as the propagation comes out. And as we all know in the theory of relativity is that mass and energy are equivalent. And this is also where this works in that same characteristic of energy, which would replicate what kind of mass that you would have in order to get this same type of effect. Obviously, the Earth has a compression of the fabric of space around the equator regions, since we have an extra 13 miles or a total of 26 nautical miles of girth to the equator. So we have an actual compression of the Earth's fabric of space around, as well as like the sun, where the equator is also has a girth to it, and that gives us our planetary alignment. The same type of theory, or the same type of effect, and ephemeral, whether you want to look at this as being empirical or whatever, but the bottom line here is these fields cross, they create a side lobe, and it goes down into the engine. And this is what compresses the, quote, fabric of space. There's actually a fetch on these engines. In other words, fetch a downward range of the motor. There's an initial compression of the fabric of space around the engine itself, but downrange of it, there's an influential attraction. If the engine's in a static position, you can influence a torsion bar, for example, in a solid box, and it will actually attract that ball. And we have videos of that. You can see that on the website as well. So we know what's happening here, and the signature of the warp field was very conclusive then in the fact that we can compress in front, but it gradually dissipates to the rear of the engine. And so this demonstrates more of the functionality of how warp bubbles can be treated. And if we take this one step further, we could put this inside spacecraft. So you can have multiple warp bubbles even within the spacecraft to create artificial gravity. And it only takes 20 watts of power to create 2 gravity doses inside of the spacecraft. And this would allow astronauts to be feet on the ground, and they wouldn't have to do all the exotic exercises and everything that they have to do now in order to keep atrophy from occurring on the legs and arms of the body. So this would be more of a normal, natural-like environment inside the spacecraft. And we've tested biologics and radiation, and everything is, it doesn't affect the biologics of sensitive lab flies. We've done a number of tests with those. We've done radiation measurements. It's 1.5 millirads of radiation from the engine. Background radiation here on the Earth is between 8 to 18, depending upon strong side of the sun. During the day, can get as high as 24. I've made measurements here in my station that I've taken as well. So it's really a non-player when it comes to organisms to be exposed to this. And the exposure that we did to the biologic, or the lab flies, was over 1,500 or over 1,000 watts of power for several minutes. And bottom line, up to second generation of flies that we monitored, there weren't any ill effects or mutations or anything of that nature. So we're pretty confident that exposure to the engine is not going to facilitate any kind of major biological catastrophe. And the fact that at 10 to 20 watts of power, you can grow plants in 20 watts of power of the gravitational fields that we have, that we produce, and the 20 watts of power would then definitely allow astronauts to walk on the floorboards. Next slide, please. This is a, there are other pictures on the website that had probably a clearer, this is a solid state design. There's only, at this time, only 2 solder joints in the whole engine concept. And what you're seeing there is the 4 tripole fields, but all cut out with a laser. In this particular engine, these are aluminum 1/8-inch thick sheets of aluminum that are cut out with the fractal patterns and the tripole fields all laid in inside there. The variableness of the engine, we can actually close the vanes up, we can open the vanes up, and the advantage to us in testing is that we get different results and different pulling factors at 50 degrees to 70 degrees. And it could be useful in a space-like environment, not only to use as like a throttle, because we actually have a throttle that goes from 0, no power whatsoever, to whatever the maximum power you have available in your test that you want to do. So from that aspect, it is a throttleable engine, and you can do all, and with the variability of the openings, you can then modify the effects of the warp fields themselves. We haven't detected any kind of tidal actions on the outside like Alcubierre had discussed, although we're working in smaller wattages. 1500 watts isn't really a whole lot of power, but we've been able to, and I guess that's the real significance of this whole thing, is that just using that amount of wattage, we've been able to get the 2.6 pounds of pull on the engine. This is not a thrusting engine. I have to make that point known, is that this is a pulling engine, okay? And that it works differently than other types of like ion drives or whatever. Now, a lot of people will say, well, how can you compare this to an ion drive engine? Well, ion drives, they're basically cathode and an anode. They're pulling xenon gas and other types of gases through and creating a nozzle and creating a thrust, but it's very, very low of millinewtons of force that they're expending. And it takes years in order to build up in space to go to 25,000 miles an hour, 50,000 miles an hour, like Project Horizon that went to Pluto. It took them 4 years to build up to 25,000, and they slingshotted around Jupiter to get it up to 50,000 miles an hour. So in our case here, we're talking 11.7 newtons that we've been able to measure, despite the fact that we broke the scale, and it's probably even more force. But they use, like NASA's current ion drive engine, NEXT, uses 6,000 watts of power to create 0.234 newtons of force. And we use 1,500 watts to create 11.7 newtons of force. So looking at the difference of energy savings, no propellant, no moving parts. Ion drives, they wear out. They literally burn up over time, and they have to, extend the cathode and all this into the engine. So anyway, that's a whole different kind of technology. Ours is fairly simple, and we would be able to utilize existing power availability on board spacecraft and amplify it, since we only use 48 volts of DC power. So we actually use, in our battery packs, we have 170 amp hour batteries, and we run our tests and whatnot, but everything's been run, like I mentioned, it's all run on battery power. So we've been preparing to go to space for some time in that type of environment. And plus our equipment is fairly lightweight, as linear amps can be reduced and lightened up. But the picture that you're seeing here in the lower left, there's the actual throttle. We have different modes. It can be computerized. It can be manually done. I run everything in a manual mode. There's a clock up there, which is the clock from the photo lab, and that calibrates everything for us as far as we run all of our experiments over the same type of pattern, timing patterns. So the data that we get out, we can make comparisons from the different model types that we're testing at any given time. We do have software that can engage the engine as well. We're developing some newer software. The previous software was the Visual Basic, and it's not as robust, and so we're rewriting the stuff and doing it in C++. We also have the battery pack over to the right, lower right there, and the quad pictures. That's the actual battery pack that was all custom made. And the other thing I have to stress here, everything that you're seeing in these pictures were all handmade. Everything is custom, and they're not cheap. Everything is extremely expensive. The linears are all custom designed. We're using the latest chips available for power increase, minimal wattage in, and massive amounts of watts out to power the arrays. And we have the tuners and whatnot that will adjust, correct, and get SWRs down to 1.01, and that means we get maximum power going into the arrays to get maximum effects. And you can see these graphs in some of the previous models. The exponential curves haven't been as great because the different improvements in the motor have now created situations where even our R² values are close to 1. So we're approaching the full capabilities of the monitoring points, the power along with the weight, showing the exponential curves that these engines can generate. Next slide, please. Now this is our quad design, and these are articulating corners, and the motors are mounted in here. And in essence, this will allow us to gimbal these motors in not just in a downward or an upward direction, but also to use the fetch of the engines, as I mentioned before, to cross over focal points of the actual engines themselves. And it will allow us to test 2 and 4 engines at a time in a clustering environment. These can be put into a cylinder to, as an additional engine mount. But for right now, these articulating attachments, or harnesses as we call them, can be hung from the Faraday cage where all the experiments are done, and then all the adjustments can be made to these, and they all are attached to scales. So right now we're pulling things in a downward direction, and within the next several weeks we're going to be reversing that and going in an upward direction, and eventually we want to lift. It's called Bluebird. It's a prototype spacecraft that I designed and built. It's a quarter scale, and we're going to lift that. If you go to the website, you can see the pictures of the Bluebird itself that we'll be lifting off the ground. And that device, that craft weighs approximately 36 pounds, and that's what we're moving towards, is mounting these engines on the craft, and also like a quad device that would allow 4 independent engines to be lifted off the ground and controlled. Next slide, please. There's I almost forgot. There's the picture of Bluebird, and that was just one of an engine on top of the actual craft. It's full design is 30 by 30 feet, can seat 7, and we intend to build that in the future. We always have to have future missions, future plans, and this is one of those. It kind of looks like a saucer from the front, but actually from the side, it looks kind of more like a shuttle craft than anything else. But that's where the engines can actually be installed within the leading edges, underneath the leading edges, and it sees right through materials, so it doesn't make any difference what you're using there. Next slide. And our goals initially are to go to space and to provide station keeping functionality, to put this and modify this on existing spacecraft so that they can do up orbit, design new spacecraft to deploy to space with actual R-engine technology and software control. We actually are designing an AI component into the engine itself, so it can self-monitor and take corrective actions if necessary. Ultimately, to sum it all up, we want to go faster than light, and we know that's possible. And we're crawling right now, but we believe that not in the too distant future, with adequate power and engine size in a craft, maybe even Bluebird, that we'll be able to achieve that. Next slide. And you can follow us on Facebook, YouTube, Instagram, QED-CON. And that pretty much concludes the presentation. And if we have any questions, we'd be more than happy to answer them without giving away the secret sauce to the engine.
Oops. Okay. Let me unmic myself. So I'm going to take out the slide deck, and you know what? I want to bring everybody in here. We need to give Mr. Paris a giant hand. Let me see. Sir, tremendous. David, that is, so you were on an earlier conference call with us this week. That is a tremendous breakthrough. And I see Mark with his hat. I'm gonna have to put mine on. I may not keep this on.
You better. Hey, we had a deal.
We did. You know what? This hat's too small. That or I have a fat head. One of the two. Probably the fat head. But I'll wedge this on later. You know, I got it from the dollar store. That's what you get for $1. You get a hat that's too small. David, it's absolutely tremendous. So let me see. We've had lots of people in chat mention that there is background noise. Believe it or not, we worked on that before the call. We were not able to fix it. When David isn't speaking, the software takes that out, but it may reappear, and that's unfortunately sometimes we can't fix that. I would urge everyone to focus on the tremendous breakthrough that he's talking about rather than transient background noise. Just kind of a thought. But so guys, do you have any questions for David? Jared, go for it, sir.
It's two parts of the same question. So when I look at one of those fractal antennas, just a single one, right, and you have them pointed opposite directions, I'm trying to imagine the force diagram on one of those. Is the center pushing down and the legs are pushing up? Is the whole thing pushing up, or and then the one next to it's pushing down, or what's the forces like on those antennas?
They're in a V configuration, okay, and the fractals are laid out onto the we call them fractal arrays. So each side of this engine has two of these tripole fields that are mirrored on the other side of the array itself. So that they work independent of each other. The end result is that the fields cross and then go down into the engine. I don't know. I'm thinking that should answer your question.
Sort of.
There's critical spacing in the fractal arrays themselves, and that's been worked out over the years. It's taken, I can't tell you how many hundreds or thousands of hours it took to manufacture these fractals and to get them into the right configuration.
So it's a net attractive force on each side of the V, each opposing fractenna. It's a net attractive force between those two, is what you're saying. That's how you get the...
It's two near fields, okay? It's not attractive at all. It's two propagating near fields that cross. Think of it like radar. A near field on radar, a far field. Well, in this case, we're doing two near fields that are closely coupled together that cross, and that focal point goes down. It was the only way I could come up with, other than flying through two vertical antennas, transmitting all kinds of energy and flying an airplane between it to get it to do a linear displacement. I mean, I actually had that thought process to do that. But I work with fractals with the Army Atmospheric Science Lab. We're working on backpack weather stations and stuff. And there was one guy down there, Mr. Brown, and he and we talked about fractals for hours and hours on end. And it was one of these things in antenna propagation that you can, well, you have them in your cell phone now. But back then in the 1990s, this was all new stuff coming up. And we had talked about fractal antennas for military applications and whatnot. And one of the backpack systems that I had built for them, we were looking at generating some fractal antennas. Anyway, the bottom line was I got that idea to apply it into this particular unique situation to try to eliminate flying through two vertical stacked antenna arrays, kind of like two thunderstorms, and that's what we're emulating here. So each one of those fractals represent a thunderstorm, and we're crossing the fields just like they would inside the thunderstorm.
Awesome. So who else has questions? We got about 10 minutes left. Curtis, go for it, sir, and then we'll go to Drew after that.
Yeah, my question is that you brought up one possible theory that could explain what's happening. Does that theory explain all the effects you're seeing, including the radiation and the temperature effects?
You mean this in comparison to Alcubierre's initial theory?
Yeah, if that's the theory, from what I understood, you said that's the theory you think that might explain this effect. And if
yes,
if so, then
it was
predict the other.
What he had predicted or theorized, much of it actually has come true, but there are discrepancies. As I mentioned, the back end of the engine, it dissipates gradually. It does not push at the same compression rate as compressing in the front as decompressing in the back. That we noted in the signature that I showed on the slides, which will be available for everybody to look at on the APEC links or your websites there, which are fine in that respect. You can see the thing will actually taper off. So his theory there was, at least from an empirical standpoint, is not correct. The tidal actions on the exterior may be there. He was also expressing violent tidal actions on the outside of the warp bubble. We haven't seen that at all. But then again, I think the kind of power levels that he was talking about might actually do that. However, all the pilot reports that I have, the outcome of, particularly in Bruce Gernon's effect, he disappeared from Bimini Island on radar, reappears at Miami Beach, and the time signature between there, no one ever noted any discrepancies in the atmosphere, which if there were tremendous tidal rips happening as he was theorizing, either nobody noticed, never happened. And I would say that the thunderstorm themselves that he got involved with produced over 10 to the 15th watts of power. And the fact that there was actual antimatter being created inside these thunderstorms. I don't know if many of you are even aware of the fact that nature does produce antimatter in thunderstorms and gamma rays as a result. And subject to that recent discovery, 2010, theorized in 2007, 2010 was confirmed. NASA did a lot of studies flying near these thunderstorms, and now the FAA has mandated that if all possible, you are to avoid flying near thunderstorms 20 miles away. So it actually has affected aviation and some of the natural attributes of the effects of thunderstorm fields and their antimatter generation inside.
So the reason I ask is
and the gamma rays emitted. That's really the hazards right there.
Right. The reason I ask is from what I understood, that theory didn't predict things like the temperature, things like the radiation, and all these. And the reason I asked that is
this is
the theory
this is an empirical.
The reason I ask is that the theory that I described back in October, I doubt you've seen that, but if you look at that presentation, is one of the slides, one of the effects of that theory or the consequences would be exactly those things, because not only does it has to do with a background pair gas at a ground state, but not only does lowering that gas density in a volume would that reduce inertial mass in that volume, but when you're lower, that gas itself is made out of electron and positrons. So if an effect is creating positrons, antimatter, and if there's gamma rays involved, those are the exact energies that are involved with that theory. In addition, the background pair gas in that Sachs's theory is what you use for black body radiation. So if you're lower that density of that gas, you would subsequently see in an IR camera kind of like a cooling effect, where the device might not be actually cooler, but it would look cooler because the gas is less dense, so the transmission is reduced. So that's why I find it very interesting that you have these discrepancies that like match this theory a little bit more closely than it does that other theory. Thank you for the answer.
That is awesome. Wow, that's exactly what our theory predicted too, that we would have a cooling effect directly as a result of the temporal difference between energy and reference frames, that it would appear cooler, but it would radiate out its heat as it blue shifted into the external zone, where internally it would be completely fine and everything would be symmetrical, but outside that information horizon, you would end up receiving the blue shifted light that was emitted as heat. And it would be reversed as soon as you shut it off, that the object would appear to be absorbing heat from the external environment.
Yeah, and so guys, we got about 5 minutes left for Mr. Paris. David, again, I cannot thank you enough. So I dropped links to your website as well as the QED video that we played earlier in. And one of the things I would urge people to take a look at this. I mean, I've gone through this a few times. You definitely have. I mean, this is, to me, I view this as being a breakthrough. And again, you've outlined seeing red shifting. You've seen it pull on objects through solid materials. So you've seen effects that definitely go above and beyond anything that ion wind could explain. And again, in the video, and we've gone through this earlier, there's no hissing, nothing along those lines. And as someone who's done a lot with ion wind, what you're doing is far beyond the scale of anything that ion wind would produce, especially with that kind of a like an emitter. So there's something else going on here, and it's very exciting. Mark, you had a question, sir?
Drew is first, and then I'll go after.
Okay, Drew, go for it, sir.
Yeah, I don't. Can y'all hear me? Because my picture is frozen.
Yeah,
Okay,
yeah,
well,
no, I can still hear you.
I guess I don't know what's wrong with the picture. Is the picture frozen for y'all? Can you see my? Can you see?
It is, but we can hear you. Okay, maybe your
that's fine.
camera's a little frozen.
David, I just got to ask the obvious engineering question. This thing is basically a V-shaped thing, and it's got some magic, and it points downward. So, are you saying you're attracting to the floor? You're trying to pull the floor up, which obviously you're not going to do. So you're pulling the V-shaped thing down. Is that what you're saying is happening?
No, what we're saying is happening. It's compressing the fabric of space. Anything that's in front of it, it's compressing that space into the engine, which then basically it's a bubble in relative space, and it's pulling itself through that space. Whether it's in a downward direction or an upward direction, or a side, wherever you point this engine, it will go to that. If it's not secured, it will move towards that direction.
Okay, so even
one of
empty
the
space,
earlier videos that we did. I'm sorry.
Even empty space. I mean, just theoretically, you point this thing towards a little bit of vacuum. It's truly vacuum, and it would just magically pull itself forwards.
It will work in a vacuum.
Well, it's not magically. I mean, he's
no
shown
difference
this before too, Drew. So to
I
answer
get
your
it.
question, you have
I'm
two
saying-
factors: the Mach effect, which is actually a distant connection to other objects, and then you have your local space-time effect, which is the modification of the refractive index dynamically increasing over time. Both are important.
Yeah, and guys, we got about 1 minute left, so
Thanks.
Okay, real fast. David, first of all, round of applause for you. This is amazing breakthrough.
Again.
My question, I'm not questioning the validity of this drive. It's obviously doing something, but your analogy to the Bermuda Triangle, the craft that was flying between two thunderstorms. I fly a paramotor, and I've experienced turbulence before. Is it possible that there was some sort of like tailwind that was pushing the craft forward, and it wasn't warp drive? Like Drew also flies a Cessna. There are flying through thunderstorms in a small craft is really inadvisable. But if you do, there are really strong winds.
Well, the fact that he made the trip, which is 240 miles, and trying to dodge in and out of thunderstorms, he went 260 miles. He did the trip in 47 minutes versus 75 on the average time. There weren't any tailwinds in this. He would have had 319 miles an hour from takeoff to landing in order to do the trip in 47 minutes. And the fact is that the aircraft can't do more than 210, and only for 20 minutes, the wings will fall off. It's 180 knots max speed for the aircraft, and that's what he was doing at 10,000 feet. The other interesting aspect here, just to provide a little bit additional information, Alcubierre had predicted that warp bubble, you travel a straight line. Well, we actually found out that in Bruce Gernon's case, he went in at 10,000, came out at 10,000 feet. And the fact that if he went in a straight line, he would have ended up in outer space. Actual warp bubbles are affected by mass. So the mass of the Earth kept it within the curvature of the Earth, going in at 10,000, coming out at 10,000. That's what we also noted that. So if you go to space with this thing, you're going to have to account for all the mass around you, all the big stuff. To fly a straight line, you got to do course corrections constantly. It's going to require a quantum computer navigation system in order to functionally, at low speeds, yeah, you can manually do this. But if you're going to start to acquire any kind of speed to get to some place, you've got to be able to account for all the mass around you. Just one of the things that we noted in our experiments.
Awesome. And again, we're just about top. We're just past the top of the hour. So everybody, please put your hands together again. Mr. David Paris. David, thank you. We look forward to seeing more updates on your work. I am so excited to see this progress. This bodes so well for 2024. And so what I want to do now is I'm going to take everybody out, and I'm going to go to Dr. Charles Buhler. And let me see. Okay. And there we go. Charlie, welcome, sir. And you have a presentation for us as well. You guys have a breakthrough as well. So Drew from sunny Florida, Mr. Andrew Arigma, who was down there. Oh, sorry. I horrible okay. Names. So he has been on, I mean, he's a regular on APEC. He's been doing lab updates. You've been on the past as well. You guys are doing tremendous breakthrough work. And so I cannot thank you enough for doing a presentation. Let me do this. I'm going to put your slideshow up, and okay. I'll take myself out. I believe that I'm going to have to do the back and forth on it. So just let me know when you need me to advance.
Okay. There's one video. I thought I got rid of them, but there's one left in there. So I hope it works, Tim.
Oh, okay. And if it doesn't, I can always open that up. Like if you have YouTube or something like that.
It's okay. I got videos at the end if we want to look at videos. I think it'd be easier that way, just to separate them out. Okay.
Awesome. Okay.
So I can begin now. Okay. Hi. Dr. Charles Buhler. This is the first time I'm presenting at APEC. I'm very excited to be here. I've attended a few of the meetings, but not as many as I'd like to. I want to thank Tim and Mark for having us on here. Today I'm going to talk about the discovery of propellant propulsion. That's right, it is a discovery. It's a major discovery in terms of physics, which we're very excited about it. I don't know who gave the title of asymmetrical capacitors, but I will include them. They will be a big part of this. And I'm going to introduce the community, if you don't already know, to Exodus propulsion technologies. So next slide. So I'm going to give a little bio on myself, because this is the first time I'm actually presenting. I'm the lead scientist and co-founder of NASA's Electrostatics and Surface Physics Laboratory at the Kennedy Space Center, a lab that I helped create in 1998. That started in 1998. I received my PhD condensed matter physics from FSU in 2000. I'm working on high temperature superconductors at the National Magnetic Field Laboratory. Currently, I serve as the NASA's subject matter expert in electrostatics and lunar dust mitigation for the Artemis program, and I'm the principal investigator for two self-cleaning electrodynamic dust shield payloads that are going to the moon in 2024. I've been studying propellant propulsion since the early 1990s, and I am a member of the AIAA UAP group. There's a lot of people, but they asked me to join. A little bit concerned that I was only the second physicist asked to join that community, so I'm happy to do it. Our team consists of a mix of engineers and scientists from NASA, Blue Origin, Air Force, ExxonMobil, and we have a bunch of legal folks and businessmen that also give us a hand. I do have to do the disclaimer here. This presentation is not endorsed, nor does it reflect any of the views of NASA in any way. All the images, data, graphics, etc., are solely the property of Exodus propulsion technology alone. So I have to give you that caveat. Next slide. So looks like it's not working. That's okay. I could probably show it afterwards, but all you're looking at is the needle that's on the bottom. Exodus basically started with a meeting of myself and Drew, who was also on the teleconference here. When he came up to me and asked for electrostatics help. And what he gave me is two little electrostatics, he called them stingers, that were embedded in a Teflon cavity way back in 2016. And after about 4 hours of meeting with Drew, with my wife, who's also a physicist, we left his house. And then on the way home, it's about an hour drive, my wife convinced me that the stuff that he was doing was the same stuff I was doing in a different light. So he's been working on it for, I don't know, 20 years. I've been doing it for close to 30. So I decided to see what I can do. And I went home and I built this needle thruster here. And the video shows the thing moving about 3 or 4 feet across the room. It's not very impressive, but it's kind of cool. Basically, it's just a high voltage needle with no ground inside of a plastic tube and some tape. It costs about 15 cents to make. So next slide. So I initially thought this was a version of this E cross H or E cross B momentum. You guys are probably very familiar with this stuff. You know, the Slepian drive from 1949 is on here. Corum's drive, dielectric motor, Brito's electromagnetic motor. So there's all kinds of E cross H momentum drives, since we know that there is momentum stored in the fields. Now, as a physicist, I want to make sure that any kind of physics for propellant propulsion actually is based in some physics that we know. We do know that these do not give forces, not alone, because they do not possess a change in momentum or force. Feynman told us how to do that. So next slide. So Richard Feynman, the very famous physicist, gave this, he gave this example to his students. Basically, you have a charged ring on a disk where you just have little spheres, you charge them up. In the middle of that disk, you have a solenoid, creates a magnetic field. You have a radioelectric field created by the charge that you put on the disk. And then you have a azimuthal magnetic field. And then you turn on this magnet and you turn it off, and all of a sudden the disk rotates, and you ask the students, where does it get the momentum from? So what happens is, and we all know this, is you create this secondary electric field when the B field changes, called the Faraday field. That Faraday field acts on the charges. So I thought this was always a great way to at least explore propellant propulsion, because it made sense. Physics was sound. Feynman believed in it. But the analog, the linear analog to the case, was not realized. And it wasn't even really much talked about till after 2000, when this example here on the right, the coax cable example, was presented in the textbooks, both the Griffiths and Jackson E&M textbooks. And it's a very good little model. It's basically, you have current going down a coax cable, the return current's going around the shield. You have the radial component of the field, you have the magnetic field going around the axis, and then when you turn off the field, you have a Faraday field that's created to reduce the change in current. That acts on the charges. But the problem with this system is it has a third momentum, which was also discovered. It's called the hidden momentum. The hidden momentum acts on those charges because those charges are mobile. So although it's a nice example in the textbooks, it's not quite the analog to the Feynman disk as you would hope for. So I went to search for that. So next slide. So the next slide is basically just, we'll take away the coax cable, just a regular cable. And don't use the return current on the outside, just use static charges. So this is basically static charges on the outside, those are stuck. So now when the Faraday field acts on those charges do not possess hidden momentum. Therefore, the wire should have a recoil. So what was Drew doing? What were we doing here with our needle in a volume? Well, with our high voltage needle, at very high voltage, it would go into what we call brush discharge to break the air down. It would create a current. That current would create a B field that goes around the wire. The E field is still radial. And then you have a force that would take this thing to the right. What's interesting about this, the force goes to the right. If it was an ion wind, it would go to the left. But it goes to the right. So it goes with the direction of the propellant, if you will. So this is clearly something different. So we decided to try to see if we can optimize this. Maybe stumble across something. Who knows? So this is 2016. So next slide. So we made a lot of needle thrusters. There's 4 needle thrusters. There's 9 needle thrusters. There's 100 needle thrusters. I think that's a 10 by 10, and got some pretty decent results. Nothing to write home about. Next slide. If you can make needles, you can make wires. Wires go into coronas, a lot more current, a lot more discharges. You would think a lot more force. Didn't happen. So we made many types of different wire thrusters. Next slide. We made Pac-Man class thrusters. We like these because it has a cool name. But basically, you have a wire running down the axis and corona wire, and they have grounds on the sides. And say, oh, well, this is how you test these thrusters. Forces were so small. They were still there, but they were so small. We had to operate these things in what we call resonance. All of our tests are done inside of a Faraday shielded box, a clear, transparent plastic indium tin oxide box that's grounded. And the box has some weight to it. I mean, it doesn't weigh very much, but because it's made of balsa wood and styrofoam, but it still has a weight to it. And what we do is we turn it up and we operate these things at AC frequencies, low frequencies, and see if we get the box to go in resonance. So on the bottom, I have an example of one of these hundreds of graphs that we've done on the resonance. And you can see that the integral of the references of the resonance here in force is momentum. Not a big deal, just to take a picture of it, just to show you what we were getting. So next slide. We did these hundreds and hundreds of times, and then we went to the sharp tube type thrusters. So this is another type of corona generating thruster. So you can take a sharp tube, wires work, the tubes work pretty well. That device in the bottom right made some pretty decent forces. It's attached to our field, our actual meter. But there wasn't everything wasn't all honky dory here with the sharp tube type thrusters. Next slide. So once we got good at measuring these, the Trichet discharges, that's what they're called. Their positive discharges are much bigger and farther spaced out than the negative, so that's why we chose to use positive fields. The Trichet discharges were not big enough to. Oh, it doesn't have my equation on there. Well, that's troublesome. It wasn't large enough to generate the magnetic fields necessary to create the Faraday fields. So that was pretty sad. So we had to go rule out the high voltage discharges and the magnetic effect to account for the forces that we were seeing. So let's go to the next slide. So although the theory that I worked on for almost 20 years didn't pan out, that's okay. That's what science is all about. We kept testing until one day we got brave and said, you know what, we didn't think we needed the discharges. Let's see what happens if we just get rid of the darn things. So I took one of the sharpened tubes and I shoved it in a vat of styrofoam. Now, that should quench any corona or any ion wind or anything. And then we did the same thing with the needle. Just shove that in a vat of styrofoam. And lo and behold, the damn thing still moved. I said, okay, what the heck is going on here? So let's make a real one of these suckers. So let's go to the next slide. So on the next slide, oh, that's actually the force. Sorry, I just wanted to include that. So this is the force on the of 60 micronewtons, whopping 60 micronewtons. Not very much, but it's enough to show in the styrofoam, a sharp tube shoved in styrofoam. Pretty interesting result, but it kind of led us down another path. So let's go to the next slide and see where we go from here. So from here, we do the wire plate. These are fireglass thrusters. There's a lot of weird typos that are popping up here, but anyway, fireglass is nothing special about fireglass. This is glass that's used in schools and hospitals and stuff. It's basically laminated glass. You have two 1/8-inch pieces of glass with a laminate on top of a grid. Well, there's no way that darn thing is going into corona or giving up discharges. And I just turn it on and see what happens. Same thing. We got the nice resonance with this also. So what we did is there's a black, do you see the white square behind the fireglass? That's ground. So we make our fields up and we put high voltage to the grid, put a small frequency. This is only about 3 hertz or so to 2 hertz to get to resonance to watch these, those forced oscillators give us a force. So well, that was cool. What the heck is going on here? So now it's like, okay, well, I need new physics because clearly there's not a momentum being generated or field momentum or hidden momentum or Faraday momentum. So this darn thing, it better conserve energy. So now we have to go back to the physics drawing board and say, okay, what am I doing wrong here? What am I missing? So let's start with the next slide. There's some weird typos on here. Apologize for that. So anyway, does it conserve energy? Well, I learned from my years of working with the field momentum, the hidden momentum, and all that, that if you do the conventional energy to momentum classical mechanics, you get that term there, MV is equal to -2U dTdx. It's pretty standard, straightforward stuff. But I also know that from those tests, from all that testing, you want your center of mass to have a non-negative result. Basically, you want your energy of your system to not cancel completely, but to add to your center of mass momentum. So that means I need a positive sign there instead of a negative sign. So I decided to do a little math trick that we do when we go to Lagrangian mechanics, the basis of all physics. Lagrangian mechanics. What do they do in the advanced classical mechanics textbooks? Well, they do a transformation. And the transformation is not very complicated. It's the action integral. The action is defined as the energy-time product. And nature, as we know, chooses the path of least action. So taking the delta, which is a tiny change in the product of the energy-time, you can set that equal to 0. So that's just minimizing it. You can find a little simple derivation of u dt is equal to minus t du. So now I can put that back in above and I get my positive sign back. There's nothing magical about this. F is equal to minus the gradient of u dx. So there's nothing magical here, but I wanted to include it because I thought it was a neat little thing to do, to give us the positive sign, to kind of say, well, do we have a center of mass translation or not? We better, if that's what the physics is telling us. Now the next step is, well, what the heck do I use for U, my energy? Well, let's go to the next slide.
Oh, and Charlie, let me jump in really quick. I am going to do a slide switcho changeo. I'm going to put the PDF up. So what I did was convert this to PDF, and let me apologize for
That's good. I mean, I don't know what the errors are.
Yeah, it's just a conversion because it has to translate that PowerPoint. So see, it's much better. PDF is a little bit more universal
Oh, look at
format.
that. Not Spanish anymore. Okay, thank you. Appreciate it. So go to the next slide. Okay, so energy, an electrostatic system. Well, you don't have much to choose from. Usually a potential energy in an electrostatic system is QV, charge times potential. Nothing magical about that, undergraduate physics. So that's what you could use. That's what most people do use. I'm going to choose the right side here, totally equivalent energy system for fields. So instead of writing in charges and potential, I'll write it in terms of fields only. So it's the energy over the volume of E squared, d tau, times the permittivity of free space. And I can do that. It's completely equivalent. Next slide. So when I make that transformation, I got the red term there. So now the energy is in terms of fields. I stick that back into my momentum equation. Now I got to take my derivatives. Now the derivatives here are not hard, just chain rule derivatives. First derivative acts onto the volume element, and the second derivative acts onto the field. The first element down there, as you go down, the ddx of the x integral, just choosing one direction for now, is the integral of the area, E squared, times the delta of where it's at, which is at the edges. That's the sides. And the volume element, I get just basically a divergence in the E field, a gradient of the E field within the volume. So I have two force terms. I have an electrostatic pressure force. So epsilon E squared is not unknown to science. That is the electrostatic pressure force. It tells me that any system has an unbalanced electrostatic pressure force. This should give me a force. Well, that's interesting. And then you have the second force that we call the divergence in E force, or short for divine force, which is very biblical, but we like it, is any kind of divergence within the field will also give us a force. So that's neat. Now, these two are not friends. They don't play nice, but you can set up systems to make one stronger than the other. So let's talk about what we do from here. So next slide. So what is the electrostatic pressure force? Well, simply, it's basically you have two parallel plates like a capacitor, and explains how kind of asymmetrical capacitors kind of work. So you can shrink one like the high voltage side, and those little white arrows are not field. Those little white values are electrostatic pressure lines of force. So they're basically E squared, so the magnitude. And if I shrink it down a little bit, even though the area is a little bit smaller, the E squared root goes much faster, so the force goes to the left. On the right side, I could take my high voltage electrode and just shift it a little bit. When I do that, most of the E field goes to the top and the bottom of the plates, and a very small area is exposed to the left and right side. So the plate number 2, the ground plate, wins. So it's a battle between these two plates. So that's essentially the electrostatic pressure force. Well, that seemed pretty straightforward. Next slide. Well, this is easy to simulate. So now I could put this in COMSOL or MATLAB or MathCAD or FEM or whatever, and kind of optimize the length of these electrodes. I can do the spacing of these electrodes. I can mess with the gap, and then I can optimize all three of these things at the same time very easily, and I could build these things. So next slide. So that's where the forces are coming from in some of these cases. But what the heck's happening to the needle then? Now, you always got to look at the fields. So the needle, even though it was completely clogged and there's no current coming out, the fields on that needle are defined by the geometry. When you have a right angle, there's no field in the corner of a right angle. The field drops to zero there. On the outside, the field remains. So you have an unbalance of pressure on the left side than the right side. The needle moves to the right. It's not more complicated than that. Next slide. So we started building these things. We're off to the races now. So now we got a nice graphic on the top left there of what was in our patent of the divergent, the divine force things. This is a 3D printed structure. You can coat it with a metal. You can embed it in epoxy, and then you can apply the voltage, turn it on, turn it off, and as long as you don't go too crazy, you can turn it on and have a nice off switch, and you can just turn it on a smaller thrust, a couple hundred micronewtons, and very repeatable and very robust. Next slide. Then we can make these things much lighter. We can take advantage of the electrostatic pressure force. So now we can have multi-stack T-blades. So essentially, you have all these blades where on the blade side, there's no electrostatic pressure because there's too many corners. But on the ground side or the flat side or the back side, that was where all the pressure would be. You can make them thick, you can make them thin, you can play with those games. So we started making these styrofoam thrusters, and we made hundreds of them over the years from 2016 to 2019. And we named them different things. There's Mighty Mouse and there's Brack, Space Ghost. We got so many fun names for these things, but they're very easy test articles to make, and they're damn sure didn't have a lot of ion wind associated with them. So next slide. So we built spinners. So you can see a little spinner there on the bottom left, spinner on the bottom right, on the right side. Some of them are cased, some of them aren't. These are nice devices. They're fully remote, Bluetooth compatible, Arduinos, apply high voltage to them. We can operate them remotely. In fact, the test operator that we use is in Texas. He operates these thrusters here in Florida. The bottom figure is a multi-blade stack that's inside. So that's kind of the guts, what's inside the right-hand side there. If we have time, I'll show you the videos of those. And then the rotator up top is a pretzel can. Nothing magical about a can of pretzels, but that pretzel can moves like a whiz. How does it move? Well, what the pretzel can has inside of it is half of the side is covered with a ground metal, and the rod that's going down the center is a 16th inch brass rod. That's about 5,000 volts. So you want to keep it below Corona, because as soon as you get about 8,000 volts, that rod goes into Corona, which collapses the field, kills the force. But if you can go up high enough where it doesn't go into Corona, you can get a nice little force, and you can see this thing move towards the ground. Ground is obviously much bigger than the rod, so it moves into the page here. Pretty cool. Pretzel can. Very exciting. Very expensive. Next slide. Okay, this is Space Ghost. This is just another example. You can step it up the voltage, and this is way back in the day when we didn't have very large forces, but we knew what to build. We knew how to build it. We knew how to test it. Next slide. So here's a couple of cool things. This is Mighty Mouse and one of the small foam thrusters. I just put a couple examples on here. So you see a few things. You can see the E squared dependence, or the V squared dependence, the voltage squared dependence, is what you would expect to see, from the theory of electrostatic pressure force. There's two other terms. I'm going to talk about those in a little bit, but and then there's some interesting physics that goes on to those terms, which we will talk about a little bit more. But this is some of the results. Obviously, we've done hundreds of these. I don't want to show hundreds of them, but I'll show a couple hundred of them. So go to the next slide. And so here's a few hundred of them. This is over a 6-month period, 150 tests between June and October 2019. And you can kind of see different voltage levels, different force. So we knew what we were kind of doing. We knew what worked. Very surprising, very weird stuff. So we were excited about that. I mean, I think with styrofoam and tape and copper tape, there's not, not a lot could be going on there. So we decided to file a patent. We made about 3 TAs per week, and that's basically what we tested, 1 day per week with 3 different test articles, roughly on average. So next slide. All right, so the theory was nice, but it was completely not complete. Very weird stuff was happening here. No current was needed. This is a problem. You could turn these things off, the force would remain. You could put them on the scale, the force would remain. This needed some explaining because that violates a lot of things. We did see the E² dependence of the force. We had no clear frequency dependence of the field on the force. Not the frequencies we were dealing with. Went up to about 100 megahertz or something. They're not. E², the time average is about, if it's a sine wave, is about a half. So for these thrusters, the E² doesn't really, the time dependence doesn't show up as it does in RF. We'll talk about RF later, but this, for what we're doing here, there's no dependence of the force in terms of time dependence of the field. There's no frequency dependence of the field of force. Like I was saying, the polarity doesn't matter. E² plus or minus doesn't matter. Both the electrostatic pressure and the divergence samples worked. We saw the linear dependence on the area. Computational designs were verified experimentally. So we filed the patent, but other work remained. The biggest problem that we were trying to face is why the force was so much lower than the classical model. It was about 10,000 times lower. Well, that's weird. It's there. Well, the model says it should be pretty high, but it was nowhere near the Newton range it was predicting. No explanation of the linear term or the constant term in the fits. In some cases, the flow remained with the power off. That's a problem. We've got to figure that one out. We needed to test in high vacuum, and we needed the test articles to be smaller. So we had a lot of forward work to do back in 2019, 4 years ago. So next slide. All right, so we were able to do this. Drew was able to get a nice high vacuum chamber. It's a big chamber. We were able to put test articles in it. These are fancy. This is a fancy rotator spinner in the high vacuum from January 21 to 2021. To September, 146 test articles were tested. It's pretty awesome. That was a nice jump to TRL5, technology readiness level. It's a NASA term. You don't have to worry about that. But it made the testing a little bit more complicated, but it certainly made repeatability easier because you're not testing in air, you're not dealing with weirdness. Next slide. So the test setup is essentially like this. It's a horizontal pendulum. There's a digital force meter, commercial device that's used to measure the forces. You have to test in high vacuum. Ground shielding is certainly critical when you're doing DC tests. AC, you have to worry about a lot of other different things, but DC really just going to shift the fields, make sure the DC fields don't attract anything. We were able to get compact form factor for the test articles. I'll talk a little bit about that. Okay, so next slide. So, this is some of the data acquisition, fully automated LabVIEW system that we're able to do. There's his chamber on the bottom right there. It's a really nice chamber. It's got a very large viewport, which is very useful, handy. We can measure the voltage, you can measure the current, all of that in the system, the pressure and all that. So that obviously took a lot of work. Our software engineers to do all of this work, so kudos to them. Next slide. All right, so another breakthrough. Obviously, we've been testing asymmetrical capacitor for 3-4 years, but there's a lot more ways to skin this cat. Another way to do it is not to use asymmetrical geometry, just to use it in the the materials. Materials can have different permittivities. They can have different permittivities. Are nice and useful. They're dyeable. You can control which materials you use. They'll have different permittivities, and you can see that if you have a different permittivity, you can actually lower the field if it's high enough compared to a second material. In this case, this is an example of vacuum. Obviously, the permittivity of dielectric constant of 1, permittivity 10 to the minus 12. Dielectric constant of the insulators, all that does is lower the field at the interface. There's a nice way to knock off the field, see if you get any thrust. Works well, very simple to do. Easy thing to test in vacuum, much harder in air, but easy to test in vacuum. Next slide. These also actually created much higher forces for us, which I'll talk about a little bit. We developed a standard build configuration, which basically means the test articles themselves are grounded on the outside. So they're inside a grounded box, but they're grounded on the outsides of themselves. So we moved away from kind of the mechanical asymmetrical capacitors to the layered materials, if you will. Okay, we're still moving forward, but that's basically where we're at. And in this case, so we can stack these things. So the area, it should work, right? The area should stack. We can stack them. We can sandwich them like a notebook. Next slide. We did have some strange behaviors. We certainly drifted away from the quadratic term quite a bit. Samples, so again, still producing forces with no power. That's a problem. The plates were making unusual forces. Higher forces repeated without sparking or kind of any weirdness going on. So we had to, seriously start taking a good look at the fields and what was generating this thrust. So we had to do a little bit of tweaking to the theory, I would say. So next slide. So the first tweak, F is equal to epsilon naught A E squared, electrostatic pressure component. Way too oversimplified. The data shows a quadratic form. So you got AX squared plus BX plus C. The E field was all too simplified. So what we did is the first permutation is to break the E field up into its two components. There are two components to the field. There is E1 and E2. E1 is the electric field generated by the free charges. These are free charges in metal. These are the ones that come out of the power supply. They connect to the antenna. They connect to the metal surface, the metal grid, the ones you can control. And then you have the second E field. That's due to bound charges. These are static charges. They are embedded into the plastics. They are not relativistic. They are like charges from a balloon on your hair. Two totally different fields. And now we have to do quantum mechanics. I hate to say it, but we have to do it. We can't get away. What quantum mechanics did we do? Well, we knew that that first term was off by a factor of about 10,000. And the second term was off by a factor of 100. Well, that's roughly 1 over alpha, or basically alpha, if you will. Alpha is the fine structure constant. If you don't know what alpha is, it's the ratio of the Coulomb energy between two charges divided by a photon of the energy of that same wavelength. It has many, many meanings. It's a Sommerfeld constant. It's got many, many meanings. It's in chemistry, it's in biology. It shows up all over physics. What's interesting, though, here is actually the ratio of the force that we see of the free charge divided by the bound charges. They're off by a factor of 137 different. So I'm going to make that simple substitution of my E field. I'm going to put, instead of E, I'm going to put alpha EF plus EB. And I'm going to throw that back into my force equation. When I do that, I just do the simple math. I get this little equation on the bottom. And what's interesting about it, I can measure these constants experimentally. And it's been experimentally confirmed, at least for the earlier thrusters and in the new ones, that the third term, which is the constant, I can get E bound, the field from the bound charges. I can multiply that by alpha and I get the second term. That's pretty awesome. 2 alpha. And that happens in every case. It's pretty cool. So there's something to this. So next slide. So now we're not playing with bound charges, plastics and insulators. Ugh, hard, awful, but give great forces. So going from the micronewton regime to the millinewton regime. So on the bottom left there, force is dominated by free charges. So that's the metal thrusters, the plastics that don't absorb charge, all the way up to the right here where you have thin films or dielectrics that can easily absorb charge. So now you're in a different regime. Very exciting. Next slide then. Take a look at this. I'm going to give you guys this, you can digest this in its gory detail. So I'm going to skip the hard physics stuff for now. I'll get back to it, but the stopping point right here is validations and observations so far. Well, I think I can say with confidence at least 2 of the labs have validated some of our results to date, at least that we know of. We believe it explains the physics of what was seen by Becker and Bott, the Cornell group with the dielectric layers testing. I don't know if you read those papers. They did reach out to us through a colleague of ours for help. Unfortunately, we couldn't help them at that time. But I think now that the patents are out there and we're real, I think it's possible that we can certainly help them if needed. Asymmetrical capacitors, they've been observed for 100 years. No one knew how or why they work, but I think now we kind of know. We can explain momentum anomalies. This is a big problem for NASA. It's been unable to identify these for over 50 years. Satellites pass through the Van Allen belts, and when they do that, they gather charge in the Van Allen belts. So they come out of the Van Allen belts with different momentum. Drives NASA crazy. They don't know why. Well, satellite is not a very symmetric capacitor. It's ugly, and it's got solar panels. It's got all kinds of stuff on there that can, obviously feel this forces if there's an imbalance of charge on it. We think we can explain the EM drive. I think it's worth a shot. The Mach effect thruster, same thing. We'll talk about the Casimir effect. I'll talk about that. And it might explain gravity. Why not? Throw gravity in there. Just throw it all in there. And then dumb humans. One of the graphs, one of the things I like to tell people is if you look at the graphs of the force and you really look at them, like the previous chart, for example, the constant in there, when the power is off, the force remains. This is problematic. And this is one of the problems with all, I mean, not all, but majority of direct electric to force systems. What happens when you turn it on and leave it on? What happens if I put charge on this piece of styrofoam and I put that in space? How does it slow down? It could take months for charge to decay out of styrofoam or Teflon. This is why the aliens are here. I've said it. It's my guess. This is my joke of the day. So why are the aliens here? They're here to save us. No. They're here to wipe us out. No. They're here to get us off their lawn. What happens if we send a piece of junk in space that has this asymmetrical electrostatic pressure force on it, and we can't turn it off? It keeps accelerating. Well, according to at least the special theory of relativity, the rest mass doesn't change. The effective mass certainly goes way up as you get closer to the speed of light. Well, holy crap, what happens then? Your mass goes to infinity, or at least gets big enough to make a black hole. So I can't prove that that's going to happen or not happen. I just don't know. We haven't done any of these tests in space to verify that, but it leaves open the possibility of what the heck is happening there. All I do know is that something fundamental is happening. And I don't have all the answers, but I have a few clues. So let's talk a little bit about some of the other things that we think we've seen. So let's go to the next slide here. So the EM drive, Sunny White's EM drive. It's a beautiful thruster. It's a resonant cavity. RF is a great thing to use. RF doesn't have any wires to it. You want to send energy down a system, you use RF. It's a great way to do it. He's got an asymmetrical capacitor here, whether he knows it or not. So essentially, you have I just put a constant charge density in here. I didn't do the COMSOL RF modeling, but if you just take the size of what the EM drive looks like with our little alpha factor, our epsilon naught E squared area, orders of magnitude stuff, nothing massive. And you give them the highest field you can put inside that. So that's about 10 to the 8th. 10 to the 8th squared is 10 to the 16. So that's what that 16 comes in that math down there. The highest field they can get. They load it up. Just as before, field is not allowed to exist in corners. There's no field allowed inside corners. But on the larger side on the left, you're going to have more electrostatic pressure than the side on the right. Theoretically, about 100 micronewtons, roughly, order of magnitude, what you should be able to see with the EM drive. Pretty close to what they have seen. It's possible that this could describe the EM drive. Next slide. Woodward's Mach effect thruster. It's got this piezoelectric plates. I don't know how well you guys follow all this stuff, but they've got the piezoelectric plates. There's about 2 kV in there. In theory, use this model to kind of say, well, maybe there's an asymmetrical field inside this. 2 kV is not a lot, but there's a sizable field there. you can get 1 to 10 micronewtons of thrust just on that alone. It doesn't have to vibrate. They see about 2 micronewtons. It's possible that this is just another effect of just an asymmetric pressure, electrostatic pressure. Next slide. Oh, can't do anything until we talk about Bob. So what about Bob? Next slide. Not that Bob. This Bob. Yeah, Bob Lazar. Good old Bob. Next slide. So Bob Lazar, he was a big proponent of the gravity waves in the 80s. And at the time, I didn't believe a thing he said, to be honest. The gravity wave thing, that was the buzzword of the 80s. If you're going to use a buzzword, I'm not going to buy it. But here, he said something different about, I guess, a year and a half, 2 years ago, when he started drawing some of this down, a little bit more detail. And then things got a little interesting. He did mention that there was a source and that these waves traveled down these EM traveling wave guides, which I think they actually were waveguides. Maybe not for gravity waves, but they were probably for EM waves. Then they would go into this amplifiers and then go into these emitters. And the force is always in the direction of whichever direction the emitters go. Reminiscent of what the electrostatic pressure force would do, would go in the direction of where you point it. Element 115. My wife and I looked at this. She's an RF expert. And it's been theorized that element 115 was his transmitter. And the only thing we know about it, 115, we only made about 4 atoms of it, but it's theorized to be a very high melting point. And I think that's exciting because if you're going to do a resonant cavity, an RF cavity, the problem, the reason why we don't do this is because if all this energy it's trapped, it's going to go right back into your emitter, your transmitter, and it's going to melt it. It's going to melt, and we don't have materials that can sustain really high electric fields in RF cavities. We just don't have it. So it's possible that maybe the aliens figured out a way to have a very high material with a high melting point. Not only did that, Bob Lazar also showed us the size and the shape of how they chopped up and sliced the element 115. Well, that's wonderful. Thank you for doing that. That gives us the wavelength and the frequencies of what you're testing. So pretty cool. And another point, just in general, alien spacecrafts are this 3-metal sandwich. Well, what the heck is a 3-metal sandwich, right? There's the bismuth, magnesium, all that stuff. It only makes sense in the RF world, right? Because those materials have different permittivities, dielectric constants, if you will, permittivities as a function of frequency. So when you get to those higher frequencies, when an insulator becomes a metal, metal becomes an insulator. That's a big deal. That's important. It's important for this theory, for that to happen. We're going to use it, not just for direction control, but also other things, which we can talk about at another time. But all the spacecraft material and the alien stuff is always so light. It always bothered me. I mean, it just always bothered me. Why make a spacecraft light? If you're going to make a wormhole or a black hole or something, and you're going to walk right through it, just send the Titanic. Why are you going to make it light? It always bothered me. So, because we know how hard it is to make things light. It's incredibly difficult. We even found, they even found isotopes of materials that if we tried to do this in the lab, we could. It's cost millions of dollars. We can do it, but some of this wreckage or objects that were found have isotopes where they remove the neutrons from atoms. And why the heck would you do that? It doesn't change any of the properties of that material doing that, except for one, and that's the mass. Why change the mass? Maybe, just maybe, their force is the same as ours. Just an incredibly weak ass force. And you need it as light as possible. Maybe. It's just an idea. Next slide. All right, now let's get into the meat of it. Hope you guys are ready for some quantum. I'm not going to go crazy in this. This is Casimir effect. If you know what the Casimir effect is basically you have 2 metal plates and vacuum, they attract. Why do they attract? I'm not going to go through all the physics here, but you can see the math there. So you have the electric fields. The energy of the electric field is a product or an addition, if you will, of the E field and B field. These are not quantized fields now, quantum mechanics, given by those 2 little equations below it. I'm not going to talk about the Fourier components and the transformations and the polarization vectors and all that jazz. But essentially, if you were to take the average of the E field, or the average of the energy of the E field itself in vacuum, it's zero. Pretty simple. So if I take the little average of the field, it's zero. That means the energy is zero, average energy. However, the average of the fluctuation is not zero. So what's the fluctuation? That's E times that E star right there. And that number comes out to infinity. Ugh, infinity. So the fluctuations are non-zero. So the 1/8 pi, theoretical physicists don't like to use real math because they don't ever have to build anything, but that's equal to epsilon naught in SI units. So what that means is that E field, that's at the top there, squared times epsilon naught. Guess what unit that is? That's electrostatic pressure. That is electrostatic pressure. So what do you do in the Casimir effect? So the Casimir effect, you have an infinity to the left and an infinity to the right. And then in between, you also have an infinity, but it's the difference of two infinities. But there's one little catch. In between the plates, the wave number kz is quote unquote quantized. Basically, there's allowed values. And those values are in orders of parameter d, which is the spacing. So basically, you're using Neumann boundary conditions, just like we do with photons, to have allowable modes and non-allowable modes. How many there are, we don't know, but there's a difference of infinities. So someone got really smart, Casimir, and subtracted those two. So next slide. Subtracted those two infinities. And when you do that, energy difference within the plates and all of that, and then once you get the energy, you take the derivative to get the force, and you get the force of attraction between the sphere and the plate. Well, I think that's interesting. And the reason why that's interesting is the energy per volume is pressure. And in this case, it's the electrostatic pressure. So one way to look at it is, oh, I have an energy in the middle that's lower than the energy on the side, so they move in together, they're close. But an equivalent statement would be, well, I have a higher electrostatic pressure on the left than I do in the middle, and I have a higher electrostatic pressure on the right than I do in the middle. Remember, energy per volume is pressure, and they're both in units of Pascal. So I think that there's something there to be said about what is gravity. I mean, this happens naturally. There's no power associated with it. This is just an artifact of the vacuum, the quantum vacuum fluctuations. Now, it's not going to be a nice straight cutoff between an object with mass and an object than a metal plate. You don't have the same Dirichlet or Neumann boundary conditions, but you do have some kind of grid, if you will, or some kind of something in the way that can lower the quantum vacuum fluctuations in between two masses in the universe. It's not my theory. It's been around for a long, long time. But I think now, in the context of electrostatic pressure, it might be worth looking at again. So I'm just interested in working with any physicists who would like to see that. All right, so just a few little thoughts on that. Next slide. All right, thrust per mass. Where are we at today? So this graph is our thrust that we're making versus the mass of our thruster and units of Earth's gravity. So one, the red line there, is can the thrust that we're making lift up the thruster? And that's where we got a few weeks ago. So back in 2016, we started this. All the asymmetrical stuff kind of ended around 2019. And then post 2020, these were all thin films, dielectrics, moved on to charge injection systems and solid state versions and all of that. So we're moving right along very, very quickly. And we're excited to see these thrusters that Drew has been making, see how they perform in air. So that's where we're at today. I didn't have enough time to go through in detail 2020 to 2023, but I'm sure I'll be invited back. And then the second patent is now it's not released yet, but it was submitted about a month ago, and that kind of covers everything in the last 3 years, post 2019. We understand what's happening. We think we've discovered a phenomenon. Can't really explain all of it perfectly well, but we're onto something. mean, you can only have so many theories with tape and needles and foam, but something's obviously happening there, and we're excited to share it with you. So I think that's my last slide. I do have a lot of references and stuff for people to look at and read. Our website's about to come online. We'll have videos and stuff there, and I could share a video, Tim, if you want to.
Yeah. But
If we have
you know what? Yeah. If actually,
You
if
want
you
to do
want to,
questions first.
yeah. Well, why? You know what? Why don't I bring everybody in first? Because to be honest, Charlie, you have stunned me, and that almost never happens. So, like, I'm literally stunned. We lost our Christmas hats. Here.
Oh, Mark's got his.
Okay.
Who's got
I'll
his?
bring Dan in, and let me see. I think that's everybody who has their. Yeah. So everybody, Dr. Charles Buhler, enormous applause. I would say this is a historic APEC conference today. I mean, absolutely historic.
It absolutely is. You'll see that Space Case Zero is probably in the background there. He has major bandwidth issues, so his
Okay.
cam is likely not on. But I'll vet him. And him and I have been working together and doing a large number of experiments dealing with specifically magnetic pressure, whereas this presentation today from Charles talks about electrostatic pressure. We've been dealing with the other side of that equation. And we've had several successful experiments that really lead into a possibility of a very, very powerful and high density warp drive field.
Yeah. Well, Jeremiah, let me go to, so I guess the first things first, in terms of questions for Charlie, that would be the absolute first thing. And again, this is for me, literally mind blowing. So let me go to Jared first for questions. Okay, Jared, go for it, sir.
So Charles, seriously, one of the best presentations. I can't stress enough how appreciative I am that you went into the meat of the math and the physics behind all of it, and you walk us through from beginning to end. Look, this is totally legitimate because X, Y, and Z. I absolutely love that. So thank you. So my question is, you mentioned that you are part of one of the UAP UFO groups there. I was wondering if you have drawn upon any of the resources or witness testimonies or anything in that field to help aid you in this, because I think of like Bill Uhouse mentioning the 6 million volts. I think of the ionization colors that you see around craft and flight that is hundreds of megavolts, and I'm sure there's much other resources out there that talk about these potentials that you see around the crafts.
Yeah, unfortunately, I just started. I just got vetted last week, so they haven't released much to me yet. At our first meeting with the community, a couple of gates to allow in, but I haven't anything concrete yet. That's my aim. I'm very interested in the signature. My expertise is discharge physics and all of discharge, sparks, corona, lights, glow, discharge, that. So I am interested in what the RF signatures are, what the spectroscopy is around these UAPs, and see what kind of to look at them. Saddened to hear them only the second of the 30,000, but you know, I'll be happy to look at it, see what I can do. I mean, and I'll come back and report to you guys. So, something learn something from me. I don't know if we have the tools to see what we want to see, but that's the biggest thing.
Okay, well, thank you. Let me go to Mark really quick. Mark?
Hey, Charlie. I don't know if you had a chance to watch the previous presentation from David Perez. Does your theory explain how his drive works?
It probably does, but he won't tell me his secrets, and I don't want to give him mine. We'll have to talk. Honestly, to be honest, I haven't spent a lot of time looking at his thing, so I don't really know. But I mean,
his thing does use RF and standing waves in the near field, so it's like building up charge in free space, which you said you had pretty bad results with, in terms of capacitors. But he's building it up in free space away from the array, so there's like unlimited amount of power you can throw in there. But they did notice when they turn the device off, the thrust continues. Not indefinitely, like you're saying. It continues for a number of seconds.
Yeah, so, I mean, it's possible. I mean, the reason why thrust continues is because you have trapped charge in something. And if he's trapping charges in his dielectric, yes. The one thing RF can do.
They're not really using dielectrics in that sense. They're just those are just for holding it in
So
place.
they're
Not
embedded
really-
on something.
I wanted to mention this case of George Pigott in direct relation to what you're saying, Mark.
Jeremiah,
Uh,
just one
well,
more thing.
Hold on, guys. Let's try and keep the questions focused on Charlie and Drew's presentation, right?
Right. And one other thing, I know people are throwing around all these terms, warp drive and whatnot. Do you actually believe this is a warp drive? And in what sense is it a warp drive? Does it equate to Alcubierre warp drive? Or
I mean,
these terms?
To be honest, it's, general relativity is not my strong point. I'll be the first to admit that. But I also, I'm trying to see if it's needed. Okay. We don't know much about the fabric of space-time, what it is, what makes it up. I personally think it's not necessary, but I don't know. I don't want to say that someone's wrong, but I'm also not sure that it's absolutely necessary. Physics is the one thing about physics, and I think that the important thing you want to make is if you can't find 5 different ways to explain the same thing, it's probably not true. So anytime you make a statement in physics, you better find 5 different ways to prove it. And the warp drive is another way to prove that gravity exists, just like Newton's law is another way to prove that gravity exists. Pushing gravity is another way to prove that gravity exists. So you can't just discount them. They all have varying degrees of truth to them. But they're not useful for me as a physicist. The warp bubble. Okay, great. The warp bubble. What do I do with that? What do I do with it? So I'm interested in forces. I really don't think I'm bending space-time with a needle in high voltage. I just don't think I'm doing that. Now, there's ways to test that. You can do some Millikan experiments. You can do some spectroscopy. You can do some, you can use
Laser interferometer.
A lot of ways to do it. Interferometry, you can do that. I'd like to see that. I want to see that kind of, okay, I've bent space-time. I want to see that. It's probably out there.
Yeah. Yeah, David has done that and saw movement in the laser, but continue on to the other questions.
Okay.
Well, if I could ask a question really quick. So, Charlie, one of the things that you had mentioned, and I want to focus in on this, was the model that you've developed can explain a lot of other things. And so part of that's historically, we can go back through stuff like Biefeld-Brown, right? But there are a lot of other experiments. And I think several of the folks here have touched on this in their comments. Is that something that you might consider focusing in more on in the future? Like, how could this model help to explain some of these anomalous results that we've seen in other experiments?
I mean, I'm hoping to at least try to scratch the surface for that, right? The EM drive, the Mach effect, the thruster, the T. Thomas Brown stuff. I try to scratch the surface. I can only do so much in an hour. Mark would like me to focus on the VEM drive. I'd be happy to do it. There's always different ways to skin the same cat, and we haven't talked about RF for our thrusters yet. We haven't done it yet, but there are other things. If you have something in mind that you think might be an electrostatic pressure, we just don't know it, let me know and I'll take a look at it. These things are easy to model. They're easy to check.
Wonderful. Let me go to Jeremiah, who's been very patient. Jeremiah, go for it.
Well, I can't take credit for being patient. I mean, I was disruptive as I usually am, overly excited because this stuff is exactly what I've been trying to proselytize, if you will, for fucking years now. And so what he brought up, Charles, you had the absolute perfect best presentation. Again, what Jared said, that I have ever seen. I did a presentation on APEC some years ago talking specifically about gradient field drives and exactly on the stuff that you're talking about now. And there are a few people who have really done the investigation, seen this stuff, and I'm so impressed with that. What I wanted to mention is specifically about one of the most phenomenal factors of these types of drives, which is the delay or the decay of the field force once the voltage is stopped or once the current is stopped. And so this effect appears to be directly related to the Mach principle, where outside coupled matter, where the field is generated from the moment that it is turned on, begins to propagate out through all of the physical matter and through the free space, and it couples with external matter at a distance based on the light speed bubble through the permeativity and permeability of that given material because of its refractive index and the fact that it's slower. Light travels slower through the Earth, for example. So it seems that for the forces to balance, for them to completely decay, the field has to decouple from the farthest point of matter that it was able to couple with. And when that force finally comes back at the velocity c through whatever that refractive index is of the material that it's connected with, then the force decays. So PNN has reported almost a minute of decay on their V-shaped drive. Perez is talking about several seconds. Back in the day, there was a case from George Piggott, and he was using a 500,000 volt CO2 pressurized enclosed Wimshurst machine. And in that machine, he was producing from a 3-foot distance above ground a small sphere. I think it was like a 4-inch sphere with a 16-inch base plate, and had levitating spheres that would produce exotic vacuum objects around their perimeter and have a glowing plasma surrounding the surface. But after he shut the machine off, it was 1.2 seconds after even electrically disconnecting the wire before they finally fell down. And so this effect, we see it again and again and again and again throughout history in all these drives. And this speaks to something much more fundamental about gravity, which is we have two kinds. We have our aether gravity, which is directly correlated with the refractive index of the localized vacuum space. And we have a second kind of gravity called matter gravity, which is directly correlated with the physical polarization of all the subatomic particles in the physical matter. And I thought what you talked about today, it directly correlates with recognizing these two types of different gravitational forces that have directly to do with time. I just wanted to at least mention this in the context of what you brought up because of this excellent presentation so that we can start to think about how we can screw with these things.
Yeah. And Jeremiah, did you have a question?
I mainly just wanted to bring that up and see if you had any thoughts about that. You know, have you ever thought about these two different types, you know, the Mach principle versus the local?
No, I think you're way over my head there, dude. Look, my expertise in electrostatics. So when we put charge into an insulator, it takes time for it to come out. And as long as that charge is stuck in there, the field remains. If the field remains, the force remains. Beyond that, I got nothing, man.
I'm sorry to be so. I'm
No,
sorry
that's
to
okay.
bring all this up, but thank you so much again. Best presentation I've ever seen on this subject. Absolutely,
You're
hands
super
Jeremiah.
kind. You're making me want to come back.
So let me go to Curtis really quick. And Curtis, you had a really quick question, and then we're just about out of time for this. We have to go to Dan. So
yeah, Charles, real quick, if you're looking for someone to talk to about theory, I'm interested. Just let me know. So I don't know if you saw my talk back in October that I gave, but yeah, I'd be very interested in collaborating, and you know, and if you could like look at that and let me know what you think. My main question is about the Casimir force. Do you really think that is you know, explained well enough conventionally to be an anchor for this?
I think it is. I mean, it's, you know, I've been in the textbooks a long time. It's been experimentally verified. It's kind of straightforward math. There's no magic to it. Now, is it electrostatic pressure? I think that's sounds like a stretch, but I don't think it really is. It's energy per volume. That's pressure. It's not. It's just another way to look at it.
Yeah, and I'm in agreement in terms of like what we need to. I think what I think we need to do is find what the fundamental physics is and confirm that. That's what we got to look for, and I think that's, you know, I don't know if you agree, but that's where what, you know.
Well, you start from the fundamentals and the 0 point and stuff, but you know, who cares about no energy thing? I don't mind putting energy into the thing. When I put voltage on my capacitors, there's a lot higher than 0 point. That's where you see the magic. So
thank you.
Wonderful. Guys, again, let's put our hands together. We're just about out of time. Let's put our hands together. Charlie, I cannot thank you enough. I'm literally stunned. Absolutely. Yes, please come back and tell us more. Please answer questions for us. Yes, we are not worthy. So
you guys are great. It's fun.
Yeah, well, and I know everybody has lots and lots of questions. I'm just trying to keep our time on track. So thank you yet again, sir. Let me go to Dan. I'm going to remove everybody else out. And let me see. I lost my notes here. Mr. Daniel Davis is going to be giving us a lecture on the current state of research into warp drive propulsion. And let me finish taking everybody out of the studio. Okay.
All right, you hear me?
Yes, I can. I can. You don't have a PowerPoint. That is totally cool. I'm going to remove myself. I will mute myself out. And thank you, Dan. You were in the open mic last week, and you had absolutely brilliant comments. You were discussing things with Jack, and so I said, please come back. So thank you.
All right, so just to give you guys like a quick outline of what my talk's going to be about today, we're just going to go through some very basics of general relativity first, just to make sure that we're all on the same page. Then we're going to go and we're going to write out the canonical form of the Alcubierre metric in its simplified implicit form, and then we're just going to go into some problems with it, and then we're going to go into some modifications of it that start to solve those problems. So we talk a lot about warp drives, right? So what is warping? You need to warp space and time to get some type of propulsive effect. How do we do this? Well, we already know how to do this, thankfully, to general relativity. So if we start out with our g mu nu equals 8 pi g divided by c to the fourth t mu nu, excuse my notation, that's not the best here. So summed up in the term coined by John Archibald Wheeler, you have your space-time curvature tells matter and energy where to go, and then matter and energy distributions tell space-time how to curve. So now that we have this kind of basically covered, what is we're gonna get rid of this for right now because we're not really that worried about it, and we're just gonna focus on our space-time metric. So what is our g mu nu? Okay, so we can normally it's a series of 10 partial differential equations. Your clocks, rulers, and protractors. Right now, we're only going to worry about the clock and the rulers. We're not going to worry about the protractors. So we can say our g mu nu is equal to g 0 0, g 1 1, g 2 2, and g 3 3. So these correspond to our t, x, y, and z dimensions. So we can see over here that our ds squared, ds in general relativity is going to be our geodesic, equals dt squared. Now, at this point, we need to talk a little bit about just choosing a signature for our metric. You can either do positive, negative, 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 or negative, positive, positive, positive. Just for today's sake, we're going to be doing our chosen metric is going to be positive, negative, negative, negative. So minus dx minus dy and minus dz squared, squared, squared. Okay, this should be mostly review for you guys so far. All right, and so this is just your basic form of your metric tensor and what it's mapping out. So what is the Alcubierre metric written out in this? So we can say that it is ds squared equals dt squared minus, and we're going to have our bracket here. We're going to say that this is for a spherical warp bubble moving in the x-axis with time. So dx minus v. F is our shaping function. R tells us that it is a spherical bubble. dt brackets squared minus dy minus dz squared and squared. So what does all this mean? So obviously, we have our time, our x, y, and z dimensions. As I mentioned, this is for a spherical warp bubble going in the x-axis through time. Okay, so we have our x right here. So what are the v? The v is the velocity of our bubble. F is going to be our shaping function, which informs us, what's the, it should be pretty self-explanatory. What is the shape of our bubble? And again, as I said, because we have R right here, we can infer that our bubble this time is going to be spherical. Okay, so now what does this mean? If we're going to draw out more of a visualization to help you guys, we're going to have our geodesic right here, and here's our positive well, here's our negative energy well, and we're going to put our little craft right there. So this is what's going on. This is what people are meaning when they're saying you're contracting space-time in the front and you're expanding space-time in the back. Now, again, this is an oversimplified implicit form of the Alcubierre metric. I don't really have enough room to write that entire thing out here with my board size and keeping the camera where it can see it. Okay, so now there are normally some problems associated with this. So what are our 5 problems? There's traditionally 5 associated with warp drives. Okay, first is going to be our energy requirements. So 1, 2, 3, 4, and 5. So first is our energy requirements. It was shown not long after 1994 when Dr. Miguel Alcubierre put out his original paper. It wasn't shown long after that in subsequent works that it would take, I think it was on the order of 10 times the amount of mass in the observable universe in order to create this space-time geometry. Now, I think it is worth noting that Normally, when you solve for general relativity, you start with a given mass energy distribution, your T mu nu, and then you solve for your spatial curvature, your G mu nu. Alcubierre, he ran this backwards. He started with a particular G mu nu, and he solved for T mu nu. And this is how they started to figure out how much energy this is going to require. So if you need 10 times more the amount of energy that's in our entire observable universe, obviously that's not going to be good. On top of that, you need to worry about exotic mass or negative mass, meaning that it violates the weak energy condition. Now, we don't know of really anything in nature that gives us negative energy, with the exception of the Casimir effect. But as we should know, that the Casimir effect is a very weak force. It is nowhere near large enough. Nowhere near large enough to give us 10 times the amount of what would even be about the mass energy of the entire universe worth. So again, two very big problems. Third, and it's going to be related to the fourth, is going to be our horizon problem. Now, what is the horizon problem? Once the bubble is turned on, effectively, it was shown in certain papers that the Alcubierre metric, anyways, in particular, the bubble itself, especially as it's approaching the Planck length with the thickness of it, it starts to act like an event horizon, and which comes with this is a few kind of nasty implications for any engineering implications. One is going to be the Hawking radiation that comes off of it, especially as, like we said, if the thickness is approaching the Planck length, the Hawking temperature that's going to come off of it, the Hawking radiation that's going to be coming off it will be on the order of the Planck temperature, which is, if you're familiar with the Planck temperature, this is going to be very, very bad for our crew. On top of that, any signals, electromagnetic signals, photons, anything that we want to send to further manipulate our bubble once it's already once it's made, they'll never get there, because again, this is why it's called a horizon problem. So that brings us into our radiation problem, which is in part related to the horizon problem. Now, there are still some radiation problems that are associated with the warp drive. We will get back to them a little later. And then finally, and we will touch on this one last, causality. Again, if you're familiar with relativity, and this should be more of a review for you guys this far, if you're going faster than light, you're also implicitly going back in time. You're starting to behave more like a tachyon, for if you want to choose that terminology. And this has some implications of it that become paradoxical to our everyday thinking, and we need to account for this. So, what are some things that we can do to address each of these problems? Now, it should be noted, again, the original Alcubierre metric came out in 1994. We are approaching the end of 2023 as we speak, so we are coming up on 30 years of having warp drives in the scientific literature. And as I'm sure many of you know, and you can imagine, there has been some work that's gone into this since then. So what are some things that we can do to reduce our warp drive energy here? So you had a series of papers by like Heisenbergenfeld, Gianluca Persiano, Carlos Barcelo, I think is his name. I don't want to spend the whole time just going down an itinerary of people that have worked in this field. It would be rather exhaustive. So if we're going to start out with like let's just write up our original Alcubierre metric up here, just so we have it to compare it to. So our df squared equals dt minus bracket dx minus vfr dt squared dx dy square. All right, so now how can we modify this? Okay, so one thing that was done by Barcelona is he started to ask, what happens if you start to make it more aerodynamic? So we're going to start to notice right off the bat, one of the first changes people start making to this is to the shaping function. And so in his paper titled Warp Drive Aerodynamics, and again, this is a much more of a qualitative overview and then instead of a quantitative talk. So if we're going to, let's say we have our spherical warp drive right here. Now let's just assume that, when we're going faster than light, the vacuum itself starts to act a bit like a fluid, okay? And so we're going to start to get energy that comes and it gets blue shifted and it gets trapped in the front of our horizon right here. Okay, and that eventually will destabilize the bubble. And if we find a ways that it not destabilize the bubble, again, it's a lot of energy that we're going to have to figure out how to deal with. So what he does, so he kicks us down into 2 dimensions, and he assumes the metric of this. So we're going to say dt squared minus, in our bracket, we're going to be v, and then xy dt squared minus dy squared. Okay, so this is just a very basic, simple change. And what he's basically making a tic-tac shape. It's a symmetrical ellipse. So we're going to, and again, you guys can find these papers. Go read these for yourselves. Don't take my word for this. I would encourage people to try to come to their own conclusions on these interpretations. So what he finds out is you still do get a point of blue shift here, though it may no longer be infinitely blue shifted. That is important. But what he finds out is much of this radiation starts to follow a geodesic that goes around the ship in something very akin to laminar flow. And this right here alone goes a very long way into reducing our overall energy requirements. Okay, this is good, but it still requires negative mass, and we still have the horizon problems. So let's go look at another one, someone else's modification to this. So we're going to go now to the work of Gianluca Pierciano, who has put out a series of papers on this since at least 2016. He might have been working on this earlier since that. You'll have to go and double check. Okay, and so he gives us the metric. So again, we're going to have our ds squared equals dt minus squared. Again, I should have this squared up here. My bad. All right, and then we're going to have our dx minus v. All right, and here is where it starts to get different. So our shaping function goes up here. And then x, y, z. So again, we're working in 3 dimensions instead of just 2 right now. Minus k, this is a dimensional analysis of our scalar constant, and t double parenthesis divided by a, x, y, z, k, t parenthesis, and then dt bracket square dy minus dz. And again, everything here is assuming a warp bubble moving in only the x-axis. So what's going on here? As you can tell, there's quite a bit going on here that becomes different. So first of all, our shaping function becomes complex. We can make it different shapes. This kind of builds on the work of the aerodynamic warp drive paper to some degree, where we can now start to really play with the shape of our bubble to get as many of these geodesics to go around the ship as we can, instead of getting piled up in the front, causing our blue shifting problem. Okay, so now we notice this parameter over here. So we have the shaping function divided by alpha, and then again, we have our x, y, and z, k, t parameter here. So what this does is, again, this is a bad qualitative overview of what's going on here. Again, go look this stuff up on your own. It starts to it makes the bubble even more dynamical. We can start to play with how it's shaped through time. We can make it asymmetrical. And this starts to do some interesting things for the fending zone. Now, the fending zone of your warp drive. So again, here's our warp bubble, your fending zone. So this is going to be your overall bubble. Okay, and the fending zone are the areas right here where the warping is specific, but is not your area of flat space-time here. So what does this metric do? Now, in the words of Pierciano, you are able to reduce the energy requirements to quote-unquote arbitrary values. You'll have to ask him what he means by arbitrary, because I've been trying to figure that out myself still. And on top of that, he also is able to lower the exotic energy requirements to, he doesn't get rid of them altogether, but though there are papers that do that, like Schoenfeld, Levigny, Heisenberg, Eric Lenz, and a few other, Chance Glenn is another one. And so, where am I going with this? Sorry, look at my thing here. Oh, I said this how this starts to solve the horizon problem too. So how is this solving the horizon problem? So as we as we get into that Fenning zone that I talked about, it no longer becomes singularity-like. You no longer have a Cauchy horizon in it, and therefore it no longer exacts or it behaves exactly like a event horizon anymore. Now it's just a well of severely relativistically dilated space-time. And so if we have a positive space-time well here, well, what happens? Time slows down in your warp bubble. So the Fenning zone of your warp bubble actually experiences time at a different rate than the flat time of your warp bubble and then the real time on the outside of it. So this is kind of how he reduces the energy requirements. And in terms of the exotic energy requirements, well, he's not getting rid of them altogether. This is what I was going to say that I was drawing a blank on. He's not getting rid of them altogether, but he is reducing them to an amount where the Casimir effect might become viable to use. So we've gone over a couple different views on modifications to the Alcubierre metric. People are not unified in these yet. Okay. And that needs to happen to some degree. So if we're going to go back to this here, we have our positive well, we have our negative well, but we don't need our negative well anymore, at least not to some degree. So let's just say if we go, we're going to turn to Lavinia Heisenberg's work. No, I'm not going to write out her equations because she takes a little bit different process with your scalar and vector fields. It's a lot more to write out. I'm not going to waste your time with that here today. But essentially, what she and a few others finds out, we can turn this into positive energy 2 instead of negative energy. And so, unlike Parisiano's metric, where he's reducing the negative mass to where the Casimir effect might become viable, they're getting rid of it altogether. Now, when we're dealing with only a positive mass warp drive, we have to start doing a little bit, we have to start playing with it a little bit more and making it asymmetrical. If we just have it symmetrical right here, okay, it's not going to have any force. And here's our ball in the middle. But what Heisenberg, again, Lavinia, not Werner, finds out is if you take the same amount of energy and you distribute it asymmetrically, so it's heavier on one side, this is what can get you your accelerated forces. And again, we're talking, and this is kind of reflected in Parisiano's metric up here, where we're adjusting the shaping function over time. Okay. So we've already had what 3 of our problems are solved now, and I'm going to extend that to a 4th problem a little bit, and now I'm going to erase these. We can always redraw them again if we need to. Radiation is still going to be an issue even without event horizons, though in a slightly different manner. Noticed what I was saying about how the energy at the front of the ship, it no longer gets infinitely blue shifted, but it still does get blue shifted. Now, some of you should, I hope you're familiar with some of the literature that suggests that when you drop out of FTL velocities, you're going to release an energetic burst of radiation at whatever your target is, or towards wherever you're headed, because all that blue shifted radiation is finally getting released. This is not a physical barrier in our laws of physics to warp drive. So we can come out on a tangent from our target planet over here, exit FTL, and then complete the rest of the journey at slower than light velocities. A good analogy that I like to use for this is, when you're driving your car and you're coming home, do you just drive the car right through your front door and then get out of the car and you're now destroyed living room? Or do you slow down and park in the driveway and then walk through the front door? That's kind of a good analogy that can go with that. So we've rendered our energy problems to an engineering. We have rendered the radiation problem to an engineering, and we've all gotten away with, gotten rid of the exotic matter and the horizon energy. This still leaves the problem of causality. Okay. Now, as we mentioned earlier, any time that you're going to be going faster than light, you're also going back in time. This has been a rather robust area of study. And as I mentioned in the talk that I was on last time, there's been one particular physicist from Brock University, and Dr. Barak Shoshani, who recently has put out a series of papers on this, at least 4. And he's working. I know he's working on more as we speak. Titled "Time Travel Paradoxes and Multiple Histories," "Wormhole Time Machines and Entangled Timelines," "Time Travel Paradoxes and Entangled Timelines," and then "Warp Drives and Closed Time-like Curves." And so this is it's a series of papers where they investigate. There's essentially 2 models in our current laws of physics that are most accepted for, 3 models on how time travel paradoxes would be resolved in reverse time travel. The first and the most boring is the Hawking chronology protection conjecture, just that, some quantum wibbly wobbly happens at the whenever you try to go activate your time machine, and it prevents it from happening. This is boring. We don't like it. We're all talking about time travel anyway, so let's just kind of push Hawking off to the side. He did good work, no disrespect. The other 2 is going to be the Novikov self-consistency conjecture, where essentially time itself is just one big closed causal curve where, kind of like if you go far enough along on the equator, eventually you're going to wrap back around on yourself. Now, closed causal curves are allowed in this, but free will is an issue with that for obvious reasons. Again, it's just saying that you can go back in time, but you can't change it. Excuse me. Now, the third, and this is the one that we're going to be interested in, is the many worlds interpretation of quantum mechanics, or the Everettian interpretation. Now, I'm sure some of you are probably rolling your eyes at that. Okay, we'll talk later. And so they go through and they do a rather exhaustive numerical analysis on which paradoxes are able to be solved, if at all, with the 2 different models. And they find out that eventually you're going to run into a paradox or a series of paradoxes that can no longer be solved in Novikov's single timeline, but they can be solved in the many worlds. What they further go on to propose is the entangled closed timeline, or the ECTC model, which essentially says that time travel paradoxes can be explained with certainly an infinite number of timelines, but we don't like infinities. They make us uncomfortable. But they can also be explained with a finite amount of timelines, as long as each timeline comes back around to the original one via the correlation operator T. So instead of the traditional reverse time travel thing that you have with the many worlds, where each time you go back in time you're creating a new branch, what he's proposing is rather, instead of creating new branches every time you go back in time, you are exploring existing ones. Okay, so if we want to understand this a little bit more, we should need to turn to the work of Dr. Sean Carroll, who you guys should be very much familiar with, who himself is based on the work of Ted Jacobson and himself, Jacob Bekenstein. And so what they're playing with Everettian quantum mechanics. And what they find out is that you can find general relativity. And again, I'm going to take a slight tangent into quantum mechanics here, and then I'm going to reel it back into general relativity and warp drive. So just bear with me here. You can find general relativity as a emergent semi-classical approximation of entanglement entropy. So I'm going to draw a hyperbolic space here just to help give a visual aid for this. Now, don't get too caught up in this, because a hyperbolic space is technically representative of an anti-de Sitter space. We live in a de Sitter space. I can link you guys. I can link to a whole plethora of papers that showing that this space, this emergent space from entanglement concept, not only works in ADS, it also works in de Sitter and Minkowski space. So it's that's a different that'll be a slightly different. Debating on that would be a different conversation. So starting out with our hyperbolic geometry here, I've gotten pretty good at drawing this here. Okay, I'm just going to keep talking here so you guys don't get too bored. You guys hopefully should be familiar with a hyperbolic tessellation. If you're not, then you're probably in the wrong talk. So what are we looking at here? This is not too bad for doing it freehand that quick, hardly even looking at it here. So the whole idea of entanglement entropy is that, so I'm going to make this red here, and I'm going to draw a dotted line on the outside of here. And we're going to label this S for entropy and A for area, okay? So what is this saying? Saying that our entropy, what is entropy? It's the, like, one definition of it is the total amount of ways that a system can orient itself. It's just one way. So we can say the entropy is the amount of little nodes, these little branching nodes that are inside of this. And it's always going to be proportional to our area. So we could say that this is true for the whole circle as well. Well, what is area? Area is a measure of geometry, right? And entropy has a relationship to energy. So if your area is proportional to your entropy, well, then your geometry is going to be proportional to your energy. Well, if your geometry is proportional to your energy, that's just relativity, isn't it? You know, your curvature of space-time, g mu nu, is going to be proportional through your proportionality constant to your t mu nu, your stress energy tensor. And so this isn't quantum gravity. I'd like to stress that. This is what's known as entropic gravity. This only works in a many worlds context. It does not work with Copenhagen quantum mechanics. And if you look at it through this particular point of view, you no longer need a quantized theory of gravity because you have an emergent theory of gravity. So, you know, this is not a quantum theory talk. Again, so now that we've realized that we can relate this to our g mu nu and this to our t mu nu, let's rechange this picture a little bit to turn it into a bit more of a quantum picture that some of you guys should be a little bit more familiar with. So we're going to say that our area turns into the well potential of our quantum harmonic oscillator. We're going to make these our little energy states. How am I doing on time? Okay, perfect. And then we're going to have our eigenvalues and our harmonic oscillators. Boom, boom, boom. All right. Again, if you're not already familiar with this probably isn't the best talk for you. Sorry. So again, we have our well potential of our quantum harmonic oscillator, and then each one of these nodes can combine to make our entropy. So again, our entropy is always going to be proportional to our area. Okay, so now I said I was going to reel this back into general relativity and warp drives. So again, keep this in mind and what it's supposed to represent, and we're going to redraw again. Only this time we're going to do it in a graph that might be a little bit more representative of what we're familiar with in general relativity. So we're going to start down here. We're going to have our x. All right, we're going to have our y-axes. I'll label this up here, y. And then we'll throw in a z-axis for fun, even though I'm not really going to use it right now, just for posterity and art's sake. Okay, so we have our three spatial dimensions, our x, y, and z, right? Remember what these start to be able to relate this back to what we talked about earlier with our general relativity and its coordinate system. So now here we're going to have our t. Okay, so t representative of time. Okay, and down here now I'm going to put theta. Now I used to call this the m-axis. I have started calling it theta for reasons which I will explain in just a second. So we'll make that our theta. Okay, so remember, as I said, we were talking about how this applies to time travel, and if we're the only way, so as Shoshani showed, the only way that time travel works is in a many worlds context, at least if you're not worried about, at least if you don't want to invoke causality and, you know, free will and all that. So again, assuming our quantum many worlds interpretation here, and again, this shouldn't get into a debate on, you know, what the proper interpretation of quantum mechanics is. That'll be a different talk. So if we want to have, let's just say we're going to have point here, and let's just say a point here. Okay, let's keep this simple. Okay, if we want to find a geodesic that connects these two, through our entangled. Remember, we can call these our entangled pairs. These, you should kind of be seeing how this looks sort of like our eigenstate, our eigenstates of our quantum harmonic oscillator, which itself is just a zoomed in version of our hyperbolic tessellation. Okay, well, let's just say we're in the 1, 2, 3, 4. 2, 3, 4. Let's just say that this is in the 2, 2 position in our spatial coordinates, right? And we want to get from here to here. Well, we need to calculate the difference from this. Well, we need to know where these are in space and time. So if we just do a regular 4D axis, your 4 space and 1 time, and you only look at a 1 timeline, this should look like our regular universe as we see it. So again, we know these are both in 2, 2 on the spatial axes. We're going to say it's in the second here on the t. Now, what am I doing? Now, here's where I start to explain theta. I'm counting. I'm playing with and so this is the point of the talk where it starts to get out of established physics and into my own speculative ideas. So these are incomplete ideas. Bear with me here. I'm hoping for feedback. We're representing time as polar coordinates instead of Cartesian in this sense. So t would normally be our r, if we're thinking of polar coordinates. So the magnitude of our vector, and then theta will be our angle of this. So we'll say if this is here, we can say it's at level t on our time axis, and then it is at a certain angle from our theta over here, and then same thing over here. We can find the difference between the angle as long as we know all the other coordinates, and we should be able to calculate the spatial temporal distance between them. Okay, and so this starts to get into a navigational equation. And or at least what I'm wondering is, if this whole multiversal time travel thing is legit, how do we account for navigating in this multiple time dimensions without getting lost? If we want to come back home. And so this is kind of where I'm coming from in all this. So let's start to relate this back to our general relativity equations. And again, so we're also going to assume another axis here that we're going to call phi, but we'll just keep that in mind. So let's go and erase all of this, and we're going to write back out our general relativity coordinate equation. Again, it's a very simplified implicit form, taking these extra spatial dimensions, or these extra time dimensions into account. So again, we're going to start out with our ds squared. dt squared, that's staying the same. And again, so this is going to be our g00. Okay, so because these are time dimensions, we're going to do plus d theta plus d phi, and then minus for the spatial dimensions dx minus dy minus dz, and we will square them all. Okay, so this becomes our G11, G22, and then our spatial coordinates get knocked over into our G33, G44, and G55. Now, if you guys are familiar with general relativity, you should already start to realize that if we're extending the metric down in this, just by adding two, I'm not gonna write up. Actually, I do have it written out here. Here's what it would look like extended written out for the whole metric. And so what we find out here is that just by adding 2 more dimensions, and for our general relativity equations, we more than double the amount of PDEs that we have to do from 10 all the way up to 21. So, general relativity is already hard enough to solve with the 10 differential equations. We're doubling that now, basically. Come on. I can understand where apprehensions might come from this. I don't even know if this is the correct way of doing it. So we're going to go back and think about our 5 problems that we have, that we originally had. We had our energy, we had our exotic matter, we had our horizon, we had our the radiation that came with it, and we have our causality problems. Well, the causality's been fixed if we're assuming a many worlds interpretation. The radiation problem was solved with the horizon problem with Gianluca Persiano's work. Exotic mass has been solved in a plethora of papers by different people, and the energy requirements, I believe the lowest that I've seen them have been from Dr. Sonny White with about 700 kilograms worth of mass energy. Now, if we're going to take into like Dr. Sarfati's ideas on how put off something like polarized vacuum with changing the permittivity and permeability, we might be able to get that even lower. Again, these are all things that need to be solved. So I'm proposing now 3 new problems that we need to address as we start to pass the baton from those of physicists to those of engineers. So one, we need to combine these metrics, the Parisianos and Heisenbergs, everyone that's contributed to lowering the energy requirements and fixing one of these 5 problems. We need to start asking, how do these different solutions fit together? And I don't want to hear people saying, oh, well, he did work down on that, he did work on this. Half of you guys are talking about the same thing, like Sarfati and Puthoff, for example. Sarfati says that his ideas are different from Puthoff. Well, they're all they're doing. So if we have our G mu nu equals 8 pi G divided by our C to the 4th T mu nu, C to the 4th. Well, what is C? C is equal to 1 divided by, that's mu, not the square root. I'm getting ahead of myself. 1 divided by the square root of epsilon naught mu naught. And so he's just replacing C with this. So parentheses 1 divided by square root of epsilon mu. That's basically all they're doing. So the difference is Sarfati is saying to do this with metamaterials, and other people are saying to do this bipolar. So you polarize the vacuum or you polarize metamaterials. You're polarizing the space-time with something. So again, we have different ways that we can start to look at this that doesn't have the same pathologies against it, that are, while fairly leveled against the Alcubierre metric, I believe are unfairly leveled against warp drives as a whole. So that's one of the problems. The second, again, is going to be our navigational issue problems. I have proposed some potential solutions to multiversal navigation. I don't know if these are correct. Again, I'm looking forward to your input on that. And then the fourth one is going to be handing these off to the realm of engineers. You guys might be a little bit more familiar in that world than myself. Now, personally, I think Sal Pais has some very good ideas contributing to this. Now I see we're getting a little bit low on time here, and I want to leave some time for questions. So this might be a goodish spot to leave it. So yeah, we know what warp drives are. We have 30 years of literature on it. Most of the problems have been solved. They just haven't been integrated together yet. And so we need to start putting our brains together a bit more on this, whether or not we're using polarized vacuum or whether or not we're using general relativity. I don't think it should matter. As the previous gentleman was saying, you should have multiple ways of mathematically describing one phenomena. And if you can have if our models are both valid in general relativity and they're valid in the polarized vacuum and they're valid in our entropic gravity relation that we went over. Well, if they work on all 3, it's probably pretty good indication that we're on the right path. And yeah, I guess this will probably be a good spot for me to leave off before I go into a rant on something else and don't leave enough time. So yeah, let's have Tim bring some people in. We'll do some questions. People can have comments, and we'll go from there.
Well, Daniel, thank you. You are brilliant. You are absolutely, and I knew that. I have a sixth sense for people, but that's absolutely brilliant. Let me bring everybody in. Before anything, let's give Mr. Daniel Davis an enormous applause. I put this in chat. You are a whiteboard ninja. You do more with a whiteboard than most people can do with a PowerPoint in 6 months to prepare. So that's absolutely brilliant.
That's what I was trying to say to you.
Let me go to Jeremiah Pop first.
I wanted to mention, when you were giving us that lecture, which you absolutely dominated the mathematics of warp drive physics on Brendo Sapien server the other day, I did not know who you were after seeing the graphs. It's immediately obvious who you are, kiddo bites, and holy cow! Like, talk about bringing this thing in directly into the time differential fields and a multidimensional time factor. I think you've really got it. You may have actually one of the first approaches to geometrically explaining these physical fields. And a lot of the mathematics, they deal with purely a spot point vector. They aren't dealing with the three-dimensionality of multi-axis time. And yours does solve that almost completely, if not completely. So, man, beautiful fucking presentation. So good. So excited to see you here. That was awesome. Today's APEC is historical, like Tim said. It really is.
Yeah,
That's
this
all I
is
had to say.
historic.
Thanks.
Absolutely historic. And if I could jump in, Dan, I love the meta-analysis also. This is one of the things that Dr. David Chester has done as well, is everybody has different models and theories, and they have siloed those. And one of the things that you said in the presentation, and I absolutely agree with this, is they are circling the same core concepts, and they're just expressing them in different ways. And so all of us and all of these models are greater than the sum of their parts, right? And if we're able to work together, we can find some cores, and that lifts everyone up. And I truly mean that. So let me see who is the next question. Andrew.
Yeah, really very simple one. I was looking at when you're talking about causal information. Were you trying to model causal information for you T nu V in the general relativity equations? Where would your causal information come from, especially as you're thinking about something like a warp drive or something like that? That's a very naive question, but I just had to ask.
Can you rephrase that for me? By like, where am I getting the causal information?
I worked in my early papers on causal discontinuity that might exist in the beginning of the nucleation of a new universe. And there would be the introduction of causal structure. And so I'm just asking you, in your equations that you're working with, where would you put to say questions of causal structure or its introduction in terms of the nucleation of space-time, to say at the start of a Big Bang or something like that? Where would you do it in your model?
So I think if I'm understanding what you're asking, to kind of answer that, we have to look back at Carroll and Shoshani's work, saying about how these timelines eventually wrap around back on themselves, sort of like how you keep going.
That's exactly what I'm getting at.
Yep. And so it's a multiverse that has recursion, I guess.
So like you're doing it in terms of a multiverse model.
Yeah, so we're assuming an appropriate version of the Schrodinger equation, and then we find Einstein within it as a semi-classical approximation.
I see what you're saying. So where would the multiverse in terms of your presentation be at the feeding into a recycling process or something like that, That's one thing. One of the things I tried to work with was a multiverse model of generalization of the Penrose cyclic conformal cosmology model. And I tried to have inputs into that sort of thing, And so what I did is that where I got essentially in a little bit of a sticky wicket was the issue of the timelines and other things because you have timelines for different multiple universes or something like that, and you'd have a feed in to say to a loci to start to say a new expansion. In other words, is that the question I was asking, and I asked this in all seriousness, is when you have the timelines and other things of the sort, are you able to generalize? The question I was asking, are you able to generalize so that the multiverses had pretty much the same constants of nature, like H bar, like G, like gravitational constant G or something like that, or could they all be different?
So if we're going to assume this, this multiversal Big Bang model, recursive multiversal Big Bang model, there will be certain branches of the wave function where they split off early enough where they will have different laws of physics, but they will be so disentangled from us that we should never really be able to.
Saying is that they would be disentangled, so you couldn't have some sort of causal inference or something like that. Disentangling, so to speak, because of what you might call different laws of physics, means in effect we would have to have something that would be relatively congruent to our own laws of physics. In other words, to have an input into a recycled universe.
Mm-hmm. Yeah. So in this model, and this is going to be a bad analogy, you can think of entanglement and entropy is sort of being traded, like in the Heisenberg uncertainty principle, between your momentum and
That's
your position.
exactly what I tried to do, and I tried to
Okay.
also look at the G nu B. The
Well,
G nu B. What?
and Andrew, I'm sorry to interrupt, sir, but we were running short on time. So let me.
Well,
if
I
it's okay-
apologize.
Oh no, that's okay. Let me go to the
It's
next question.
fascinating.
Though. It is fascinating. And Dan, thank you. I would love to have you back. Actually, all of our presenters today. I want to have everybody back. But let me go to Mr. Michael Boyd next.
No problem.
Michael, go for it, sir.
So I'm curious if you've considered an alternative where there's instead of a Big Bang, for example, or the bang and collapse, where it said our universe is a multiverse where it's like buds in a flower or in a plant, where there's like a budding process where universes are being constantly formed, and this is what I call a forever universe, where basically matter and energy is being created and destroyed, like in a black hole, where it's not really being destroyed, it's just being recycled through the black hole. Would that work with the general?
Yeah, some version of that. So I would really recommend you go. So if I was gonna say, we'll pick one paper for you guys to go check out, they'll probably answer that question. It'll be Sean Carroll's recent. He just came out with it in, I think, October. Completely discretized finite quantum mechanics is the name of the paper.
Could you say it again?
Completely discretized finite quantum mechanics.
Discretized. All that.
And you'll find he talks about basically in analyzing versus comparing infinite timelines versus finite timelines. The only way that they're allowed to be finite is if they wrap back around on themselves, kind of.
So it's kind of like a retrocausal time.
I don't know if retrocausal would be the best way to put it. I almost wonder if like Pius's super bang is almost like a better analogy for it, where you get it once you get out to your max entropy, you start to have a quantum bounce, and then once you get back to the core bounce limit, which the analogy he uses would be like at the where the strong forces start to interact in a supernova. This is going to be where everything starts to interact back at the Planck force near the Planck time, and then you have like a reciprocal kind of bouncing back and forth between a highly entangled state and a highly entropic state.
So the other question I had is, have you considered the effect of what I call strong theory of gravity, where gravity is stronger close up than it is far away?
Where gravity is stronger close, isn't that just gravity?
String theory is kind of like that, but without all
so this isn't string theory, but it's kind of string adjacent. So string theory deals with very small extra dimensions. I'm considering if the extra dimensions are there, they're very large. So it's at the opposite end.
So and I'm agreeing. I'm just saying you have a far field and you have a near field. So what I'm suggesting is that what we experience as gravity would behave differently in the near field than in the far field. And that would have
Do you have any
solved a
papers I
lot
could
of
look
the
up?
problems with the amount of energy you need to go to work.
That would almost be like Mond theory, right?
Right.
Okay. Well, if you have some papers that you can link me, I'd be more than happy to look at them.
Yeah, and in the meantime, if it's okay, let me go to Jared. Again, I'm trying to keep us on track.
Thank you.
Michael, thank you, sir. Thank you.
Dan, yeah, I had a question for you. So we're invoking many worlds so that when we go FTL, we're able to, get all the things to mesh well with each other, all the causality problems, right? Well, when you're going FTL, you're going to have energy dispersion leakage into the environment. And in this case, it's tachyons, right? Your EM radiation is FTL, so you're getting tachyons. So that's your energy out.
You're getting
right?
the Cherenkov radiation from the vacuum as you go through
Yep,
it. Yeah.
yep. But we're also invoking many worlds, and you're saying that you're traveling through these multiple timelines, these multiple worlds, these multiple universes as you're going FTL.
Yep,
right?
so
You're crossing
that's going to
over.
be a navigational issue. So we're going to have.
What,
so that's something that we're going to have.
I'm almost there. I had one more sentence on that. So you have energy leakage across infinite possible multi-universes, right? But it's a different size of infinity than the larger infinity of all possible universes, of swampland, right? It's only the possible universes for the timelines that you're crossing over, which is a smaller infinity. So I just wanted to try to put that out there.
So the model I've been playing with is not an infinite number of timelines.
It's a finite number of timelines.
Yeah, so that's kind of what I was saying about. So the dimensionality of your Hilbert space is always going to be proportional to your entropy, right? Or at least for proportional to your entanglement entropy. So again, if you go and look at that Sean Carroll paper that I mentioned, the dimensionality of our observable universe is going to be proportional to its entropy. So your entropy becomes the exponent. So for our universe, it would be roughly 10 to the 10 to the 122 possible different universes, which is an extremely large number, but it is still less than infinite. In terms of having to deal with the radiation bleed as you're going between these timelines, that is a very valid concern, but it is a navigational engineering concern. We got to make sure that as we're going these velocities, we have to make sure our geodesic doesn't intersect too close to any life-bearing objects, that we don't want to X-ray, which, again, these are still problems that we have to figure out, but they're engineering problems. They're not physics problems.
Okay. And again, sorry, go for it.
Just my last part on that. I'm just wondering if it might be possible to whittle that 10 to the 10 to the 120 down even farther, because you're not taking the lifespan of the universe, you're taking the lifespan of the time, the sliver of the universe's life where you're traveling, right?
I don't know if you'd be able to get it smaller. That seems to be about the smallest number people have been playing with, is on the order of 120 orders of magnitude. Now that starts to play into a little bit with Dirac large number hypotheses, and that could be a little bit different conversation, but we're getting pretty close on time here too. So
yeah, thank you.
Awesome. And Jeremiah, did you have another? I think you had one more, right?
No, honestly, this conversation is so good. I'm just taking it all in and absolutely loving every second of it. Thank you, Jim.
Okay. Oh, and there's Curtis. Let me add Curtis in. Oh, and Curtis has his hat on. Mine hurts. It's hurting my head.
It's a little bit warm.
Okay. Curtis, what was your question, sir?
So earlier I noticed you talked about the 10 equations, and then you added something, and now you got 21. I'm just kind of curious what you think of the fact that Einstein ended up with 10 equations instead of what was kind of some people expected, which is 16, to have a fully covariant theory, which is what Sachs's theory is based on. I'm just kind of curious why you think he required reflection and space symmetry, and if that's something that you think we still need.
Well, the timelines might not work out for this argument, but this is just a bit speculative. We all know that Einstein didn't, much like Schrodinger, didn't believe what the Schrodinger equation had to say, right? That was part of what the Solvay conference was part of. And so I wonder if his reluctance to expand it anymore had something to do with his also reluctance to that came around to some of the implications that kind of come around the Schrodinger equation.
Okay, yeah, because what I found in initially discovered this in Mendel Sachs's work is that if you do the 16, allow for full symmetry and full covariance, you end up with 16 equations, and you end up with a basic quaternion, a number system, which corresponds to quantum, or what we now know as quantum, but that actually makes it compatible with that theory in a way that that theory could be a linear approximation to a field of a traditional field theory. So
And
it's
I
a
might
little
get
bit
some flack for saying this, but it's not that quantum mechanics and general relativity don't mesh. That's a little bit of a overgeneralization. It's that Copenhagen interpretation and general relativity don't mesh.
right.
So
Right.
again, if we're assuming an Everettian interpretation, the wave function just keeps evolving smoothly through
Right.
time. There's
Right.
no observation that we have to worry about renormalizing for.
Right. Well, the thing is, what I'm talking about in matching is the group, the fundamental group that is used in the theory, right? So if those end up matching, you have some, it looks like you have something much more compatible, and that's what that theory actually does. So, yeah, that's very interesting. I'd love to chat more with you, and I mean, Tim. This has been a great one. A lot of good stuff.
Yeah. No, I'm so excited. I am so excited. Well, guys, we're at the top of the hour. Everybody, please put your hands together again. Mr. Daniel Davis, absolutely amazing. So I am extra. What I'm going to do is take everybody out of the studio except for Dr. Andrew Beckwith. So Dr. Beckwith has been working on this for a very long time. Folks who have been in this area are probably, you guys should be familiar with his work or at least heard his name. Dr. Beckwith, thank you, sir. Thank you for
Thank
joining us.
you.
So you
Thank
are
you.
in
A lot of what I'm doing is based upon gravitation and modern cosmology, the cosmological constant problem, edited by Antonio Zielinski and Vera de Sabata and Norma Sanchez in the Ettore Majorana International Series Science Series. So I picked a torsion right straight out of that book.
Wonderful. Now, I have two files for you. One of them is called New Scaling Torsion, and then the other one is, let me see, I'm gonna have to open them on my computer here. Decidability of the Riemann hypothesis. Would you like me to put either one of those up?
Put the first one up.
Okay, New Scaling Torsion. Okay, so and just tell me, I guess, to scroll if you need me to scroll, and I will take myself out of the
Sure,
screen.
that's fine. All right. Let me just read what is. How torsion is presented by De Sabata, Sarah Baum, and Erika 1990 arguments modified marine permit cosmological constant and a baseline the dark energy, and it's redone for assessment for JHAPGC. And my name's Andrew Beckwith. I'm in the United States with foot surgery. A lot of times I'm in Chongqing University working with Dr. Bang Yu Li and with Wen Hao and with other people. So I'm in the United States for another month because I had foot surgery. But anyway, let me see. Based upon the idea of cyclic conformal cosmology, we discuss how torsion may allow for a cosmological constant which links to ideas given by Beckwith and Kazi 2023 in a presentation as far as torsion, as given by De Sabata, Shirabaman, Erika 1990. The 1990 article claims that torsion cancels cosmological vacuum energy, whereas our formulation leads to a leftover cosmological constant 10 to the minus 121 times vacuum energy. Meanwhile, speculation is how this relates to black hole physics and speculation given by Corda, which replaces traditional firewalls with a different formulations are included. And as that presentation by Corda uses the idea of a quantum number n, which ties into our cosmological constant presentation. Now, let me say one thing before we get going, which is that the usually when people look at torsion and everything sort and the cosmological constant, what was done, and I had a discussion with an Indian theoretician who graded my paper, is that they are thinking in terms of a particle with a particular spin. So what happened is that we would treat that the early universe black holes were equivalent to something like a spin 2 particle very close to it. I'm talking about primordial black holes. But if you have two black holes that are interacting with one another, that is equivalent to first approximation to something like a torsion effect, because, between the two constants, and you have a contribution of many black holes that would contribute toward the cosmological constant problem. Now, that is my statement of what we are going to be starting off with. Next slide, please. Thank you. Introduction. Review purported rule given by De Zapata and Serbanam, 1990. It's cancellation of vacuum energy, cosmological constant. Present preview what we are doing. First of all, I wish to thank the referee for his comments, which are reproduced below. And there are other papers to point out where torsion, quoted often by Birkenstein, can indeed give rise to a residual cosmological constant term of the observed magnitude. This has also been used to generate inflation. The present review has always been an advocate of a lambda term, so I agree with the author that torsion terms can give to a rise to a lambda term. Of course, the source of the spin density of the present paper is that of primordial black holes, but essentially a similar argument. Equation 4 to 14 are just the same as in the first reference in the quote. To what I ask you to adhere to at the fundamentals of the base document and then proceed to address the issues brought up by the referee. And the referee present, he uses different arguments as to what generates spin density than I do. But I use spin density as a direct product of primordial black holes forming initially. Now, the other difference is my primordial black holes are scaled via Bose-Einstein condensates and are also linked to gravitons. Having said that, the more the referee's reviews included in the paper, which we refer to three references which the referee thought were of important consideration as at the end of my summary of the arguments presented. The basic arguments is the black holes as the source of torsion given for the review. To begin with, look at references 1, 2, and 3, which report to show a global cancellation of vacuum energy term, which is akin to canceling the following completely. Next slide, Tim. Next slide, Tim. Thank you. All right. Now, what we're doing is we're looking at the density, cosmological density, and everything sort. And here's the typical calculation that's done, and it's very, very large. And so then what we have instead, we have the top of the integral. We have the delta E over C. Delta E over C. And in other words, in the traditional one where you have the so-called, the biggest problem in theoretical physics, that's 3 times 10 to the 19 GeV to the 4th, or 2 pi h bar to the 3rd power. Now, then what you have is that then what you have to do is to come up with an argument where this is cut down to 2.5 times 10 to the minus 11 GeV to the 4th, 2 pi h. And in the first reference, the first line is the vacuum energy was completely canceled in the formulation of torsion. We're not going to be doing that. We're going to say it's coming close to canceling. It's going to be close to canceling the so-called traditional term of vacuum energy, which is equation 1. But which is it because we have black holes, we're going to change the limit of the integral. We have delta E over C, and this is going to become to the, the value of can you please expand the size of that a little bit, please, Tim? Can you make this a little bit larger? I'm having trouble reading it. Okay. We have 10 to the minus 19. It gets cut down dramatically. Delta E over C becomes much smaller. All right, the term in quantum comes from an accorded derived expression of energy level of relic black holes. So in other words, what we have is we had 10 to the 19th GeV minus n quantum over 2c. And this itself is going to be the interaction of the black holes, which you get in terms of the top level integral lines, is going to be cut dramatically. The term N comes in according to the expression energy levels of relic black holes. And simply what Corda did is he came up with a quantum presentation of black holes where they have a quantum number of N, which itself, when done, is going to essentially eliminate the need for firewalls. In another one of my publications, what I said is that if you had firewalls, it might be present at the very beginning of the universe, right at the initial nucleation point. But which is when you get the black holes and everything, so you don't necessarily have to have a black hole with firewalls. So then what I just simply said is that you have cancellation of the following term. The claimant one is that there is no cosmological constant. All right, which is that what is done in the APEC reference is that they said is that torsion would completely cancel that term, which is equation 3. But what we said that we are doing is to look at equation 1 and to have what you might call a change in the overall energy integration, which is occurring. So that you would not have a cancellation, but the delta E over C would become much smaller because of the negative energy of primordial black holes. Now, then when I said in equation 1, this equation 1 is gravitation, modern cosmology, the cosmological constant problem. It's in this particular reference, APEC. And what I said is a little bit different. So I said you would look at the intersection of black holes, and the black holes would be providing a spin density. Now I'm going to say more about that a little bit later. All right.
Oh, and Andrew, if I could jump in really quick, there should be an
Go ahead.
expand. There should be an expand button in the lower. If you move your mouse over the screen,
Yeah, I see that right now.
Yeah, try clicking on that, and
I
let me
just
apologize.
did. I just did. That fixed it.
Wonderful,
Great.
thank you, sir.
That fixed it completely. All right. Now going back to equation 1. Equation 1 is this big integral value at 3 times 10 to the 19 GeV. Now what I'm claiming is you go to equation 2 is you put in the negative energy from primordial black holes, that what you're going to get, and it's in quantum over 2c, is that you would get a value of 10 to the minus 12 GeV. That the value of 10 to the minus 12 GeV is going to be so that this value, which you're going to come up with, and you look at equation 1, is going to change from 3 times 10 to the 19 GeV down to 2.5 times 10 to the minus 11 GeV. And the key point of where you'd have the black holes affecting this would be delta E over C, and it's 10 to the minus 12 GeV. Now, equation 3 is done in as far as treating of dark, vacuum energy in all sorts of books, and it's considered to be the biggest problem in theoretical physics. Now, let me go to the next slide, please. Okay, next slide, Tim, please. Thank you very much. Now, this is where I assumed Penrose recycling of the universe. Into the prior universe, mass of black hole. We have supermassive black holes of 1.989 times 10 to the 41 to 10 to the 44 grams. All right. And you would have 10 to the 6 or 10 to the 9th of them, usually from the centers of galaxies. This is Penrose cyclic cosmology. And Penrose cyclic cosmology would be that you would have a recycling universe. And so then, which is that the Planck era black hole formulation assumed to start emerging of micro black hole pairs. And you get there, and this is where you treat the sort of thing as acting like a torsion effect. And so you had 10 to the minus 5 to 10 to the minus 4 grams, the order of magnitude of the Planck mass value. And so you might have up to 10 to the 40, 10 to the 45, assume that there was not too much destruction of matter energy from the pre-Planck condition to the Planck condition. The post-Planck era black holes with the possibility of using equation 1 to have 10 to the 10th gravitons second released per black hole. Well, this is what you do, but the point of it is that if you look at the second line right over in here, the second line or number Planck era black hole formulation, this is where you would have at least the starting of dark energy and other things, and it's related to black hole physics. And the calculation that was done in APEC was assuming when you would do this in terms of torsion is that you'd have what is known as a spin density for a particle. My spin density for particles was related toward micro black holes. And the Indian theoretician who I interacted with endorsed this. Now, let's go to the math. Now let's go to the third part. The author is very much aware of the quack science and purported torsion physics presentation, which the state the torsion problem is not to link to anything other than to disruption of the initial configuration and expansion universe, more in the spirit of references 6, 7, and nothing else. We wish to delve into what was given into one, which is Ericate, with a subsequent follow-up and modifications. Now what I did in this part of the paper, it's accepted by JHAPGC, is to essentially go through the Ericate presentation in 1990. To do this, note that in the Ericate presentation of 1990, that the vacuum energy density is stated to be rho vacuum, the effective cosmological constant C4 over 8 pi g, whereas the application in terms of an anti-symmetric field strength, and it's getting right over there. That's in reference A. Next slide, please. Thank you. Thank you very much. And due to the Einstein-Cartan action in terms of SL2C gauge here, we write from 1, L, okay, minus R over 16 pi g. And here's this, spin tensor, which you would get. And ours, with regard to the Ricci scalar and tensor notation, it's related, and that S with those little indices is related to a conserved current closed in on the SL2C algebra as given by J. And here we have a description of a particular current. This is where we would define, and then this is the structure constant of the group SL2C. And here we have an explanation of where the particular terms come from. All right. Now, which is that this is assuming a metric of ds squared d tau squared plus a squared tau. And here's we have a particular angle structure. It's a metric of S3, and which is the Einstein field equations reduced to in this portion application no mass or particles as. And so this is what we had when you do this, and this is the so-called this is the presentation at Ericate. All right. And so then what they said, here's what the scale factor with respect to conformal time, and R min over A squared is something R to 4 A4. That's a so-called spin scalar identified as the basic h bar unit of spin. So the question is that there's a particular interpretation in Ericate where you'd have a spin factor. And the spin factor, what I was doing was related to primordial black holes. In the spin factor, which was done in Ericate, they were coming up with nothing that was so definite. Now, let's go to equation 13. How to modify equation 13 in the presence of matter by Yang-Mills fields. Okay, we have, first of all, we can change of equation 5, and that is right up over there. And so we have this big complicated expression, which is 15. Next slide. Next slide, Tim. Thank you. Okay. And basically, we have a redo of equation 13 to read where G is AC. We have, so the minimum radius is a Planck radius. So in other words, we have a scale factor evolution, which is related to which is very closely related to Planck radii. Planck length and other things. This is very important. And especially in the case of an unpolarized spinning fluid in the immediate aftermath of the Big Bang, we would see a Robinson-Walker universe is that sigma is a torsion spin term added to reference 1 as, and here we have equation 18. Now, what does reference 1 in equation 18 do? We'd have and why? Well, here what I did was, here we go with equation 18 right over here. and 8 pi g rho over kc. The claim is made in reference 1 that this is due to spin particles to remain invariant. So the cosmological vacuum energy, cosmological constant, is always canceled. All right. Now this is where we differ from it. Our approach instead will yield. Okay, and this is what I put in, which is an alternative to, and this is what the biggest part of back and forth between me and the Indian theoretician. He took 9 weeks to evaluate this with me. Here we go. We have the same equation, r dot over squared over r squared over r squared, 8 pi g rho, plus an observed c squared over 3 minus, and we have that that k c squared over r squared. The observed cosmological constant is 10 to the minus 122 times smaller than the initial vacuum energy. Well, where would we get that factor of 10 to the minus 122? Well, that goes back to what I discussed in the very beginning. The main reason for the difference in equation 19 and equation 20 is the following observations. We'll go to table 1 and make the following assertion. Mainly, the reason for the existence of sigma is due to the dynamics of spinning black holes and the precursor of the Big Bang to the Planck regime of spacetime, whereas in the aftermath of the Big Bang, we would have a vanishing of the torsion spin turns, i.e. table 1 dynamics, and the aftermath would largely eliminate the so-called that sigma term. Filling in the details of equation 19 collapse of the cosmological term versus the situation of equation 20 by numerical values. Next slide, please, Tim. Next slide. Thank you. All right, first look at the numbers as to reference 3 at the inputs. These are very revealing. We would have this little thing, which is 10 to 87. This is the number of vacuum energy, and this value is 10 to 122 times larger than the observed cosmological constant. Torsion physics is given in reference 3 solely to remove this giant number. In order to remove it, the reference 3 proceeds to make the following identification. So, which is, here we go, 8 pi g, and we'd have that particular term right over here. We're arguing instead, and this is linked towards a modification, is we'd have this done, all right, which is instead of a 0, it's equation 2. We had 10 to the minus 122. We'd have that little PL c squared over 3. Our time is equated to unleash a Planck time interval t of about 10 to the minus 43 seconds. As to equation 22 versus equation 23, the creation torsion term is presumed particle density of n particle, and here we have this 98 over a centimeter. We have a spin density term. All right, so these are similar. These are similar to what was done in Aricay. But what I'm doing is, rather than have their generic spin density term, is I'm assuming something straight from primordial black holes. Future work should be commenced as far as derivational tasks. We will be assumed for the moment that equations 22 and equation 23 share in common equation 24 and equation 25. It appears to be trivial, mere round-off, but I'm sure the difference anything but trivial. And this is where equation table 1 really plays a role in terms of why there is a torsion term to begin with. Make the following determination. The term of spin density in equation 2 by equation 25 is an ad hoc creation as to 3. No description is really offered first. We'll state that in the future, attached will be to derive in a coherent following. The term of, here we go right over here, arising results of the dynamics of equation 1. Now, which is what I'm saying is the Indian cosmologists tonight identified this particular term is the make or break one, which would have to be observed and commented upon from experimental data sets, or at least some sort of a process of modeling. Right. Next slide. Thank you. All right. Second, we say that the term is due to initial micro black holes to the creation of a cosmological term. This would follow from equation 2 being utilized. What we're seeing is utilization of the following. In the case of pre-Planckian spacetime, the idea is to do the following. If we have an Inflaton field, this is something that is this is a five-dimensional. This is a five-dimensional treatment of the uncertainty principle embedded in higher dimensions. And what I did was to make sense of a quantum term, give my reference in black holes for it is E, uh, you know, n to the minus quantum over 2. Third, this is what was done in terms of my integral in the very beginning when I said the modification of the modification from the giant cosmological vacuum energy to something much smaller. And you get it with respect to this equation 27. The conclusion of reference 3 states that equation 22 would remain invariant for the life of the evolution of the universe. We make no such assumptions. We assume this will be followed up in equation 23 is due to relic black holes with the suppression of the initially gigantic cosmological vacuum energy. In other words, what was done in their presentation without any particular statement as to where they got it is that there would only be a flat out cancellation of the cosmological constant term contributing, and it was seen with respect to the so-called hypothesized spin density factor in early space-time, which would somehow remain invariant. Well, this got true in Eric, but the situation was, whether as brilliant as this idea was they didn't have any observational clue as to where to look for it. So that's where I put in my primordial black holes. Now, the conclusion of 3 states that equation 22 remain invariant for life to the evolution, and we make no assumption. The details to follow after the initial period of inflation remain attached to be completed in full generality. We assume given the following input. A, the scale factor, AT, A initial, T of gamma. And here we have an inflaton, and then that second term. Then we'd have the derivative of the inflaton term. And this is something which I pass in terms of a generalized conservation law. H bar squared over the time derivative of the inflaton be roughly the order of 10 to the minus fifth. Now, the very strange thing was that this would remain invariant from the nucleation of the universe to perhaps up to the electroweak processes in cosmology. Okay, a possible future endeavor can also make sense of reference 10 as well. Next slide, please, Tim. Next slide. Thank you. All right. So, which is what I said. This is something which I've used over and over again, which is used of Bose-Einstein coefficients. Here we have the square root of cosmological constant, KB, E, HCS entropy, S entropy, KBN, and it's reference to BEC condensate, M, which is going to be a small component, something like a graviton over M proton over the number of gravitons, M black hole. And this is something that's done in Chavalis and other things of the sort, and it's quite good work. And the radius of a black hole, this is generally scaling. So in other words, one of the things which I would want to do is to make a relationship between the spin density of the black holes and this references, these set of equations in equation 30. Begin with, what is you would do this, you can ask a question, which is the equation, is you put this in, and it took me a little bit of some arguing and other things to do it. You would modify the so-called r dot squared of r squared. Okay, we'd have this particular row, 8 pi g over 3, rho minus this particular spin term, and then we would have plus k n squared over e 3h bar, and here would have, that's the Bose-Einstein, that's a kb, But then we'd had the so-called relative flatness or relative curvature units, where the K bar of C over R squared. Our analysis from here will be to drive, will be to go to different candidates at the energy E put into equation 31, and to what could be expected in torsion terms, implications in cosmology. Keep in mind that equation 3 is configured in this situation is as in 1, it canceled a cosmological term. We are not assuming that. So one of the questions is we go to the sort of thing, we come up with a particular term. If they ask the question, which is we have this evolution equation, which we pack more into it, equation 31, is what is, can we have, what is the energy E in equation 31 as thermal? And an E is proportional to T to the beta or something like that. And beta can be roughly close to magnitude, order of magnitude 1. And so then we would be looking at equation 2, and we'd observe C squared. And so we had this temperature, and then we had the number of particles, kBn squared over n particles. And this is n particles, let's say, from the relic black holes. In other words, the relic black holes have constituent components. Next slide, please. Next slide, please. All right. So the n particles would be n observed is an order 10 to the minus 35. This comes up with n, the observed C squared. You come in particles would come with this becomes smaller and smaller. High temperatures we have initially. Of course, it's not viable in terms of equation 31. The problem becomes ridiculous. There's no torsion term. We would be then looking at n going way past 10 to 120, with beyond the observed or expanded entropy in the universe. The only way to have a large number of initial particles for initial black holes is that we assume is for the initial plankton regime to have low temperature values. So in other words, what I'm saying is that we go to this and we would say something very interesting. And this piece of work is to determine that in the lead up to when we were forming the vacuum energy, before we formed that earthing chart, we would have initially, through the cyclic conformal universe, a situation where we would have low temperature. Well, that's absolutely stunning. And then it heats up enormously, and that might be packing up. I treated, the input from cyclic conformal cosmology initially, but when it got to the point of starting expansion, it was low temperature, and then it heated up enormously, but not initially. All right. Now then, the question we'll be looking at the changing the energy E to be in the quarter value of energy for a black hole. Then we're looking at the following. So we have the observed C squared. And so we have what you might call the quantum number. And this is the quantum number associated with relic black holes. But the term N comes from a quantized expression energy level of black holes and with the Plankton space-time normalization. So the frequency here would be Planck friction with the order of 6.6 times 10 to times 10 to the minus 34 joule hertz minus 1, or 3 times 10 to the 42 hertz. We're presuming doing so. This is a gravitational wave frequency for initial relic gravitational waves from this situation. Now, where is all this leading to? Modeling challenges, which this presents in future investigation. First of all, what are the particle interns and the quantum small interns used in equation 36? This needs to be explicitly worked out. Well, then, which is it in the equation 34, the creation of the torsion term is due to a presumed particle density of n, and that's right, that's equation 35. And we have a spin density term. And these terms are very close to the same. These are very close to the same that what was done in 1990 by Erike. And they're similar. Next slide. Okay, next slide. Okay. Now, let's go to what the referee was talking about. The referee delineates in 12, 13, 14 with this quote. There are other papers which point out the torsion term can indeed give to a residual cosmological term of the observed magnitude. It's also been used to generalize inflation. And then he gave a particular reference Here it's derived that the G times sigma squared divided by C support gets a lambda term observed in both the reference. The spin density is shown to be universal for all celestial bodies. End of quote. We of course delineate spin density by primordial black holes, which is different again. And it may be useful to reserve more phenomenological data set opportunities to try to verify the existence of primordial black holes as a contributing factor to spin density. It is recommended that follow-up use document adheres to the necessity of finding equipment and data analysis protocols and to verify this final step and to make it adhere to the phenomenology as well as the further intersection with instrumentation requirements, which to delve into how to acquire requisite data sets which confirm this suggestion. In addition, this will by necessity go into the matter of experimental verification by data sets of a supposition of gravitons being given by BEC condensate. Here are the references. Beckwith's new conservation law. That's what I did, and I did that. And this is a volume by Professor Carlos Pachuca and in Text Open 2023, and it was published December 22nd, 2022. That's where I came up with the conservation law. The basic workhorse I picked is Bibliography de Zapata and Siravam, Quantum Effects and the Problem of Cosmological Constant and Gravitation and Modern Cosmology, the Cosmological Constant Problem. And this is volume 56, Ettore Majorana International Physics Series, and Plenum Press, New York City, New York, USA, 1991. Now, next slide. All right. Next slide, please. And this is the integral which I use with equations 1, 2, and 3. Chang Taipei, Relativity, Gravitation, Cosmology, and Basic Introduction, all Oxford University Press. Now, the model which I had in terms of black holes with the negative energy attached to primordial black holes, Christian Corda black hole spectra from vast quantum gravitational collapse, and it's accepted for publication in Proprietary der Physik Progress of Physics. And then I had some other ones right over here. And one of the things I referred to about the 5-dimensional came from Wesson, 5-dimensional physics, classical and quantum consequences of collision decline, cosmology, World Press Scientific, Singapore, Republic of Singapore. And then, of course, my favorite in terms of scalar fields, this is equivalent to my scalar field came from Padamadan, Thanu Padamadan, an introduction to astrophysics, World Press Scientific Scientific Theories in Astronomy and Astrophysics, Volume 8, Singapore, Republic of Singapore, 2006. And then some of this, my statement about Bose-Einstein came, Chapavis, self-gravitating Bose-Einstein condensate, pages 151 to 194, quantum aspects of black holes. And I just did some more right over here. Now, which is that what I want to thank all of you for being gracious to listen to this. Just so you know, which is that the Indian referee and I were essentially arguing about this for over 9 weeks, and I thought it had been rejected. It wasn't. And then I tried to present this in COSPAR, and I got rudely kicked out by this very classically oriented physicist from Portugal, Ortu, Ooreftu, I think that's what his name was. And so this is very, very controversial. This is a very controversial topic. And what I'm hoping in the situation is to come up with what you might call specific protocols as data sets to confirm the existence of the BEC black holes, the relevance toward, which you might call primordial black hole sets, to perhaps come and get more experimental verification of Corder's supposition with respect to primordial black holes. But Corder's supposition with respect to black holes is very important. Please go to this slide 2 of this, okay? Tim, please go all the way back to slide 2. Very important. Can you go back to slide 2? Second, the next, that's, okay, here we go. 1, 2, and 3. All right. Now, all this sort of things revolve with respect to Eric physics, but that topping off, that delta E over C, which is 10 to the minus 12 GeV instead of this enormous number, which is essentially Planck energy, is due to Christian Corda giving me where could you, how could in the initial creation of black holes, let's say, as far as APEC, which you might call contributions to a vacuum energy. So I want to thank Christian Corda for that insight. Otherwise, this document would not have been possible. I just want to thank you very much for that. Now, the document was 10 Ventura. You can look at it. You can contact me if you have questions, rwill9955b@gmail.com. And you can argue it with me from here to Timbuktu, and I don't mind. As I said, I am very appreciative that 10 Ventura was gracious enough to allow me to talk about this. As I said, I had situations where people, and also Rencontres du Mordion really liked the idea. It's going to be in the program. And COSPAR kicked it out and called me crazy. So, which is, I want to thank you very much for tolerating me. And if you have questions, you can ask me now. The paper was 10 Ventura, so that you can go through this line for line, and you can ask me questions, and I'm more than willing to try to answer them.
Well, Andrew, thank you. Thank you so much. Now, you did have another paper as well. We have about 15 minutes left. Did you want to run through that, or would you like to save that for another day?
Yeah, let's go to the next paper.
Oh, okay. Okay. Well, let me take that one down. I took out the syntax, but I did put your email in there. So for anybody who wants to email you, that's in chat. I just took it out so that scammers won't just rip it out and auto email.
Yeah, I am fully aware of that. That doesn't bother me one bit. Okay. This is the durability of the Riemann hypothesis. I introduced this because actually, which is, let me just tell you, the reason I'm bringing this up and I presented this to you for you to think about is because the questions of the Riemann hypothesis in terms of the zero and other things of sort, I would say, had an intimate tie-in, so to speak, with some of the things which I am trying to be doing about the relationship, the eventual mathematical techniques which are used to identify an optimal end, quantum state end, with respect to black holes and other things of the sort, are going to be linked with respect to the Riemann, some of the things similar to the Riemann hypothesis. Now, this is a very important paper. Using result of recursive function theory and results of the complex analysis of which is based on a type theory in the work of I can't pronounce that name. It's conservative estimate first order piano arithmetic. We show the Riemann hypothesis decidable. All right. Now, what I'm saying is that you're going to have to use equivalent mathematical techniques, and this is I gave this a 10 for a reason, because some of the same issues which are in this paper, which is what I would have to come up with, would be to come up with an optimal state of N, which is with respect to the energy associated with respect to a relic black holes. This is the primary, I put it in as a hypothesis and other things destroyed, because of the fact is that in Torsion's model of black holes, that you would have that energy with respect to that quantum state. But in order to identify something like that, what to come up with bracing this modeling and other things of sort is this Riemann hypothesis, and some of the same techniques will eventually have to be used. And so this is the reason why I send it 10 Ventura for a reason. So, which is, you can read this paper too.
Oh, and Andrew, I should mention, so I dropped a link in earlier, and this is on the page for this event, right, on the Alt Propulsion site. People can download these. We have a Google Drive. It's a read-only link so that people
Oh,
can
that's
download
great.
these.
I had 25,000. I had 25,000 people who are subscribed to me in LinkedIn, and I'm a big noise box. You see me. I talk about anything I damn well want on LinkedIn.
Yeah, and yeah,
I'm a
actually,
court jester in LinkedIn.
if you'd like, I can put your. Do you want me to put your LinkedIn?
Go ahead.
Okay, yeah. Let me. Here we go. Okay, sorry about that. Well, Andrew, let me thank you so much for presenting today, and we do have a few minutes left. Do you want to do? Should we do Q&A?
Well, just ask whatever you want. Just simply
Okay.
is that
Yeah, well, let me do this. Let me take I'm gonna remove the paper and I'm gonna bring everybody in right now. Everybody who has their camera on. Let me see. And everybody, please put your hands together and give a tremendous applause to Dr. Andrew Beckwith. Andrew,
Well,
you
I
have
got
been,
my ass shot off by COSPAR on this guy was rude to me in the Christian quarter, and quarter told him to go to hell. Told
well,
him to go to hell, but other people like it, so it's controversial. I accept this.
I just want to say thank you for the tremendous legacy. I mean, you have been doing work in this area for decades. You were at the STAFE conference. I believe you were at the Tony Robertson's SPECIF conference. So you have been contributing and working on this science for so long. So thank you. Thank you so much for that. And
Well,
thank you
thank
for,
you. Well, I'm glad at least is that I did something that's not totally worthless.
no,
It's not totally worthless. That's a good thing. I just want this to improve the state of the art.
yeah, I think it's tremendous work and tremendous contributions, and you've created an amazing legacy. So thank you. So let me see. Does anybody, you guys have any questions for Andrew?
Yeah, sure. I'll try to answer them.
Michael, go for it, sir.
Go for it.
So, Andrew, my question is, you talk about primordial black holes. Are you saying by using the word primordial, are you suggesting there has to be a Big Bang?
I'm suggesting, well, that's an open question. Let me try to phrase it this way. Okay, look at the Penrose cyclic conformal cosmology. Look at Penrose cyclic conformal cosmology, what he had. I tried to do a multiverse generalization of this. All right. But the situation was that I was assuming is that you would have an input from a prior universe into a present universe that may or may not be equivalent to a Big Bang. It may or may not be equivalent to inflation. It may or may not be, but it's an input. And I tried to do it with respect to things that are which are connected with respect to cyclic conformal cosmology with some
So, for
generalizations.
example, instead of a bang, it could be like a jet.
That's possible too.
So, so it would work. Sort of the same question I asked Dan. If we assume that we have like a steady state universe where it's like a bud on a plant, the new plant starts as a bud. It's like itself reproducing something that the previous universe creates something that creates the current universe, correct?
Correct. What I did was I took a number 1 over n. I took a number 1 over n, the number of potentially, existing universes might be is huge, and time what you times a summation with respect to a partition function for universes. And there are works of Popolowski and other people did this. And I would say in effect, as I would speak in terms of a so-called averaging, you get a rough averaging of something like that. That's the reason why I asked the question I did with respect to Dan, with respect to, they said, I was trying to, what you might call, cut down the variance, so to speak, in terms of the wideness of the possible terms, so the physics laws might be different, but they wouldn't be totally different. In other words, is that what you have in some cases, which I have big questions about, is that you have example of some people who would say there are 10 to the 120, 10 to 120 different possible universes, and they talk about a Darwinian evolution of universes and all this, and there are things of the sort. And so I said, well, and you could have cosmological laws, which are all over the space, all over the space. So I tried to come up with a supposition. You might have a variance of this sort of thing, but you'd have some sort of a rough averaging, so to speak. In other words, is that the physics laws would be different, maybe different, but they wouldn't be completely different. Whereas other people would be assuming, example, Susskind and other things sort of, is that you'd have this Darwinian die-off in which in most of the universes that would be created or existed in terms of the multiverse would die out because they would not be viable. And that's one of the things. So I made another choice. Now, in terms of the budding, that's possible too. I was just merely trying to put a so-called averaging of the cosmological constant, with everything to come up with that with respect to an admissible, and say in effect you might have, so to speak, at the nucleation point, a so-called averaging, something like statistical physics averaging that would occur properly.
Okay, and then a follow-up question I have is, what if it's just, what if the universe just is, and there is no
Well,
beginning?
then, which is
For
then I'm wrong.
example, basically recent James Webb telescope, they've been able to go back to right after the so-called Big Bang.
Yeah, I know it did.
And it wasn't and they found what they didn't expect. They found galaxies that were the same size they are now. And
well, that's
so
completely to
it
be
seems like
expected.
the expansion of the universe is a fact, but the stuff in it isn't expanding. It's
Well,
not.
there's another way to state that, which is that, and it's actually the reason why I started my model is for a very specific reason, because I anticipated something like the Hubble discovery about the size of the galaxies. I anticipate that. So what I'm saying is so-called evolution of cosmological structure is just what we have today is completely wrong. And so if it's completely wrong, we may have to have another structure of input and possible expansion, which will allow for the fact is that a so-called generic cosmological model is wrong. So that, as I said, what the Hubble, what the Webb telescope is showing is something which I actually expected from the very beginning, and this was the motivation for me doing what I did in the first place, was to take into account something like this might be possible.
Cool. Well, thanks for answering my questions. I appreciate it.
Well, I'm not saying that I'm right. If I'm wrong, then everything I did is waste paper. Throw it in the garbage can.
Well, then you have wisdom.
Well, Michael, thank you, sir. Let me see who else has questions. Dan or Jared?
Hi, Dan. If I've spoken nonsense, I apologize to you, sir. I'm trying not to.
So more of a comment than a question. There's a couple papers I think you would benefit from reading. One from Sean Carroll, the other one from Yuri Oroshenko. I'm going to link them in the chat. They're titled "Escape from a Black Hole with a Spherical Warp Drive," and then the other one is called "Branches of the Black Hole Wave Function Need Not Contain Firewalls," and I think they're pretty relevant to your work. So I'll go and link
That's
them
exactly
right
correct. I'm aware of it, and I was doing it, and I was very suspicious. Dan, I'm glad you brought this up. And the reason is because there's a second addendum which I can put to this. Okay, you know what it is? Let's talk about the black hole, white hole ideas that people would have. And they say we'd have something like a wormhole. Okay? We'd have something like a wormhole. So I asked a very specific question. We transit from a white hole to a black hole. How fast does that occur? Is that entanglement or what is it? Is you put in the so-called idea of a firewall in that situation. You understand what I'm saying? If you put an idea of a firewall in that situation, is that frankly, is that you can't use the uncertainty principle or anything else of sort, because they would say, in fact, the so-called traditional treatment of the wormhole is that it had negative energy at the so-called throat. You understand what I'm saying? Negative energy. Okay, and the negative energy, and then, oh, well, we have something transit from positive energy, the negative energy, maybe the positive energy. Oh, okay, that's wonderful. Well, how quickly did it occur? Well, is you put in firewalls the fact that you have negative energy at the throat that required, like like a thorn and other things sort, and is like Kip Thorne, and also to people, other people have been doing, is that you're going to have problems if you're going to put in the firewalls. You're going to have problems is you think like a black hole and a white hole is a pair. All right, black hole and a white hole, and you join them with a wormhole. Oh, that's wonderful. Okay, so you do that, and you talk about transfer something like from one to the other. Oh, that's marvelous. Well, is you have it's when you were doing it, if you put in the firewall, nothing makes sense. I just am saying why it doesn't make sense, because you have right at the throat the negative energy. And this is, Visser, Matt Visser puts it in his book, which he wrote about black holes. About wormholes explicitly. And so this is the reason why I was thinking in terms of black hole, white holes, and other things, and how you might be able to join them. And I just simply said, yeah, but it goes to the question of the viability of a warp drive too.
What are your thoughts on ER equals EPR?
What I'm referring to is that if it's a wormhole, which is one of the so-called ideas for a warp drive, you transit through a wormhole or something like that. And if you have a black hole and a white hole and other things of the sort, is that these things are not transversible wormholes. Okay, there's something else. Is you want to have something that may have transversible wormholes, and you're talking about a black hole and a white hole. You better not have firewalls in that situation, because the construction is just going to be garbage in, garbage out. So this is the reason why I was so receptive to what Corda was talking about. You understand? That was the reason. Because this is the problem which I'm thinking of. Black hole, white hole, or wormhole. Can we talk about a transition from point A to point B through this type of construction, other things of the sort? Well, and you have the negative energy, which is put in here, and other things. Oh, that's wonderful. Well, now we're going to talk about transiting from the sort of thing. Well, if you're going to faster than light transition from one curved space to another, it's one of the models that people had about whether you use wormholes. Is that, and if they are a black hole white hole pair, is that you're just going to have essentially the conclusion is going to be anything that would attempt to do is going to be a suicide mission. So you better hope that there's not. You better hope that they're not firewalls. Because if there are firewalls, there are big problems. So that was one of the things which grabbed my attention immediately, because I did read Visser's books. I read them very closely. I even argued with Visser over this. That Visser, I saw him in 3 conferences, and I argued with him over this, and he just blew me off. Said, "Oh, it's just not even worth discussing." Okay, but you think about it, Dan. I think you would understand why I'd worry about it. You understand what I'm saying?
Yep.
What's the construction of a wormhole? So you can have something that's transversible. So you might be able to use a warp drive to go through a wormhole type of construction.
Yeah, so read that one paper that I linked, the escape from a black hole, the spherical warp drive, because they end up proposing something called it's complementary to the ER equals EPR. It's they suppose the WD equals EPR conjecture, where basically kind of what you're saying, warp drives through entanglement can.
I've not read that paper, but I just am saying I came with this on my own because
it's right up your alley.
Obvious. It's obvious.
Wonderful. Well, and guys, we're just about, actually we're at the top of the hour now, so we're going to lab time. If it's okay, I want to give Dr. Andrew Beckwith, actually, let me bring Charlie back in. I'll bring Phil in, that fills up our studio. I want to give Dr. Andrew Beckwith another tremendous applause. Andrew, thank you. Thank you for, and you're welcome to come back from China virtually. I mean, it's just as easy there as it is here. Or
I'm going to probably be there or something like that in the third week of January. I'd had foot surgery. I had 2 joints in my feet which had to be replaced.
Yeah. Well, and thank you for taking the time to go through this with us.
I'm laughing at myself. I'm not very important. I'm glad I gave a discussion with you. And Dan, please send me those papers, the complete papers. I want to see them. You know what you said when you just were last talking about with me?
Yeah, they're in the chat.
Please send a complete text to me. I would be so indebted to it because I'd never read them, but it was obvious to me just thinking about the problem, what I said, it was just obvious. And it's the reason why I was so receptive to that treatment because they said, that people have cobbled together a whole bunch of stuff and it's nonsense. Okay. And so this is why I'm saying is that I don't mind. Example, I hope at least I contribute a small amount to the state of the art and what occurs later, which is I'll be thankful is people use 1% of what I did. It provides some insight. That's all to the good. And I want to learn more about what you're doing too. So my email is rwill9955b@gmail.com. So please do me a favor and send me your papers. Okay, what you're referring to and other things, and I'd love to see it.
Wonderful. Well, Andrew, thank you yet again, sir. So let me do this right now. I'm going to take everybody out of the studio for just a bit. I'm going to go to Mr. Mark Sokol, and we are going to do some lab updates, and we'll kind of bring people back in as we go. Again, thank you so much, Mark. Merry Christmas. Merry Christmas. See, I
Merry
did
Christmas. Yeah, you did the hat. It was your idea, actually.
Was it? No, this was your idea.
Yes, it was. This was your idea, and I actually reminded you about it. Yes.
Okay. So, yeah. So we could do like a song and dance number. Look at okay. Yeah. There we go. See.
Actually, mine has 2 little bobbins on it. So.
Oh, but again, mine's from the dollar store. It barely fits, but So you had a presentation on lab updates for us, right?
Yes. Actually, after seeing everyone else's presentation, I felt a little inadequate just to give this verbally. So I was hiding out in the background while everyone was presenting and put together a little PDF to show you guys some pictures and a description of what we're doing.
Did you upload it? I don't see it, but
yes, here it is.
Oh, there it is. Okay. Well, let me get myself out of the way. Yeah. Thank you, man.
Thank you. Okay, so dynamic nuclear orientation. This is our inertial mass shielding experiment, otherwise known as the Alciphon experiment. Now, for APEC regulars, you might have noticed that I haven't been doing much updates recently in the past 2 months. That's because we've been doing a really large project that sort of put everything on hold. And that sort of built up to actually several projects that are all connected together. And we're going to dive into that right now. So I want to give you guys an update what it is we're doing. So basic overview. This is for people who aren't familiar with the Alciphon experiment. The paper, it all started with this book, actually, Ufology by James McCampbell. David Alciphon, the son of Frederick Alciphon, found this book in a used bookstore, and in it, it describes a case that was supposed to be part of Project Blue Book, which was removed because of security reasons. But basically, an AWACS plane, I'm not sure if I spelled that correctly, one of those communication planes that have large radar antenna on it and can pick up all sorts of radar and RF scanning, and it's basically a spy plane, got in really close proximity to a flying saucer and collected actual data from the craft, and there was a really strong 2.995 gigahertz pulse, pulsing on and off 200 times a second roughly. And that is empirical data about how these flying saucers operate, and it was classified. But James McCampbell somehow got that data and published it in his book. So David Alsafon took that book to his father, who they all had a sighting a year or so earlier, and his father, being a top tier physicist, was adamant he needed to figure out how this happened. So he went to a library of various scientific papers and books, and the book by C.D. Jeffries. I'm trying to hold it up over here, but it seems like it's. Yeah, okay, this book over here, Dynamic Nuclear Orientation by C.D. Jeffries, which was published in 1963, literally fell off the shelf in front of him and onto the floor. And he picked it up and soon realized that this was describing an interesting state of matter that it's basically coherent matter. We're trying to orient the subatomic particle spins. And with all this in hand, he realized that he was onto something. He filed for a patent. And since he already filed for the patent, he thought, I'll just throw it out there. And he wrote this paper and had it peer reviewed and published in the 1981 Joint Propulsion Conference. I actually have a copy of it over here, but my screen is probably not going to let me show it. But in it, he describes a method of orienting subatomic particle spins, and with it, making matter weightless, which would explain how these craft can do 90-degree turns at 10,000 miles an hour. So subsequently, the patent was rejected for no good reason, probably because the military-industrial complex already has this technology. They replicated the experiment in 1995 and had 80% weight loss within the first second. Then the company fell apart because the people involved couldn't get along very well. Everyone was arguing about who owned what in this company that really never existed. And I actually confirmed that recently. I was actually able to get in touch with some of the people that were involved in it, and they're very secretive about what exactly they did. But the bottom line is it involves electron paramagnetic resonance, which is a subset of nuclear magnetic resonance. It's just higher frequency rate. Well, we never achieved an 80% weight loss yet. That would have been astounding if we could have gotten that. The early attempts were, you can see over here, this was in circa 2020. We did get 17.8% weight loss. And with this was a piece of aluminum foil, aluminum being one of the better materials to use because of its retention of the dynamic nuclear orientation state. So it has the longest decay time. Aluminum as well as magnesium. In order to get that effect into the aluminum or the magnesium, you need to have a little bit of iron inclusions included, which is part of the process. So that was covered in ferrofluid, which is basically just iron, really fine iron powders that are mixed with oil. In this particular case, the magnetic field was oriented upwards. In order to get the measurements, we had to use like a chandelier, like a lever system in order to get the measurements. That's pretty difficult thing to set up. And in subsequent tests, we actually changed the orientation of the magnet, but it didn't help. This was with 10 watts pulsed X-band RF that was fed via the horn antenna. You see that green antenna on center right. So this is some of the earlier setups. Later developments, we turned the electromagnet on its side. You can see it over here. It's on its side. That had a negative effect on the weight loss. We did still see weight loss and strange movements. We then went searching for a better electromagnet, an RF amplifier, and also one other thing is we moved the experiment into the Faraday cage. Jeremiah Pop was with me at this time, and we started getting headaches from the RF. X-band microwaves, by the way, are about 1.25 inches long. That's the wavelength. So that's many things in your body will resonate with that. Anything that's 1.5 inches long that is slightly electrically conductive. So yeah, not very good for your health. So we got some better equipment. We got a 250 watt X-band traveling wave tube amplifier that came to us from Sandia National Labs, which is actually where a lot of this anti-gravity research was supposedly taking place. That's down in Albuquerque, New Mexico, and actually was there right when Sandia released it, and we got it from the supplier that basically digs through their garbage. We got a large industrial grade electromagnet. Thing weighs about a ton. We put it on casters, rolling it around the shop. Got various probes, cameras, sensors. All this are being fed into an OBS screen. The data was recorded in a live video. So I'll get to that in a moment. So the problem basically was that all this data is getting fed into an image instead of a squiggly line chart, which, as you saw from Drew and Charles' system, I'm very jealous of that. That's what we really want. We want to see squiggly lines. We don't want to see data on a screen that just, is just numbers that keep on changing, or on a video screen. So this is kind of what it looked like. It was like watching grass grow in slow motion. So the features were added as they became available and as we realized that they were necessary. So we were slowly adding different components. At one point, we added in a fiber scope because we thought the RF will be so intense it will destroy any camera. And then we went to different cameras. We went to those GoPro cameras inside of a shield thing. And then we realized that it doesn't even, the GoPro cameras are fine on their own. They don't even need the whole shielded thing, a custom shielded case that we built for them. So we went a little overboard with RF shielding of the cameras, but bottom line is that wasn't even necessary data. What we really need is the screen on the right side of the screen. You'd see 0.224 whatever grams. Those are the measurements that we actually needed, graphed along with a bunch of other stuff. So data capture method left a lot to be desired, and many other useful data sets may have been lost while we were running this experiment. So we decided to basically stop it all, stop running these experiments because there was too much data that was being lost. So the thing about electron paramagnetic resonance, the way you know that it's actually happening is by measuring the SWR, the standing wave ratio, or the better explained as the absorption of the material inside of the chamber. So RF is going into the chamber, and then some RF is bouncing back. You tune it to the chamber as best as possible so that it's coupled. Most of the energy is going in. The sample's in there, and the magnetic field changes. And as soon as it hits the right resonance, you'll see a drop or a peak in the amount of RF that's bouncing back. So in order to do that, we have these 22 gigahertz spectrum analyzers, and what we're really looking for is the dBm, or the signal strength of the returning peak signal, and that's data that's absolutely necessary. So we have two of those spectrum analyzers. Both of them, they're all getting connected together now in this program called LabVIEW. And in the modern day and age, we're actually able to have people remotely program this. So we have Sam from Pakistan who's been helping us. This is me and Sam working. It was about 11 p.m. at night, and he's programming our 20 gigahertz oscilloscope. So that's going to the oscilloscope's going to be snapping pictures of what the waveform looks like at interesting times. Then we'll be able to save that data and look at it. So if there's like something interesting that happens, a change in the scale that, it lost suddenly 2% or something like that, or a certain threshold, we'll get a snapshot of the oscilloscope and try to, glean whatever we can from it. Spectrum analyzers are running continuously. They're going to give us the dBm of the peak signal back. And with that, we'll actually see EPR spectra, because we're going to be changing magnetic fields. On the x-axis is magnetic field strength changing, or time, because we're going through a scan. So you could just make that time. On the y-axis, that will be the RF coming back from the chamber. Electromagnetic sweep. That's we're also got a Gauss meter that will give us live data from the magnet itself. So we'll be getting data from the electromagnet and from the power supply of the electromagnet, and from the electromagnet itself via a very special Hall effect sensor that can go through a really large range. 4 temperature probes are going to be placed throughout the experiment. We don't want heat affecting any, creating air currents that are going to give us any weight loss or weight gain or whatever. So we'll also be able to change the frequency read the pulse frequency and FM and AM modulation of the RF signal generator. Also, we're going to be doing something really cool. We're going to be, while we're doing electron paramagnetic resonance, we're also going to be doing nuclear magnetic resonance. Now, the reason for that is dynamic nuclear orientation, or orienting the subatomic particle spins. The only known use for it right now in academia is to increase your nuclear magnetic resonance signal to noise ratio. So in order to know for certain that we've achieved dynamic nuclear orientation, we need to see an increase in our nuclear magnetic resonance. So we need to actually be running an NMR probe. And in order to get an NMR probe into that system, we're going to have to change the frequency of the NMR as the electromagnet changes. So all this is going to be happening simultaneously, controlled via the lab computer in a LabVIEW system. So, and we're going to extract from that just the signal to noise ratio and add that to the chart. And it's going to be a ton of data. Hopefully it can refresh in a timely manner, and we'll get some relevant data. Oh, this was a big, exciting paper that popped up while we were in the middle of the entire LabVIEW hiatus. And that is a new paper that talks about a possibility of room temperature hyperpolarization of nuclear spins in bulk using triplet state electrons. So this paper, we found it using this new physics GPT app that Jonathan, that's Jeremy's brother, created with us. And this is possibly the holy grail of dynamic nuclear orientation. So basically the paper says, and there's several other experiments similar to this. Basically, it comes down to hitting pentacene, which is a molecule of carbon hydrocarbon rings, like benzene rings, but they're complete benzene rings. So Ron Kita, if you're there, these ones won't give you cancer. So if you hit pentacene doped crystal with an intense light, it will create triplet state electron pairs. And on the bottom of the left side, you can see what a triplet state electron is. Left is singlet, middle one is a doublet, and the third one on the right there, that is a triplet state. Those are two electrons that are both roughly spinning in the same direction, and they're free electrons. Now, what happens is when you create these triplet electron states, if they are inside the cavity where the microwaves are acting upon the sample, they will combine with the microwaves and dig into the sample and, penetrate it and act upon it even stronger, to the tune of 250,000 times better. And according to the paper, they made their crystal using the Bridgman method. I don't know if that's necessary or not, but we're going to try that as well. Just to be true to the scientific paper. Another thing they were doing is they were using heavy hydrogen, which increased some of the effect as well. But we should see at least 100,000 times enhancement if we're not using heavy hydrogen, otherwise known as heavy water. So we're working on that. So the Bridgman method. On the right, picture on the right, you can actually see this test apparatus that we're putting together. It literally fell into my hands. I went searching on eBay for the type of oven that I would need, and it turns out it was like a 10-15 minute drive from the lab, and it was being sold for not even pennies on the dollar. These are like less than a penny on the dollar of what these things would cost new. Literally handed to me by somebody who works in hydrocarbons for a living. And he was very interested. He might come down to the lab to help out. So basically, this is a 2-temperature oven. So you have 2 coils, one on top, one on bottom. And it's a tube. And we put a baffle in between the two temperature zones. And we have high temperature on top and a low temperature below. And the high temperature needs to be above the melting point of whatever it is you're trying to crystallize, and the low temperature is obviously below that. And you slowly, and by slowly, I mean over the course of, many, many hours, if not days, you slowly lower a vial of whatever it is you want to crystallize through that baffle, through a hole in that baffle. And as it reaches the bottom part of the baffle, it should start to crystallize extremely slowly. And that is a way to grow single monocrystals. Similar methods that incorporate a spin are used in industry to make silicon monocrystals. This device over here can probably even do this for aluminum, which would be really cool. Make a monocrystal out of aluminum, but it could definitely do it for a lot of different materials. So we're very excited about that. Anything that can melt at below, like I would say 800 degrees centigrade is probably what it's good for, would be able to work in this system. Borosilicate glass test tubes are going to be dropped really slowly, and there's a little motor over there. What is that? A stepper motor with a 50-to-1 gear down ratio to really slow it down. And the wire is tungsten wire. It was special shipped from the Orient. Took like a month for that, just for that little piece of wire to arrive. And that's good for like 1200 to 1500 C or something like that. It's really thin wire that was custom. The pentacene is that purple powder you see over there in my hand. Actually, that is being stored inside of an argon atmosphere. That's why there's a little haze in the background. It's inside of a bag filled with argon. You want to make sure not to get that near any air. And it's very expensive and difficult to get. So we're going to be perfecting our crystal growing method with naphthalene, which is otherwise known as the smelly version of mothballs. And once we get that monocrystal growth system going properly, we're going to add a little bit of pentacene. Now for a light method, the paper recommends using IPL, or intense pulse light. That's a laser hair removal machine. So that's what they used. We purchased one. Probably going to use that as well. We also have a nitrogen laser with a controller on it, so I can actually control when it pulses it. But the bottom line is we do want to fill that chamber up with these triplet state electrons. The microwaves will combine with it and do all their magic. So this is pretty much what's been happening in the lab. I don't have any more slides. If anyone would ask any questions or anything, if anyone wants got anything else to talk about, please don't be shy.
Sorry. Oh, I'm missing my hat too.
Can we put a copy of that document in the chat?
Yeah. And
which document are you talking about?
The one that talks about the pentacene.
Pentacene, room temperature, hyperpolarization of nuclear spins in bulk.
Mark, that's oh look, there's Bernie. Bernie, thank you. Bernie's the one who cleaned up the See, Bernie is our StreamYard master.
Had to show up. Merry Christmas, everyone, and happy Hanukkah.
Merry Christmas to you, Bernie. Merry Christmas to you. We should give Mark an applause. Mark, that was
absolutely epic way to finish off 2023 there, Mark.
I am just blown. I'm blown away. I am blown away. I see like a team and a community coming together. I see people sharing and contributing and building off each other. And like today is one of those events where it all comes together. It's just like hit after hit after hit after hit, right? And it's brilliant minds who are working together and sharing in a positive, collaborative way. So I'm like your number one cheerleader here. I'm so excited about this.
Thank you.
And we just basically saw two valid types of electrogravity or electrogravitic sort of tech, like, come out just today. That was amazing.
Yeah, I know. It's absolutely amazing. And
the thing that Drew's working on, based on what Charles was saying, that's confirmed to be. That's basically Townsend Brown's. That's a continuation of Townsend Brown's stuff, or a rediscovery of it, effectively.
And then the work that Dan put up and the work that Andrew was describing, I mean, again, this is just absolutely brilliant. So I feel like I'm definitely the dumb kid, but I'm overjoyed to be the dumb kid. I feel so happy about that. Please fill the room with people who are smarter than me. Please, You
never want to be the smartest person in the room. See how miserable Rick is in Rick and Morty?
That's exactly it. And when you find someone that always is trying to be that smartest person, it's like they're usually the ones that end up holding progress back. It's trying to learn and share ideas with everyone and figure out together.
I'm for me, I'm just happy cheerleading. I'm happy cheerleading the people who are doing the work. I'm happy. That's like, I think that's what it comes down to, you know, and that includes Mark. And Mark is, I mean, I talk to Mark all the day. He has an amazing presentation on his stuff. So it's project after project after project that are moving forward. The theory is moving forward. There's this cross pollination that's happening. I'm just overjoyed. I'm overjoyed. So,
sorry to interrupt. Do you mind I do a pitch, like a 1-minute pitch? I just want to present what I've been working on.
Sure. Phil, do you want to do kind of a lab update? Go for it, sir.
Yeah, sure. Thanks.
Mark, are you able to spotlight him, or let me see?
I think we need to knock everyone out.
So no, solo layout. I think that did it automatically. There you go, Phil.
All right. Thanks. So here's regarding the grinder experiment. I shared this with some defense companies, and they asked me to do it it's the same thing as my former grinder experiment, but I kind of improved the discrepancy, the way it's presented by using a Harvard trip mechanical balance. So I'll run the video right now. December 11, 11:40 p.m. So I did this. So you can clearly see that the spinning wheel is affecting the gravity, the weight, the overall weight by generating a gravitomagnetic field. Again, gravitomagnetism, gravity for me is simply energy density differential that creates some sort of force. So you can use any type of energy, and again, you have the gravitoelectric, gravitomagnetic, electric, and magnetic field. It explains the 1919 light bending. It's pretty much an explanation to the time dilation and gravity mixed together. It's all caused by energy density differential. So yeah, I gotta go right now, but that's all I wanted to share. I wanted this to be archived, and thanks again for your time. I really appreciate, and Merry Christmas and Happy New Year to you all.
Yeah, Merry Christmas and Happy New Year.
And Happy Hanukkah.
Merry Christmas to you, Phil. Thank you. Does anybody else have lab updates for us? Do you guys have lab updates on anything you're experimentally working on? I guess we should.
Yeah, I got one.
Okay, yeah, Drew, go for it. Today was a giant lab update for you, but
Yeah, that's just Dr. Charles talking. Just looking for where to present.
The very bottom middle of the screen.
Yeah, I'm hunting for it. Share screen, sharing screen. Share.
It's called present, Drew. It's the present button in the middle of bottom.
Oh, okay. All right. I hate technology. I don't know. Can y'all see something that looks like a stack of white plastic?
yeah, it looks like it's displaying. It's doing your whole screen for us.
Yeah. Okay. First of all, y'all saw the Dr. Charles all polished and giving his presentation for, after he wrote it all down. This is the Dr. Charles we have to tolerate. Up at that stinking whiteboard with the hundreds of theories and crazy concepts and stuff. And, if there weren't chicken wings and pizza involved, nobody would go. So just wanted to let you know that that's the other side of Dr. Chaz. And when you're in that room, you are not the smartest guy in that room. I have very humbling time in that room. Just wanted to show you something. This is where we were about 3 years ago with this is the plate technology from 3 years ago. That thing there weighs about a kilogram, maybe a kilogram and a half, and made about 2.5 millinewtons. Compare that to this is where we were, and this is where we were, I don't know, 2 weeks ago. This unit made 9.1 millinewtons of thrust and weighed in at a whopping 300 or 720 milligrams. As you can see from the graph, it used about 600 microwatts to do all that magic, and I had it running for something like 54,000 seconds, which is about 14 and a half hours. So that was a fun test. That was the 4th time that unit had run, and the only reason it came out of the chamber was to put in something other, so the next iteration. So these long duration tests really try the heavy equipment. You gotta keep track of the drift of the system, the mechanical drift, the thermal drift. It's a real exercise, in patience and in testing skill. So yeah, I'm pretty sure that's all I got. Happy Hanukkah, Merry Christmas, Happy Kwanzaa, Happy Festivus.
Yeah, well, thank you, Drew. Oh, I haven't heard Festivus in a while. That's been off the air for quite a while now.
For the rest of us.
Did
Yeah.
was Charles back there? Oh, yeah. Oh, that's different Charles. Oh, there's
There we
okay, Charles Buhler. Cool.
Yeah.
Hey,
let me
Charles.
just- well, and
Awesome
Michael, you're working
I
on
missed
stuff.
out. I was in the lab. Oh, sorry, Tim. Go ahead.
Oh, well, you're working on stuff as well, Michael, and then I know Jared and Charlie are as well. And or if you guys want, at some point we could just go to open discussion. That would also be absolutely wonderful. It's whatever works for you guys at this point.
My brief update is we're doing LK99.
And he froze right as.
Michael's computer is specially designed for cliffhangers, so and he has done this in many meetings. He'll be like, "And the secret is," and then he freezes.
Still, we found that.
And he's gone.
Yeah, and he had to add those words in there. And we found that, bam, there it disappeared. Let me see. Jared, you want to go?
Yeah. Let me share screen.
Okay, well let's put Jared on solo layout. Sorry.
There we go. Screen. There we go. So Charles and I went down to Texas and got to do a bunch of different tests in some vacuum chambers. And most all the tests dealt with electrostatics and ion thrust. And Charles, please feel free to jump in at any time. So this was the NAM-TRAM thruster. You have a positive electrode in the center and a negative electrode on the outside, or vice versa. And you apply a good 40,000 plus or minus 10,000 volts to the thing, and sure enough, you get it spinning, but that's an atmosphere. You put it into this fishbowl dome vacuum chamber, and over on the screen there, you can see we're down to 4 PSI, which you're getting up to like 40, 50,000 feet there, and it's already slowing down a lot. We figured out, let's see, I can go back here. We figured out that at about 6 PSI is really where it starts losing most of its momentum, which equates to about 25, 30,000 feet. There's a significant change in ion propulsion at relatively low altitudes of pressure. We also did some interesting tests with these parallel plate capacitors. So the idea is you charge up both sides of these capacitors, and when they arc over, it provides a repulsive force on this ruler that is set above it. We have this piece of aluminum foil separated by a piece of paper over the top of the parallel plate capacitor. Turned out on this one that it was just transferring charge to this wooden ruler, no metal in this ruler whatsoever. But during the charging on phase, it would attract it very strongly. And then the moment it arcs, it swaps the polarities of stuff. And so that's what's pushing it away, is it has now swapped the polarity of stuff on here as compared to the charge, static charge that is built up on this, with about 20,000 volts or so on this parallel plate capacitor. We ended up measuring with this static meter here, it got to about 2,000 to 3,000 volts per meter. And we had arcing problems like crazy. Let me fast forward here a little more. We did some neat arcing tests of the thing as it started burning through the paper. Here is kind of a bifield Brown thruster-ish. This is first a symmetric capacitor, 2 copper discs separated by a mylar dielectric. Each of the discs are oppositely charged. You can see it spins around there just great, but this is sped up. We got down to about 6 psi. Sure enough, it stopped spinning. And then we altered it and we took off one of the copper discs. So now you have a copper disc, mylar, and just the wire on the backside. So it's a little more TT Brown-esque with the very small electrode and very large electrode. And surprisingly, it provided about the same amount of thrust as it did with the 2 large discs. But once again, 6 psi, 25,000 feet, and it takes a nosedive. So we're barely down even to 8.5 psi and it's already slowing down quite a bit. 6.5, 6 psi stops moving altogether. So if you want to go at really high altitudes, you need a lot higher voltages. Let's see if I can fast forward here a little more. We did some testing with, oh, here we go. We did a bunch of arc gap testing in different atmospheres and pressures. I believe this was just straight atmosphere. Let's see if I can get this to load up a little bit more. There we go. Ooh, pretty. Then we started putting some argon in there. And it should be called arc-on because even small amounts of argon will allow it to arc much easier. And fast forward here a little more. More ruler testing with sparking. The one notable thing about this, doing it on the tabletop, it was very notable here towards the end. It gets very strongly attracted when you turn it on, but I don't think I caught that in this part of the video. Getting towards the end here, more arc gap testing in different atmospheres. Fast forward here to the good stuff. So now we're going to very low atmospheres. There we go. Very low atmosphere pressure, like I think it was 200,000 foot pressure. And then we started putting some argon in there. So it was almost just straight argon atmosphere. And as we continue to decrease the pressure from 200,000 feet to 300,000 feet, it starts getting real big and starts filling up the dome with this gorgeous off purple hue that just wanted to creep down along this octopus arm that we had holding one of the electrodes. And it started arcing up against the side of the bowl there occasionally. Speed that up a bit. Apologies for the shaky camera. My other camera died, and so I had to hold my GoPro. But fascinating examples of arcing in very low pressure environments. Also fascinating how you can see these multiple layers of coronas in there as well. And there we go.
Mm-hmm.
Yeah, it was interesting that the base of the vacuum chamber was metallic, so we had difficulty running the high voltage directly under it, and we ended up putting the smaller high voltage power supplies directly in the vacuum chamber. We worried at first a lot of the equipment like the transistor capacitors, diodes, and everything might not survive the vacuum, but it all survived it well. And yeah, it just had to do with feeding the high voltage through was kind of shorting to the metal that was affecting the sensors that was connected to the vacuum chamber. So it ended up working that we could just put the power supplies directly inside the vacuum chamber. And as you mentioned, we were using argon gas that they had there where we could test, and and we also used helium gas, and both those seemed to slow down the thrusters that we were using with the ionic wind. So that might be something for a future experimentation. But we weren't brave enough to do the hydrogen. They also had hydrogen gas, but we were worried high voltage and hydrogen in a vacuum might be too dangerous. And yeah, it was very interesting that the high voltage, it was 2 flybacks on a ZVS, and that survived almost the full vacuum and was able to do the spark gap inside the vacuum chamber. So that I think will help with future high voltage thrusters that will be used in the space applications. We use power supplies similar to that.
Yeah, it was very, very surprising and impressive how well so many of the electronics held up in vacuum.
And I've got the Amtrans thruster here, if they want to take a closer look at it. There's the positive, was just connected here on this carousel, Amtrans design, 3D printed. And we've got some insulating black RTV. He used about 3 different types of insulating epoxies to create that. And then the aluminum base, which is the ground, and the 2 grounds are connected on the bottom, and then we just run the wire there, and the high voltage is on top. And it's all connected with this copper screw that very little friction there, and that point at the bottom has also a little friction, so it can spin pretty easily. And we're able to get that up to about the 25,000 feet range when testing the vacuum chamber, but it couldn't make it all the way to space. So maybe with higher voltages or different design, we might be able to get that to work in the future. But up to other scientists, researchers to keep studying that. And of course, we'll keep looking into it too.
Awesome. Awesome. Guys, thank you. Thank you.
Mm-hmm.
That is tremendous. Absolutely tremendous. Well, let me see. Does anybody else have lab updates, or do you guys want to go to open discussion?
Assuming.
Oh, there's Michael. Michael, Michael, you have returned. Okay. Do you have a light you can turn on?
It's the camera itself is just really bad dynamic range, but we'll make do for now, assuming that it doesn't freeze again. Anyway, so we were looking at LK99. We got some really nice SEM photos to present at some point in the future once we're done with all this and we've wrapped it up. But basically, the crystals form in these long angular structures, and then there's a plane inside the crystal where along this axis, it likes to phase separate into a lead concentrated region and a copper concentrated region. So we figured that maybe annealing this stuff in a furnace was not optimal because it would prefer to go to this lower energy state. And then afterwards, we heard that the Korean team claimed if you took this material and then vapor deposited it, then you would get something that actually superconducts. So I assume you need to get the copper and the lead mixed, and when you heat it up, that goes away. It diffuses out, and it forms these separate layers, which is a lower energy state. So the other cool thing about these crystals is if you have any traces of nickel or iron, they'll tend to phase separate into the copper concentrated regions as well. So you get this really anisotropic magnetic permeability. It's diamagnetic along one direction, and it's paramagnetic along the other direction. And that's why we saw the behavior where these particles were spinning with the magnet, but not necessarily being attracted to it, because on average, the permeability, the magnetic permeability was near zero, but because of this anisotropy, it was still it still preferred to be aligned with the magnet. So that was interesting. That could also explain some of the LK99 stuff, especially where it wasn't fully levitating. It could have a non-trivial plane of minimal magnetic susceptibility. But anyway, that's the idea. What was I doing aside from that? Oh yeah, so I mean, I guess I just had, if Charles is here, I had a question for him. I caught up on most of the presentations from earlier. I was in the lab making another LK99 sample. So
yeah, why don't we put it? Yeah, we'll put it back on. We could put it on the grid layout there. Yeah, go for it, Michael.
Thank you. Hi, Charles. Awesome stuff. So I think based on what you were saying there at one point, if you have a Casimir effect, is that actually reducing the effective pressure at the needle tip? So
No, the Casimir effect doesn't play much of a role in the macroscopic world. That's a microscopic quantum effect.
Well, yeah, but if you made, oh, sorry, go ahead.
I think it doesn't much on the what we're doing. We're overloading that.
Well, what I was thinking is if you have these plates spaced very closely together so that the needle tip is approaching the surface, then you'll have a region of Casimir affected like vacuum at the tip, and then the sides won't be affected as much. So if that in any way affects the electrostatic pressure applied to that surface, that might be useful.
I don't know about the Casimir effect, but the electrostatic pressure at the needle is small because the needle's doesn't have much area. It's got a huge E field, but it's got many components of the E field, right? They're in all directions except for where the needle is.
All right.
It's hard to contribute to the overall force, the needle tip.
My impression was that something fundamentally new and unique was happening. That's what you guys discovered.
Well, yeah, I mean the electrostatic pressure itself is acting on charges, right? Two types of charges in everything, and they're everywhere. And at the quantum mechanical level, that's not allowed to be zero, right? So that operates on everything. So
this is
what we do
this is affecting.
Sorry,
go ahead.
No, I'm just saying we just expound upon. We just make our own pressure. It's much higher than the vacuum level.
So this is it's affecting dielectrics differently than metals, then?
Well, metals have free charge, so free charge pays the price, the alpha price, the fine structure price, because those charges are allowed to move. Dielectrics that are charged, where the charges are slow or almost slow, like wood, like you just showed Charles. Hi, Charles. Nice to see you again. Did a nice wood experiment. Wood, fiberglass, G10, like the, what's his name, David Perez's experiment. Those materials are kind of at the 10 to the 11, 10 to the 12th range in resistivity, which means they can get charge in there. But if you're fast enough with your field, you can switch it out, but the charge is kind of stuck in place. Not quite an insulator, not quite a conductor. So you get that huge range of 10 to the 4th, to 10 to the 12th, 10 to the 11th ohm per meter resistivity. So that's kind of the magic sauce there. So
what about Rochelle salt potentially? Oops. What about Rochelle salt? Jeremiah was having the exact same idea. Clearly, yeah, it's got some conductivity to it because of all the. It's a hydrate basically, so you've got a lot of water in there. So you got some proton conductivity, probably. You've got some electron conductivity.
Absolutely, proton conductivity, electron conductivity. These are all highly function of humidity in vacuum state.
Ooh, nice crystal. There's some nice Rochelle salt crystals there. He's been getting very good at growing those.
Conductivity is good; it makes things easy. But you want the big forces, you got to go to the charged dielectrics.
Charged. So you want a dielectric with charge trapped in it. What about like if you have like a diamond or piece of boron nitride and you hit it with an electron beam, so you get
into electrics,
megavolts.
Right? So you get to electric. Now you got charge stuck in there. Okay. Now if you set up your fields properly, once you do that, just don't send that into space. It'll piss the aliens off.
That's all right.
You got no way of discharging that.
Mark can ask about that earlier. Mark had asked. Mark, you were asking about electrets earlier, right?
Yeah, and that's an
Yeah,
electret.
me
That's
and
the
Jeremiah
bar.
made some electrets.
You don't want to go in the electret world. You want to stay in the wood, the fiberglass. Or you want to stay in that range or the conductive range. You can go to the insulator part, but you better be sure that you can turn it off or switch the field to do something else to slow you down at some point.
I
I don't know. I
recall
can't prove that yet until we put that in space, but that's that's what the
two
data on
more
Earth is showing me.
two more brief things. I recall in Russia they were doing this thing where they take graphite in an explosion vessel and they electrostatically charge it, and then they blast it into diamond powder. So it goes through this conducting to insulating transition, and you can load up charge into these like microdiamonds really, really effectively. And because of that charge, they have a large zeta potential effectively. So they're very useful for drug delivery and stuff like that. You can attach molecules to them, and they're stable and they're non-reactive. So they just pass out of the body. But yeah, charged nanodiamonds. I don't know if that particular one's useful to you, but that's an interesting way. There's ways of getting charge on these things. One other thing is we're for our own high voltage experiments. I've been working on a boron nitride clay sort of thing, or actually, in your case, since you're going for thin layers, maybe would you be interested in a spin coating that'll coat stuff in boron nitride, or is it just the middle dielectrics that like the somewhat conductive materials that are more interesting?
Well, depends what we're using it for.
Hmm.
Some dielectrics, accept holes, some accept electrons. It's all about the charge density, how you get it in there, what's the mass of that layer. We're looking at everything. Like, so we test. Drew, who's here, tests everything, and it's like a train coming at you at 100 miles an hour. So we're just we're testing just about anything. We know what we need. We know what we want. We know the tests that are coming out 3 months from now.
Awesome.
So we're happy to get input. We'll try other things if people have other ideas. The physics hasn't let us down yet. Hasn't let us down yet. So we're just going to keep barreling on this train until we're told it's
Very
not
nice.
Just in case.
My last question was actually, I think my last question was, have you taken a look at T. Townsend Brown's original papers? His family apparently put them up on a website. Jeremiah mentioned it a couple of weeks ago.
Not too many.
They
I mean, a lot of that stuff is 150,000 volts, huge voltages. Voltage is not the answer. It's field. So you can get the same fields with 10 volts as you can with 1,000,000 volts if you set up your fields correctly. Field is what gives us our force, not voltage. I don't like it. We started when you and I started. We were doing 150,000 volts. It scared the crap out of me. But I had my Crocroft-Walton voltage multiplier, my 110,000 volt stop stick.
That's a lot of heavy power equipment that you have to carry along.
I wanted
with
to get
your
away
motor.
from that as fast as possible. So
okay.
And I don't need it. But I understand in the 1920s and 30s, some of that stuff had huge voltages, and I appreciate that. That's awesome.
Well, that greatly simplifies the design of these systems if you can just power it off 10 volts, because then you can just have a tiny little power supply.
Eventually we're aiming for what Drew and I are aiming for is what we saw, what I saw at least. I think it was on Ancient Aliens, one of these TV shows with Travis, what's his name?
Travis Taylor.
Travis, that guy. But he had the material, they put 15 volts on the sheet and it lifted up. That's what we're aiming for. So
nice.
That's what we're aiming for. 15 volts, 20 volts. And that's the goal, that's the aim. Let's see how light we can make this. It's not the easiest thing to do. Obviously we would do it if we knew the answer, but we're getting close. We have chemists now working with us. So chemists, they know a lot more shit than I do physics. I give them all the physics. They have to do the chemists. They have to tell us what to do.
That's nice.
You know what? Michael is one of those. Michael is one of those people. He's a materials guy, so he may be able to help.
Like they got it all. Okay.
Anyway,
I'll be willing to
just
collaborate.
hang on 1 second. If anybody's got a little iron phosphate, just a couple of grams of it, I would be very indebted to you because they won't sell the stuff to me.
I wouldn't sell you.
That's weird, but iron phosphate's easy to make. Why not just take like iron oxide and dip it in phosphoric acid and just let it sit for a while? It's easy.
Because I don't know how to do that. Could you write down what that is? That a is there a thing on the web somewhere that shows you how to make iron phosphate?
I'm sure there is a chemistry YouTuber who has done it.
Okay.
Anyway, I could send you guys instructions. That's very simple to make with like local materials.
Yeah, please include me on that list of who you're sending instructions to. I'd also very much like to make that. Thanks.
Okay.
Yeah.
So what's so special about iron phosphate?
I don't know. I don't have any to play with yet.
Interesting.
But my battery genius said, "Go find some."
Oh, okay, that makes sense. Oh, you know that's wait, Drew, that's just. Are you talking about like the material for lithium-ion batteries? Because lipo batteries, like lithium, that's lithium polymer, really.
It's
But
before the lithium part of a lithium
Yeah.
iron phosphate battery.
Yeah. So like, I guess everyone's just using that for.
Well, you
lithium
could just go ahead and
you can
buy a
make
couple
that.
of cells and take them apart and salvage it straight out of the cells.
Yeah, that's true. You could just rip apart a lithium battery carefully so it doesn't explode. But yeah.
Yeah, I don't want to do
You like
that.
doing that, Drew? Taking parts of batteries?
No, I don't. No. And the crazy thing is, this stuff is actually available at the hardware store in the form of
know.
snail killer.
I know,
But
right?
it's got all kinds of other things in there, and I don't want the other things, so I wanted to spend the $40 and buy 10 grams of it, and
That
they
seems
will not
overpriced.
sell it to me.
It's probably on the DEA list or something for drug-related stuff.
Well, so
Whatever.
let's just do we'll schedule a real science episode together, everyone in their own labs that wants to participate and make the stuff. We'll just do a recording where we go through it and we'll all make it together, and then we'll all have our exact samples to test and play with.
Oh, Charles, one more thing. Try zeolites. Zeolites and molecular metal organic frameworks. Those might be interesting with their porosity. Worth a shot.
Zeolites. I'll write it down.
Trivial, guys.
Sure.
Yeah, zeolites and metal organic frameworks. MOFs.
Yeah, and it's interesting you mentioned porosity because one of the things with the Mach effect drive that we found with the discs, the piezoelectrics that work better, are the ones that actually have a bunch of voids in them, versus the higher quality actually produce less thrust.
Interesting.
So now you're getting charge embedded. So now you're adding more force unknowingly because you're actually
Direct correlation to surface area. Charge migration and tunneling is far easier with the added area. That was the same thing that Mike McCulloch was working on too with the Kapton type 6 micrometers. And that was following the Becker and Batt papers, which were referenced earlier, which you finally brought that stuff up too. And Ben Dirk also referenced it in his works, and he explains the complex geometrically amplified relativistic field. And all of this starts to come together because we now have a complete, I would say, amongst us, not individually any of us, but amongst all of us, we have a complete framework to literally build a flying saucer at this point. And today pretty much proved that point. I did want to mention two things. One of them to you, Jared, first off, which in that low vacuum arc video, you clearly demonstrated the formation of charge clusters at the surface with those little bright blinking spots. And then we had a major arc breakdown, which is basically exactly how you get a gamma ray burst being emitted off of a sphere. So if you follow the Vega reactor and then you take a look at some of these other fusion projects, you guys had achieved that at ultra low vacuum. But for the first time ever, you showed that there was actually a scale directly correlated to achieving these phenomena. And now we finally have an idea just how hard of a vacuum you need to pull to get to the breaking point where the acceleration potential is sufficient to produce vacuum clusters. So that was awesome. The second thing I wanted to mention is Michael, brilliant idea with spin coating. And that particular material is capable of withholding probably the highest temperature of individual electron impact. So at the fastest velocity, that particular material is one of the few things, boron nitride, that can actually withstand that type of bombardment, meaning that if you wanted to use it as a barrier to some dielectric where you had electrons drifting into it, and you had something that had a really high capacity, maybe it could break down if there was current flow, you could use a spin coating on that dielectric of the boron nitride to specifically stop charge migration and prevent the material from ever catastrophically breaking down. So you could basically build an ultra high density thruster like Charles, like Drew are doing, and you could get even higher energy density than they're getting out of their polymer films. So
well, guys, I think we've kind of lapsed into open discussion. We should just officially call this open discussion now. So
sounds good.
Open discussion.
Open discussion. Yeah, but let me
open
thank everyone. Thank you all. Today was this may have been our best APEC conference ever. Thank you, each and every one of you.
Thank you.
I am not hamming it up. I genuinely mean that.
And thanks, Dan, for your mathematics knowledge. I need to still read through that, and
I got a question that's been kind of burning at me.
I think between the three experimental things that we had going on today, we have Buhler and Drew with some sort of thruster. We had David Perez with what seemed like a tractor beam of sorts. And over here at Falcon, we have an inertial cancellation device. With all those three, we basically have everything we need to make, a shuttlecraft and mine asteroids with it.
And in addition to that, we also have the discovery of magnetic pressure and its utilization. We've tested it in 3 different experiments now. It's a tangible, very real thing, and you can use different elements like iron, for example, to dramatically increase the field forces at extremely low frequencies because the refractive index of those materials is so high. So we've tested that. We've tested time differential fields. We seem to have figured out exactly where we're taking the value A in the J curl tensor, and we're shifting it from one area to another. So it basically demonstrates that there's a finite amount of magnetic permeability that you can have, and if you take it from one area, you basically add it to another, and vice versa. If you add it to one space, you have to take it away from the outside area. So if you cram 2 spaces where you're taking it from both sides, and you're basically squeezing it in on both sides, the area between these, like where my 2 thumbs are, that vacuum variable gets sucked out of the region inside, and so time actually flows faster along the linear axes through that space. And this is also something we tested now, and we've got clocks to indicate that it's highly functional and reproducible.
So I have a question that kind of builds into that, what you were saying about like the time differences and stuff. So it seems like you guys are doing a lot with like trying to get noticeable force off different things. There's going to be another side and thing that has to do with this warp drive thing is detecting, gravitational fields, because ultimately that's what warp drive is about, right? And I've had this idea stuck in my head for a while now, Ned. Most people talk about using interferometers on like a tabletop setup for detecting small scale warp fields. Interferometers can have a lot of issues, in terms of like sensitivity and stuff. And if you guys have any answers to this question, is there any reason that we have to use an interferometer? Like, could we use like an atomic clock and measure the time dilation from a an artificial gravitational field as
technically an atomic clock? Technically, an atomic clock is still sort of an interferometer. The way that it works, if you look at how the atomic clock is working on the inside, you've got a whole bunch of RF signals bouncing around inside there, and you've got a collector, and it's using like what, strontium or something? It's using an NMR thing, and it's basically using the fine structure constant. You're using your Zeeman effect, and you're getting data from that using radio frequencies instead of optical light. You can do that optically. That's basically, you can see the Zeeman lines at least optically. And that's one thing Todd's trying to do actually is he's got this interferometer where we're actually just trying to directly measure the Zeeman lines of bismuth nanoparticles, because bismuth has a very large spread of Zeeman lines to begin with. And then when you have nanoparticles, that produces a large nonlinear Zeeman effect, which can potentially be noticeable in different gravitational fields. Like the Zeeman lines will not be affected linearly with the amount of gravity applied, so they'll shift relative to what you would expect. Anyway, at the end of the day, all ways of detecting this stuff seem to be analogous to the LIGO detector in some way. Like, for example, in this setup with the bismuth nanoparticles, you still need squeezed optical light to have enough sensitivity to detect anything.
I just want to toss out that when you're talking about interferometers, there's lots of different kinds out there. I played around with the Bath interferometer, a highly modified version that we were using to do check telescope mirrors, and the Bath interferometer is bulletproof because it uses its own light path. It doubles them back. It is way better than trying to set up any of the other ones. So if you're looking to build your own little toy interferometer, like it looked like somebody just did, if you look into the Bath, BATH, and don't use the one with the internal prism, use the one with the split mirror, the beam splitter, and the secondary mirror. It's way more forgiving. Way.
Well, what about the one that they made at NASA, the White Jude interferometer or whatever it was?
Yeah.
Isn't that like a scaled down LIGO?
What I just showed you guys,
Sunny White.
This is basically the White Jude interferometer. This is just a single balance EPL. And so what I was showing earlier on camera, I'll just flip it on. What's really cool about this type of platform is that one, it's made of insulating materials, so I can expose it to electromagnetic radiation without having to worry too much about the antenna physics of how it's being affected by the ground plane. And so each
technically dielectrics are still interacting with that. But anyway, go ahead.
Absolutely, and you're absolutely right. This is entirely a function of frequency, so you have to account for what kind of excitation you're actually putting into the platform and make sure that it's not within the heating range or inducing any currents into the dielectric or moving free charges. So acrylic is one of those things that's kind of a pain because it does contain free charges, but we account for that in terms of the platform mounting. So what's really cool about this thing is that basically it's this entirely portable battery operated platform, and I'll pull this back and once again show the beam paths here with this little fog machine. You can kind of see where your XY cross is. What's nice about this is I can place a sample here in that direct area right here in this beam path and be completely isolated from the optics and the elements, and then it expands using that little beam expander round lens right there, and it hits this projection screen, which gives you a live display. Very useful.
I thought that the White Jude interferometer used squeezed states. It doesn't have a balanced homodyne detector, or
the White Jude interferometer is very much like the Michelson-Morley interferometer, except for it has a bent beam path. But if you take a look at the diagrams, it's basically what it is. I've just added one more bend so that I can get a projection display instead of having to go into a detector. So that's about the only. Well,
I just want to. I want an interferometer that's a tabletop, inexpensive setup that uses squeeze states. We need this.
Then all we have to do is add on the X or the Y axes a field compression device, and we can just use a couple of polarizers to generate the ideal interaction, and then we'll have to add our magnetic element.
Well, you need balanced homodyne detection for the readout, ideally, and then you need some means of generating squeeze states. So you need some oscillators driven at twice their resonant frequency. Anyway, this is all stuff. I should probably
answer Dan's question though, and like complete his question.
Go ahead. Yes.
Can we use any detection mechanism or method? Yes. The answer is we've found over 7 different detection mechanisms and methods that are all equally valid and basically are detecting the exact same thing, whether it be the speed of a photon beam through a specific area over a unit volume, Cartesian coordinate wise, or whether we consider a 3-dimensional time and we're basically looking for differential clocks. We can consider it in forms of the field gradient, like Todd Desiato's work, which talks about the warp drive phenomena directly correlating with field gradients and the variable gauge factors of E naught, mu naught. I mean, there's a lot of ways to approach this, but basically we can use many different detection mechanisms from clocks to light to even mechanical oscillators. And actually we found that we can even use the spring constant as a detection mechanism compared from one frame to the other. So say you had a spring inside this field, but you had a string attached to that spring that was measuring how much that spring was pulling outside the field. Well, through the information horizon, the tension force on that spring would actually indicate that the spring constant changes for the spring inside the internal temporally modified field. So
I would like to mention I would like to also mention Ray Chiao and Jack Safadi are investigating this idea of using two yttrium iron garnet spheres that are entangled. So if you're familiar with yttrium iron garnet, you can optically you can pump Yig spheres with RF frequencies, and they can form a magnon condensate at room temperature. So then you have these two macroscopic quantum objects with a spin according to and then as the gravitational field comes along, it adjusts how this quadrupole is affected. So you get some entanglement difference introduced by the gravitational wave signature. So that's what they're looking at, and that sort of system can detect gravity waves all the way up into the radio frequency signals. And I recently actually found a paper, and Jack was saying it's ridiculous, but basically what the paper was saying was if you apply squeezed vacuum states to these two Yig spheres, you can actually induce similar changes in the quantum entanglement between them. So that would suggest that squeezed vacuum states are indeed gravitons, which is it's a little bit sad for communication, because that means high frequency gravity will still interact with matter to an extent, and that's a hypothesis we can definitely test a lot. Once you can generate high frequency gravity, you can generate squeeze states, but you still have to prove that those are gravity. Anyway, there's lots of ideas floating around. I would just, Dan, if you haven't seen, maybe we can, maybe email me, and I can at some point pull up all of the best APEC stuff that was done on that topic, and compile a list.
So then I got another
I'd also
question
ask you
for
to include
Jared.
me in that list too, Michael. Thank you.
So I got
Sounds
another
good.
question for Jared. With his setup, you said you were basing a bit of your stuff on, like, you mentioned T. Townsend Brown, right? And as Mr. Buhler said, the kind of voltages Brown was playing with in order to get vacuum effects were fucking stupid. I think it was I believe, if memory serves correct, I'm pretty sure it was like 210 kilo electron volts. So over 200,000 volts for just to get those kind of effects, which is really dangerous to do.
Well, now you're to field emission too, so you're going to see a lot of other effects show up.
Yep, for sure. So what I'm curious about, Jared, is like what kind of voltages were you playing with in your setup there?
Before I tell you the voltages, it's important to note that for T.T. Brown's work, initially it was the high voltages, but he soon figured out that it was actually the dielectric constant had a far greater impact on the amount of thrust than the voltage.
Yeah, so and he was playing with both fluid dielectrics and solid dielectrics.
Yep, and
It's
as
the fluid
he,
ions, but yeah,
as he,
guys.
And I just
go
wanted
ahead,
to mention real quick, though, that in addition to the solid dielectrics, it's extremely important to understand that Brown utilized high mass materials, including litharge and other metalloids, in fine particle form, where he added them into the dielectrics in order to increase the mass density, so that basically the permeability of that space be modified along with its permeativity as you have the transition wave traveling through the distance of the dielectric. In his patents, he specifically chose you that the density of the metalloid particles that are added to the dielectric are concentrated towards the anode side. And this is intentional in order to create a gradient field in that dielectric material, pretty much exactly like what Drew has already demonstrated and proven now and what you're talking about. So Brown had this figured out, and he found a specific set of materials that worked really well. One of them was tungsten carbide. Another one was he used tantalum. That was a popular one. I mentioned this earlier, but he also found that certain elements in bentonite clay already contain ideal ratios for gravitational and inertial isotopes that he added into what he called a lofting cake in order to produce the maximum gradient thrust. So this has all been around for a while. So if you're wondering if T.T. Brown is relevant to what you guys are doing, it absolutely is, and you've got to read those family notebooks. But last thing I wanted to mention, voltage is not a problem. This is 130,000 volts. It's handheld, only draws about 8 watts. And, basically no problem here. At the tip, you can put an isolation terminal on here and bring it all the way up to the point where it's producing 6-inch sparks right out of this. This will levitate a feather. This will screw with the chirality of materials, and you can do all kinds of fun stuff with just a handheld voltage multiplier. So it's not like we need a lot of power or massive equipment to do this kind of stuff. It can be done on board. And Ethan Krause and I have talked many times, as he's the first person ever to have a completely self-powered or power supply on board ion lithium mechanism. And we've spent many hours over the phone talking about miniaturization of this technology to the point where it's gotten mind blowing. I've done 40 watts with a 7.5 gram power supply. So, and that's at 65,000 volts pulse with a maximum burst rate of 40 kilohertz. So,
this might be a really bad analogy, but sometimes part of me wonders if the Pice effect is just almost like MHD on steroids.
If you bring MHD down to the Planck scale, then yes.
Okay.
But it does go down to that Planck scale ladder. So we basically have like these two extremes. We have one, the Planck energy density at that scale, which is your positronium, your particle pairs that can be broken out with sufficient amounts of voltage, 1022 kiloelectron volts. And then on the extreme other side of that, you have the Schwinger limit, which sets the upper boundaries of how much energy density can be in space before space comes apart. So between these two, you have your entire sliding scale of how much energy you need to put in to screw with that space to the point where it's literally not space anymore, but it becomes the physical particles it's made of. And so with that in mind, we can now engineer warp drives, and we can basically take the particles out of the physical space. We can move them to the back of our craft and recombine them. And so we're sucking the space out. It's physically contracting in front of us, and we're adding it.
Like cavitating the vacuum.
Right, but we have a mechanism of action now. We understand this is physical particle separation. It's happening at the Planck scale. It's happening because we've exceeded the Schwinger limit, and we now have a full mechanism for warp drive, and why we, just like in Star Trek, need our positron electron beams to run parallel all the way to the back of the craft where they are recombined, not annihilated, but recombined. They re-enter that physical space-time in the cosmic lattice at the Planck structure. So it's interesting to think about the whole entire orchestration of how these things come together. Everything from the magnetic moment of these pseudo monopoles and what Bob Greenyer was talking about, right up to the point where we're talking about electric field gradients and gradient field engines.
Yeah, so I wanted to mention just real quick for the Mach effect, the lab, we had an issue with our turbo pump that failed. We have a new turbo pump in, but with the holidays, I haven't been able to come in and go in and set that up, but that's going to should be up and running next week. So hopefully next time we can give an update as to what the experiment's going through. Also the null device, the null drive, which has equal masses on either side, is something that is getting repaired, and so that's going to be run. And initially it looked like it was working okay, but it was built slightly differently, and I kind of brought that up. So Jim has gone ahead and put constructed it similarly to the other devices, so that we, skeptics won't have to point that out as well. Yeah, the other thing I wanted to say is, in terms of this, the whole idea of, a lot of different theories kind of pointing at the same effect. That's good, but one of the things I'm kind of curious about is, if we're talking about new physics, how do you prove that, right? First of all, you got to have an idea of what it is and what the different theories would predict, right, logically. So and the reason I bring this up is that there's so many different aspects to what is being seen empirically. Let's say these experiments are replicable, and we can repeat them, and you can get the same effects. We really do need to I think we need to have some kind of a matrix of different theories and the different predictions, and kind of narrow it down, because from my point of view, like I said, when I first got on here, is my motivation is the physics initially. I'm excited about all the applications, and the applications could be as far reaching as the linear stuff, right? What we're talking about here is very fundamental to how the universe works. And if for example, if Sachs is right, or if gravity is really emerges from quantum mechanics, or quantum mechanics emerges from gravity, those are two very different paths. And I know there could be at a high level a lot of categorical type equivalencies, but what we want is something with predictive power, right? So it's a little bit more what I'm looking for personally in terms of like the way I do physics, is I'm looking for, okay, this theory ABC, okay, here are the predictions, here what we see, it's more likely that this is coming out, right? And so all that being said, I'm lately, what I've been trying to think about is what kind of physics can we point out that, okay, this would be a big difference and something fundamental that is not there classically, and can we narrow down an experiment, just do a raw physics experiment to prove that that's there? So if we're talking about a particle antiparticle pairs that are an existing kind of gaseous state versus the vacuum, or the traditional quantum vacuum, what is the differences in those? And how can we differentiate
I may be able to add some light to that. The difference is we are going to predict our three main variables. We're going to have angular momentum, we're going to have spin precession, and then we're going to have the net energy density. So with those three things together, we understand that each nodal point with positron electron pair known as positronium, which is shrunk down to its finest scale, where the electron and the positron, they never quite touch, but they get as close as they possibly can up to the information horizon at the boundary layer of how far they reach out to the next set of particles. So if you imagine an entire lattice structure, a matrix of positronium particle pairs, then each one has its own boundary or its bubble, and each of those has a physical size comparison to some other point in space that's far away from it, say some point in space in the gravitational field surrounded by matter, which directly affects it. So if we're talking about antimatter and how to physically utilize it, we can test it because we would look for these other properties that we wouldn't expect to simply be there from the vacuum conditions alone. And then we would expect that the variables would be completely modified if we start splitting these pairs out of that vacuum space and then allowing them to transit as physical matter to another location when they're recombined. That we would expect a physical delay of clocks. We would expect a tremendous difference in the velocity of light through that region, and we would expect a gradient field compression that would also show up in terms of detectors for where the gamma rays are emitted. Here's the greatest part about the positron electron positronium warp drive. When you add 1022 kiloelectron volts to separate your particle pairs out of the vacuum, and you take them all the way from the front of your ship to the back of your ship, and you recombine them, they give you back 1022 kiloelectron volts. So, you get to recycle your energy if you can realistically capture the gamma rays. And basically what this means is once you get the system ramped up and you've added whatever energy it takes to generate, a warp point factor, that you get to continuously recycle that energy over and over again. So you just got to build it up or tear it down, but you don't have to sustain it if you have high efficiency for conversion. Sorry, I don't know if that answered your question a lot. I know it was probably a lot.
Yeah, well, that is that would be an ideal in terms of usage of the effect. But getting down in the weeds of it, what is a good experiment that we can do that's replicable, that differentiates and maybe says, hey, yeah, there's a background pair gas, and that's the right physics, and we're going to fundamentals, right? And with physicists, going to fundamentals is really tough, right? Because we're so trained with the math, it's just
I agree. I hear you, Curtis, man. I agree with you completely. I mean, that's why I try to make my experiment as simple as possible, as dumb as possible.
Yeah.
Voltage,
So for me, the question is, what are we fundamentally showing that's in advance? And that's why I like Sachs's work, and in terms of potentially explaining what's going on here, because what he did is he said, okay, well, Einstein had included, time and space symmetries in the field equations for general relativity. When you remove that, you get 16 equations instead. And then lo and behold, you can have a nonlinear, when you take the Dirac equation and you make it covariant with that field theory, that relativistic field theory, you get a nonlinear field matter field theory that recovers quantum mechanics. And so that is like a, it's a statement that includes, so basically quantum mechanics is recovered. It's not throwing it under the bus. Just like anything that does, a lot of the times, like 99.9% of the times, people are taking quantum mechanics and they're trying to develop relativity out of it. But they're not changing relativity, right? The predictions are recovered. If it's the opposite, what is it? What's different about that theory is that the field theory in Sachs's work is a classical field theory for matter, and it has that background pair gas in the back, and that's where the Mach effect comes in, right? So there's a mechanism there for this. It connects the mechanism for matter, which is the Mach effect, to the fact that it's a background pair gas, and
Right.
that
May I? I think I have an actual answer for your question, and we could use as a definitive experiment to check for this. We could use either cobalt-60 or sodium-22, both viable isotopes that generate plenty of positrons, and we could measure when those positrons are recombined with the source of electrons that we provide in our experiment, that in the region where we combine the positrons and the electrons to form positronium pairs, that if we pass a beam of light through that region, or if we use a clock that's directly associated with that region far away from another precision clock that's outside the information horizon, we will see a change in both those things. One, the velocity of light, two, the speed of the clock. That's directly affected. These would be make or break experiments that we would see when we combine positron electron pairs and they re-enter the lattice. It would have a direct effect in inflating the space, and we would expect a faster velocity of light through that same region. Or sorry, no, slower velocity of light through that same region. Thanks.
How are you keeping the positronium from decaying?
It does decay down into the finest scale, and it re-enters the Planck scale lattice.
Yeah, positronium decays into 2,511 photons.
Right. Well, it gives them back up, but actually the particles don't go away. They technically annihilate because they recombine and they get back the energy that it took to separate them out. But they still exist and they reinflate that space.
So I think that's the key difference here, is that the question is there a matter field background that is there, and can we test for that? So that's it's Dan and Charles, I don't know if you've heard of this before. This, like I said, this something I covered in my talk back in October, but it is basically a big question, because if that is really the case, then a lot of the effects that we're seeing here are kind of like very apparent results of that. So yeah, I'd love to hear. I'm sure you would need to go, listen to the talk and maybe come back to me. But I'd really like to know what you guys think of it.
Sure, I'm sure Tim can help me.
I'd really like to talk with you privately at some point too, Curtis, because I really like the approach that you're taking, and I would love to try and combine our experimental data and the things that we've learned with what you're attempting to do and bring this all together. So if you want to work together, let's by all means do exactly that.
Yeah. Oh yeah, definitely. I'm open. I'm looking for people to collaborate with and talk with about this. It's, like I said, and last time I've been, at this for maybe 20 years now or more, like trying to understand, okay, why is it that that Sachs is just like set aside and ignored? I kind of get it. It's being such a nonlinear theory, it's really difficult to make predictions. And if it really is what is really going on, it's not as fun as the many worlds or the the black holes. And by the way, I wanted to mention, you guys are, I don't know if you guys are familiar, one of the name solutions to Einstein's equation is the Kerr metric, which has to do with a rotating black hole, right? Well, Kerr recently came out with a paper where he kind of showed that the whole idea of singularities inside a black holes is not needed. And so this kind of like really put in question Penrose and Hawking's work, where they made an argument for a singularity at the center of a black hole. It's a very interesting paper. I put it in the chat earlier. But in there, I mean, he has some quotes. It's a really great paper. I highly suggest anybody technical interested in that. The earlier presenter, I think he's gone now, but it's really great that that he went and did this. And there's some quotes in there, like he even quotes Einstein. He says Einstein once said, "General relativity is about forces, not geometry." And he says that may be a simplification, but it's a useful one. Anyway, so yeah, I would highly recommend reading that. I know it's not directly applicable, but when thinking about relativity and what we're getting here, the fact that Sachs was able to basically, just so you got Charles and Dan, just so I could, you guys can kind of see what I'm going with this. But if you're familiar with the Dirac equations and how the Dirac equations are a factorization of the initial Klein-Gordon equations, right? Basically, what Sachs did is he took Einstein's field equations and he was able to factorize them the same way. So by taking just like a Dirac used spinors, right? So Sachs used quaternions. Anyway, so you end up with 16 equations, so full covariance with time and space included. Reflection symmetries are not there, and which is what we find in nature is that is not a symmetry that actually exists in nature. So it's really I never, at least in terms of like the relativity, the problem with relativity being what it is, I think that's an advance by itself, but there's more consequences, which is what we're discussing here.
Just
Go ahead, Dan.
I'm just curious as to what everyone's take is. We don't need to get into a big debate on it right now. Just like, how many of you guys have entertained Everettian interpretation of quantum mechanics? Is that something you guys have played with much or no?
Could you say that again? I couldn't hear you.
The Everettian approach to quantum mechanics instead of Copenhagen?
I have looked at a lot of different approaches, and I somewhat consider Sachs's thing like a different approach, because it's almost like saying that, okay, well, there's a a strict field theory there, and can we recover it? So I have looked at years ago. I looked at a bunch of different interpretations, and I am in agreement that Copenhagen seems to not be enough, especially with what happened with Bell, and the EPR stuff. There's more going on. That's how I feel.
I just wanted to mention too, same as I told Curtis, Charles, you are so sharp that it makes me feel dumb. So it's a delightful experience to have somebody that knows and can eloquently deliver the things that they've learned. I would love, if you can find the time, that we might be able to speak on the phone at some point in the near future. Your brain is overflowing with information, and your presentation clearly shows it. I would really like the opportunity, if you're willing, and if you can make time for us to have a private call.
Talking to me?
Yeah, you.
Okay. No problem. No, I enjoyed it, guys. Thank you.
Thank you.
Yeah, just while I got Tim here and everyone, just a quick wrap up to do. A couple thanks. And last night we had Bob Greenier on with Jeremy Reese, myself, Dave Rossi, Ashton Forbes, Michael Perrone came on for a bit. It was really good, and looking forward to having Bob Greenier on again. last night. We couldn't get John Hutchinson, had some prior engagements, but I've been talking with John, and thankfully he's been recovering from some health issues, but he's getting better and should be able to have him on in the next year to talk some more on his stuff. And Tim, I'll be in touch with you sort of to try to correspond to plan that together.
Thanks, Bernie. Now, Bernie, I should
that's all
mention.
right.
Oh, sorry, Bernie. Your channel is, and we are live casting on your channel, but we're on a couple of other channels as well. You might consider dropping a link in to your YouTube channel. That way, folks don't miss it who are listening on, Alien Scientist or on the Alt Propulsion channel or Facebook. I mean, we're all over the place.
Or,
So.
Oh, exactly, right. And I'll help you get it live on the next one. We can also get on LinkedIn as well as of course X, former Twitter, and then usually Rumble, and now Instagram as well. So we can bring APEC to Instagram and take it to the whole new generation of people, right? And
we'll have to start putting up selfies, though. We'll have to start. We'll that'll be interesting. But hey, we got Christmas hats,
I
right?
still have the worst picture ever up on the APEC official website, all propulsion. So I got to fix that. You're right.
Well, and then
I gotta get going. You guys have a good holiday. Happy Christmas. Have a good one.
Well, Curtis, thank you.
Yeah, hopefully we can have another technical discussion soon. I'd really like that.
Yeah, it's absolutely wonderful. Yeah, and it's been, guys, we've been going for like 5.5 hours here. You guys run me into the ground. It's like the Baton Death March of science conferences. So
yeah, definitely probably time to wrap it up. Let everybody get to their families and enjoy the rest of the holidays and start again year 4 in the new year, I guess, right?
Let me thank everyone. I mean, Charlie, Drew, Dan, Andrew presented, David Paris. I mean, what you guys, this is probably our best conference ever. It's just breakthrough after breakthrough after brilliant idea. So
Yes, absolutely. This is an epic historical conference today.
Yeah, I'm stunned. I'm literally stunned in a good way. Just stunned. So thank you guys.
It's all about the hats, Tim. We ought to just implement a hat for each conference. Just we'll do elf hats, and we'll do Santa hats,
tinfoil hats,
fedoras. Maybe the really cool fedoras.
I love that.
We could do
wizard hat.
St. Patrick's Day. We could do the leprechaun hats.
Leprechaun hats. Okay.
Pirate hats.
Harry Potter hats. I'm sure there's something in the Harry Potter theme world.
Yeah. So
all right.
Okay.
We'll do little tinfoil hats. Have a I want to believe night.
Well, how about this?
I just want to mention that y'all, I just sit and listen to the physics discussions, and I'm thinking, where in any of this is something for me to build? Y'all got to figure out, attach this to this, and then go, because this babble that y'all come up with, I'm sure it's incredibly important and insanely interesting, but I don't understand any of it. You got to break it down to the idiot level.
Drew, it's collaborative, and that's the thing that excites me. It's the strengths of one person feed into the strengths of another person, and then together we can accomplish more than any one person can, right? And that's something where, when it comes to warp drives, you've got, again, like NASA's breakthrough propulsion, and you had the STAFE, the SPCIF, the HFGW conferences. You had a lot of those folks that were working independently all the time. They were only able to connect periodically or through email. And so my hope is that like APEC as something that brings people together more closely, we're able to foster better collaboration, right? And that just moves everything forward. It's the rising tide that lifts all ships. That's my hope.
And I really do appreciate you taking a gamble on me too.
No, Dan, you're wonderful. You know this stuff left, right, and center. It's amazing.
You explained warp drives today in a way that I had never heard or even knew existed.
Yeah, but that's kind of one of my overarching points here, though, is that if I'm figuring this out and I have zero classical training, like I'm just a kickboxing instructor from upstate New York, like there's no reason I should be even talking to you guys about this. And
Oh no, never think that. Never think that. There's you got to where you are right now, and don't think that there's smarter people out there working on this, because there ain't.
Well, and
You know,
when you
you
talk,
might be the guy that you were looking for.
Or they're classified.
and when you were talking to Jack about the physics the other day or a couple of weeks ago, you know, you met him like on his level, and what you said made sense, and he was like, "This guy is so." Yeah, I wouldn't sell yourself short, you know. And I mean, what they describe again, I have a lot of psychology, but like in the business world, they describe it as imposter syndrome. And the problem is we're so used to looking up when we start out in life that as we learn and grow, we're still looking around for, you know, everyone who's necessarily better. But
that's kind of part of why I wanted to just kind of give like an overview on like the Alcubierre metric and like where the state of the art is because it seems like a lot of people are talking into corners, not realizing that they're just having like mathematically equivalent versions of the same thing, almost sort of like how like the Schrodinger equation was proved to be mathematically equivalent to Heisenberg's matrix mechanics. You know, they both came out around the same time. And there needs to be an establishment of common language, you know, whether or not we agree about relativity or not, you know, everyone at least needs to be reading the same book.
Well, and physics, I think one of the difficulties is because of like competition for funding and competition for recognition and things like that, right? Scientists tend to, in all branches, they tend to silo their ideas and then they will compete. And so you end up with this not invented here syndrome, you know? And like, again, I think they say like in the business world, what you want to do is compete on a large level, but collaborate on a smaller level, you know? So. Well, guys, should we close things down for today?
Yeah, take this hat off to Jeremiah because you know he's one that wears the town.
Well, I'm going to take my hat off to everyone, guys. Thank you.
Things are hot.
Yeah, absolutely an honor having you.
I couldn't find my Santa hat for the life of me since I used it last year, so I'm at least going to like bring out your stocking or something to
there
end
you
it
go.
all off. And
there you go.
Did I fix my sound? Sorry about that. I promise
it's a little,
little better.
It's a little better. Okay, well, guys, let me
thank you.
On that note, let me wish you all a wonderful Merry Christmas, Happy New Year, and we will hit it again next year. And again, amazing things are happening with more yet to come.
Yeah, Merry Christmas, Hana Kwanzaa. So
God bless and happy holidays.
Thanks, guys.